big or is it
Yes, sir. It is visible.
visible? Okay, so we can start. Yeah.
Yes, you can
Okay,
start.
so I have 40 minutes. Let me see my time. Okay, okay, it's perfectly 10. So I must, thank the students and the promoters, Gautam and RPG, and my good friend Jay Banerjee for this opportunity. And I must say that I wish our institute is Indian Institute of Technology, but we are IISCR, Indian Institute of Science Education and Research, and hopefully we should also get into some technology related things soon, because nowadays there is pressure from everywhere that whatever blue sky research we are doing, convert it into technology. So it's a very pleasant surprise, and I am pretty happy that I got this opportunity, because my learning in optics really started in PRL. I joined there in 2002 June, and then seventh floor, where in the eighth floor Professor G.S. Overall he was there, and our colleagues J. Banerjee, R.P. Singh, and we all started our life there. A lot of students, active place. Ahmedabad is an exciting city. That is where I really started learning optics. Although I did my PhD from Rochester in the half optics and worked on quantum electrodynamics, but I realized optics is an entirely different ballgame. It is really the engineering of light with atom levels, and these people can do miracles. So I have learned a little bit, and what I have learned from PRL, I'm going to elaborate on that, and some more research which we have been doing here using the same principles. Quantum optics in phase space. So this is this Wigner function, and what I mean by quantum optics are these states which are slightly deviant from classical, like namely cat state, hidden state. As you know, the so-called coherent state is a classical state. So
Sorry to interrupt you, sir. Can you please make your presentation in full screen mode?
full screen, can you? Full screen. Where do I make it? Yeah.
Thank you.
Yeah. And I move with this one. Okay. So I'll be talking about quantum optics in phase space through pictorial presentation using Wigner function. And okay, so primarily we'll be dealing with coherence, which gives rise to interference, and this kind of interference can take place in real space. The picture which I am showing you, if you throw two stones into a pond, you find waves emanating from there. They add up constructively, destructively. So coherence and interference has been with us since our eyes are open. We literally see it, and we can do the experiments starting from a pond to two sources of light. So now the thing that quantifies this interference is so-called visibility, and it is as you are students of optics, it is related to E star E, the bilinear. So visibility can go from 0 to 1. So visibility really characterizes mathematically interference. So you may think that this coherence is well studied. Optics has been, well investigated. Born and Wolf book exists for so long, but believe it or not, in 2016, this coherence was quantified to two different kind of norms, so-called L1 norm and one, this logarithmic norm. And there is, optics people are not very happy. They think it was there, but this other group, led by quite a few, primarily from quantum information side, they think coherence was not well defined mathematically, and that mathematical definition has come out only recently, around 2016-15. So optics is a pretty much growing field. Now, this quantum optics, I also launched this Hanbury-Brown quiz experiment in PRL, and it was an eye-opening experience. And so this paper was a lecture paper, 1956. Experiment was done in Australia. One of them is an applied mathematician, and the other guy is an astrophysicist, astronomer. They were apparently looking at the light from this experiment was a later on experiment, but the experiment which was done early was looking at light from the stars. This is intensity correlation. Intensity correlation. So that was reported in Nature, and in the modern language, it is something like E dagger E, E dagger E, four-field correlation. So that led to development of quantum optics. You can ask your teachers there, all of them are experts in this. RPG का आपको बता सकते हैं. That subsequently it was Glauber and Sudarshan who took up these things. Glauber started it. Apparently there was a colloquium in France attended by Wolf who had defined the coherence. He comes back to Rochester and tells Sudarshan, with whom he was having lunch, that I don't understand what Glauber is doing. Then Sudarshan takes it up and then studies it carefully and finds out that Glauber, instead of dealing with wave function psi or electric field in their language, because they are dealing with optics, was dealing with this density matrix and expressing it in terms of this object Z, which is actually coherent state, written in complex variables. So don't have to be too mathematical. Main point is that, this is like your identity. Identity you write in terms of JZ or a complete set. You see rho, this phi is not there, this is identity. Because of rho, this phi is there, expansion coefficients. And note, Z and Z prime, two bases and two integrations. Sudarshan noticed that this object, this so-called coherent state, has a beautiful mathematical property, and it can be converted into one of them. You see, this is the beauty. This actually alpha is Z1 plus I Z2, and D2Z represents D alpha real and D alpha imaginary, which is an integration. You can go to X and Y variable, convert everything to X and Y. The so-called Glauber-Sudarshan representation, but this was Glauber, this was Sudarshan. It was a remarkable breakthrough. And the so-called P function was born from here. So people are now studying what is quantumness. Believe it or not, even now also, these things are very well understood. One thing for sure, quantumness manifests through singular behavior of P. So these are the classic papers, very readable papers. Sudarshan and Glauber, even now, it's very readable. And Sudarshan passed away without getting due recognition recently, I think 2018, May. And Professor Mukunda gave a colloquium which is there on YouTube on September 16th in a joint IISCR colloquium. You can access it. Whole story of Sudarshan's life, his achievements, his coherent state, how it came to him, his V minus U theory, you can get it from YouTube. Beautiful talk. So now, by the way, Sudarshan was a particle physicist. I was a student in Rochester. I have heard stories that during lunchtime, he would not join with particle physics people. He will go and eat with optics people. And there he learned about this problem. And a Nobel Prize, almost a Nobel Prize came to him, which he really deserved because of this P function. It goes by his name. He really showed what is classicality. This alpha coherence is classical. You can expand a quantum object in terms of a classical object, except this thing could be singular. So the singularity brings in quantum. Otherwise, this is completely classical. Quite a, mathematically, these things are well studied, but in physics, it was for the first time, this classical concept, quantum joining up, came through Sudarshan's work. Okay, so now, here is our ECG, man of remarkable personality, great scholar in Sanskrit, almost, every other thing he always chants a sloka. He came to Institute of Physics when I was a student there. He went to Puri, stayed there for 2 days to learn Sanskrit. Here is Glauber. Glauber is pretty much alive, doing well. Now, just because of this memory, going back to memory, Sudarshan's contribution you young people should look up. Quantum genome effect. With now a lot of quantum information people are doing it. Quantum computer people are realizing quantum genome effect. Basically, if you measure something, tests don't collapse. Quantum mechanics has this collapse hypothesis. The moment you measure, it collapses. So claim is that if you measure it like complete, quick succession, the state will not collapse. This is being used to sustain a state for a long time. Baidyanath Mishra and Sudarshan, they did it. Baidyanath Mishra was from a remote place in Odisha, Sambalpur. Was in JNU for a while, passed away 2 years back. Now, open quantum system, this is also another remarkable contribution, this so-called Krauss operator. It was actually Sudarshan, B minus Q theory. Just, amazing kind of person if you read about him. And he was nominated several times. B minus A theory and laser, two of them. In future, people will be still debating what happened, where did it go wrong. Okay, so now coherent state, you see, it's actually a Gaussian. If you really look at mathematically, we mean, it's just a shifted Gaussian. Coherent state is a shifted Gaussian. Here is your harmonic oscillator. Go to the harmonic oscillator. There are lots of interesting, nice books. One review article, students here have found it nice. They have written it here, review of modern physics. Recently, there's a beautiful review there in the archive. Only few months back it came out. Rukomandari Bose, Simnadar University, Dr. Avinash Khare, and Vigyan Bagchi. They have written a very nice, readable review article on coherent state very recently, 6 months back. Got published in terms of Journal of Physics. Very interesting, a lot of mathematical developments you can learn from here. You can use it in other fields also. Now, okay, so how do you create a, this, you see, this was done, created in our, using this tool available, strawberry field. Nowadays, these things are available to do quantum computation. You can actually play around. IBM US kit, strawberry field. I think this was done by our student here, Gargi. So you can actually play around. And you can do quite interesting things. You can actually create coherent state, you can create cat state, you can see what happens, all those things you can do. I have seen US kit. Students become expert very, very quickly. So I hope that you can play around with this. So you take your harmonic oscillator vacuum and then apply the so-called displacement operator, exponential alpha A dagger minus alpha star A. This object, although it looks, A dagger commutator is equal to 1 harmonic oscillator, but this object D has interesting property. If you, go to, for example, Sudarshan's own book on coherent states and other books also, you'll find out that, it has beautiful mathematical properties. It gives rise to the so-called projective representation. So if you, on your time, you read it. Now, if you go to, this phase space, coordinate and momentum, or these people call it quadrature. They deal with electric field and its corresponding momentum. So this coherent state is a localized object. And, if it is here, it is localized along X Gaussian real axis. If it is here, localized around x2. If you take coordinate and momentum, in the coordinate axis, it will be shifted Gaussian, exponential minus x minus some alpha 1 square. Here it will be x1 minus I alpha 2, I. Now you will find out that in the real space, if there's an I exponential minus x1 plus I alpha, you go to Fourier domain, you'll find out it will be localizing momentum. So coordinate and momentum localization, wave functions, shift is real or imaginary. It's very beautiful. So now this concept is coming in weak measurement. That you want to do momentum localization, you make that I alpha I with an I. How do you do it? There are actually optical ways of doing it. Optics people really play magic. So by playing around with the Gaussian, converting alpha to I alpha, you can actually make this momentum localized. Why do you need momentum localization? Because you want to suppose use it for creating, chips, like fine lines in chip. You want very sharp beam. So you can play around, use some optical means, convert it to I. You can create a very sharp beam, very well-defined momentum. And believe it or not, those things are actually becoming reality. Now you take this Gaussian, shift, for example, its width, put a exponential x minus alpha whole square divided by beta. This will become asymmetric. This is a squeeze state. Squeeze state, although we have read about it, very simple mathematically, was created very recently in the context of LIGO. My teacher, for example, Mandel, who is no more, he created it in Rochester, context of gravitational wave detection. Why? Because gravitational waves give rise to very small delta x. So to measure it, you need light, which should show that kind of effect. So this metrology, or quantum metrology, this state was created primarily towards measurement of gravitational waves. Okay. Now, properties of coherent state, it's an eigenstate of A. A is not a coherent, A is not a Hermitian operator. In our life, we have been all the time taught these fellows, Hermitian operators, eigenvalues are measurable. But here is some object which is A, not Hermitian, but alpha is completely physical. Laser light, what you use for teaching in the class, is an example of alpha. Okay. Now, alpha, beta, they're not orthogonal. So, but if the distance becomes too much, this distance is large, then they become nearly orthogonal. This is a very interesting thing. You can check up in the literature. So alpha is not complete, over-complete. Alpha is over-complete. When you may ask, when does it become complete? This was asked by none other than John von Neumann. And he showed this alpha is a complex number, alpha 1 plus I alpha 2. Instead of taking complex number alpha 1, alpha 2, if you make it a lattice with an area in the pi, namely pi times h bar, then it becomes complete. So somebody who is a bit mathematics oriented, try to prove it, you will find very interesting development using this fact, particularly in the works of which our Professor Subhash Chaturvedi and also Mukunda and Simon also, who showed that there is a finite dimensional analog of coherent set, which is finding using technology. So that this beautiful result due to John von Neumann, which came because of some identity of these well-known theta functions, which, by the way, our art science people, Professor Goswami and his students make use of in PRL. These are basically solutions of heat equation. That beautiful property of theta function are used by John von Neumann to show that it will be complete only when alpha is lattice, and that area pi h bar. So this kind of coherent state was used in Hyderabad when I was a faculty there by our Srinivasan, Chaturvedi, and I think Professor Simon. Whose first paper on very phase came from there. You can check out some beautiful paper. So coherent state to Indians have contributed quite a bit, as also to light. Over complete basis, identity can be broken up. Okay, now, so this is coherent state. You can actually find out that A dagger A is a number operator, and its average is alpha mod square. So physical meaning of alpha is that alpha mod square is the number of photons, average number of photons. A lot can be learned about it, which I will leave it to you. Now, cat state. This Schrödinger, of course, was a very smart man, no doubt. So he came up with this idea when he saw this experimental thing become very ambiguous, collapse of state. So, before you measure, the state can be superposition. Now, a lot of things have been written, a lot of understanding has come, and the superposition and measurement and collapse is still not much appreciated. And believe it or not, one reason why engineers and others are scared of quantum mechanics, which we physicists love, is this measurement. The moment you tell them that the measurement leads to collapse of state and completely arbitrary, they think quantum mechanics can give you nothing. That is where we score. So physics people don't give their secret away. Otherwise, the engineers will ask you to do their dirty work. So, basic point was that a superposition. This is just a superposition state, very fancy name for that thought experiment. That if your measurement leads to collapse of the state. So there are two states. This can be double well potential. You look at Feynman's book. For example, ammonia molecule. There is a double well potential from which measure comes out. So measurement leading to collapse of state. Dramatically here, dead and alive. So what is the realization? Realization is superposition of two Gaussians. Which is your alpha and minus alpha. If you take this, which Schrödinger used, is called a cascade. And here you can see it's a bit tricky because this cascade, they are not orthogonal, right? So now you can distinguish them macroscopically because you have, as I showed you, if you distance is infinity only, we distinguish them. So but this is broadly an example, and a physical example is the double well potential, which all of us are familiar. Okay, now. So you can, of course, odd and even. Now you put an I here. So this is actually a quantum state. The moment you ask quantum, all hell breaks loose. What is the meaning of quantum? And people say statistics. You take the photon, this E minus T to the power n. What is the Poisson statistics? For the coherent state, tells you it is classical. But here, this you store state, put an I here. It also shows Poisson statistics. So it's not very clear. For example, another measurement which I'll show you is that the Wigner function should be negative. Okay, but there are also examples, counterexamples. So even now, this area is not very clear. So keep that in mind. That very recently, these cat states have appeared. You can check out something called cat code. You can actually use them for quantum computation. They have been demonstrated in a PRL paper, very of last year, I think, And RPG and our PRL people will remember that Sriramon Muralidharan is also co-author of that. Likin, Sriramon Muralidharan, they are co-authors of that. Yale University paper. Yale University is a leading place where these kind of tests have been produced in circuit QED, and actually a lot of experiments have been done, and now we work also. So odd and even. Now let us see. So as I told you that one way of seeing that they are classical or quantum is statistics. So Poissonian is this, E minus T to the power n by n factorial. That is your Pn. So width and average, they're related. Sigma is equal to square root of n bar. Now SOP is this. Super is more flat. Poisson is here. Poisson is a bit asymmetric. Asymmetric was one side. Now, as I just wanted to point out that coming from Hyderabad University and then PRL, I would like to point out that we were fed and born, every morning to evening, coherent state. Professor G.S. Agarwal in Hyderabad moved to PRL, and Professor Mukunda, Professor Subhash Chaturvedi, RPG was also there. Where is my RPG? Where was also there? Professor Puri, who is now in IIT Gandhinagar, Professor Srinivasan Chaturvedi, and the whole group were talking about coherent states. So I also learned a little bit about that. Now I am finding them useful. Okay, so you see, if you go to Wigner function, you will see miracles. That there will be interference in the real space. It's just sum of two Gaussians localized on the real axis. The moment you go to Wigner function, you will find out because in the phase space there's interference, you will see interference patterns, and this interference pattern leading to zeros and negative. And this negativity thing is apparently the one which gives rise to quantumness. Double well potential, dead and alive. So superposition of dead and alive leads to this. Moment you measure, either alive or dead, one Gaussian, interference is gone. And this phase-space interference idea was actually brought to physics in 1980s only. And Wheeler, Feynman's supervisor, Wheeler and Sly. And Wheeler was one person who was working on particle physics, gravitation, those things half of his time, other half on quantum theory, collapse of wave function. So I was surprised to see in that late age, in 80s, he brought this interference in phase space and pointed out that this quantum interference is actually behind quantumness. Okay, so now Wigner function, you are all from PRLs, so I don't have to define for you. Take this wave function, shift it by y by 2, minus y by 2, take the so-called Fourier transform kind of object. These are the information about coordinate and momentum. And whole thing is that here, X and P become numbers. There is no operator. With this object, you can do just like you have done in classical mechanics. No operator, no problematic, just take the function. So what is quantum mechanics? Quantum mechanics comes from or non-classicality, from the fact that it is not strictly probability distribution. It may have negative values, it is not probability. There is another beautiful piece of work by Srinivasan and Chaturvedi, and I do not know who is the other author, that you can actually positivize it. You can go to a higher dimensional space and make it positive. Then more variables will be there. So in the context of this so-called quantumness, the higher dimensional volume may play a role. So you may look up those kind of things. Okay. Now experimental people can measure Wigner function. I just heard from a talk that apparently there is a smart way of getting information at one go using this quantum state tomography. And reading it, I'm not very familiar. Okay, so there are in different ways. This P function is the so-called P function, Q function, Wigner function. They correspond to symmetric ordering of operators like A dagger A plus A dagger, and then P function is probably what? Q function is one way you keep A to the right, one way you keep A dagger to the right. Glauber pointed out in that classic paper of 63, one of them is more physical. Okay, but for physics people, always we take this symmetry kind of thing. I have been brought up with symmetrization of operators, A dagger A plus A dagger by 2, which is Wigner function. But take this Wigner function, integrate of P, you will get psi x mod square. Integrate of x, you will get phi p mod square. All the wave functions of X and P nature, everything is here. Okay. So one thing occurred to me, I'll just leave a hint if some of you can figure it out. We know that in coordinate space, xp commutator is equal to is bar. If you take x as x, p becomes s bar over by d by dx. Momentum space, p becomes p, x becomes is bar d by dx, d by dt. Derivative of 1. So what do you think will happen if you deal with Wigner function? I'll just stop here. I give your curiosity. Now, okay. So, there are experiments. For example, 2019, you can check out this Nature Photonics. There are quite a few experiments recently, 2019, 2020, generating this kind of thing. Why people are certainly interested? Because as I told you, the so-called CAT code has been found very effective in error correction. This paper I was reading, it's very useful for error correction because moment you take event state, if it loses a photon, it becomes odd. Odd even you can distinguish because there's a parity difference. You don't have to do much experiment. You can quickly differentiate because there's a parity difference. And you can actually do a quantum operation to bring it back. So this loss of information, bringing it back is here represented. And these are the tomograph. You see, one of them is even, origin of 0, odd, origin is 0. So the moment you go from even to odd by losing one photon, 2 photon loss brings you back to the same place. So it is very robust against photon loss. 2 photon loss, you are back to whole game, the state you were there. 1 photon loss, because it's odd, you can quickly do an operation through an ancilla, bring it back here. So this points out that these things are very robust. If you use them as a logic gate, very robust against error. Only 2019. Okay, so now my journey into this thing started. How am I doing in terms of time? 29. So I have 10 more minutes. Okay, because I was writing a report to ISRO because I was division head in PRL, and I saw this paper of Professor Agarwal and Pathak, and the sub-Planck name was there. I was very curious and read the paper from where they had looked at the decoherence of this state. And lo and behold, very nice picture, sub-Planck. What is the sub-Planck? It struck me. And furthermore, I found all these things have been done using only exponential, namely Gaussians and cosine signs. It struck me that you can write a paper in Nature on using only the mathematics of Gaussians and cosine and sine and interference pattern. You see this interference, and what is sub-Planck? So there are basically 4 Gaussians. I think I have written down. If you read the paper, it says P10 state, 4 Gaussians. 2 localized on the real axis, 2 on the momentum axis, coordinate and momentum. Go to the Wigner function, you see beautiful interference pattern. And you find 0 here. Black is 0. And we know, you try to convince yourself, this is like lambda by 2. Okay. So zeros are measurable. The moment you find a 0, whatever you do, that 0 is not going to go away. So they are measurable quantity. Wave function 0 gives you numbers. For example, 1 0 excited state, 2 0 second excited state. So these zeros are in some way measurable. So lambda by 2 is here. So this tile, which is 4 times this unit tile, is the minimum area of the phase space which you can measure. And direct so it is less than S bar. Is it really physical? People have done experiment and shown that it is physical. And then we're using laser light, where S bar is lambda. Because per axial approximation, S bar is lambda. So this I'll show you some experiments. So this really struck me. So then with our student Utpal Roy, Suranjana Ghosh, and my colleague Jay Banerjee, we actually showed that I'll show you that paper, that you can actually realize it by molecules like sodium iodide. So I was told that some group in Germany did that. Okay, so you read that paper, very beautiful paper, very simple mathematics. So this is the experiment, time frequency domain. They took this, this is a P10 state, but they took gas state which I was mentioning, and they showed that you can use this phase-space structure to have delta nu. You can measure delta nu less than uncertainty relation. Time frequency, soft Fourier sensitivity. Soft Fourier sensitivity. There is another paper, 2016. Again, you see beautiful patterns. experimentally realized. And here it is the kitten state. So indeed you see zeros experimentally. This was used using laser. So there X bar is lambda. Okay, now these are all nice, beautiful patterns. Now simple Gaussians, sum of Gaussians gives you this. So I call it quantum rangoli. If you don't like it, take more of them, you will have quantum carpet. So quantum carpet is there used in the literature, quantum rangoli is not yet. So I claim in this seminar that I have this, right to use this quantum rangoli, which Indians have been using for quite some time. So this work was also done in PRL 2004, generalized coherent space superposition, giving rise to beautiful color patterns, which people can use. People have been using these kind of things in postcards. Okay, so this is the paper which I was referring to, that you can actually see molecular wave patterns. Okay, and there it is not as beautiful, but you see similar kind of structures, and you can actually measure them experimentally. Very recently, for example, there was a complaint about the states, that the states are not very robust. You can actually use them for quantum metrology. You can measure delta nu. But the moment a little bit of noise is there, the states get perturbed. Last year, these quantum hypercube states have been, given and produced experimentally. They are very robust against, beautiful patterns. You see, it is really Rangoli, extremely beautiful patterns, and they are very robust against, this kind of noise, and they are very useful for quantum metrology. 2019 only, and so now, as I told you, that people have actually started generating this kind of states, CAT4, and this has been done in microwave only 2019. And you can see this pattern, two Gaussians. Moment you see two Gaussians, now 2020, one group, the sum of four Gaussians, 1, 2, 3, 4. So primarily for metrology and robustness against error correction. So, okay, so now you can actually do it for sensing and many other things. Now, when it comes to sensing or measurement of delta X, delta P, so far I have not dealt with entanglement, only interference, namely coherence. You can actually do a lot of things, learn about atoms, their entanglement, their coherence, their discord, many other features through light, looking at light far field domain. So for that, a very simple model, whose reference I'll give you, you can actually write it like spin two-level systems, simple two-level systems, raising lowering operators, and the energy level difference is omega. You can actually couple it to light. There will be light emission for explicitness, and I have put three atoms, 1, 2, 3. On the line, they will be emitting light, dipole coupled, and if you look at light, then you can actually learn about it. What do you learn about it? For example, you read this Gauger or Wolf Mandelbrot paper, this E plus, the positive momentum part, or E minus, they are the quantities which are actually seen experimentally. You look at electricity in field domain, you will have this kind of structure, and look at intensity. So this is mathematics, don't worry about it. The entanglement nature comes through this kind of object, uncertainty relation. CHHS inequality, Bell inequality, they come through this kind of things. So now you measure, these are all mathematics. Our Mithilesh, who had been to PRL, and I think showed some poster there, he is behind it. So this phase here is the one which brings interference, which brings information about the lattice separation and many other things. All right. So first of all, you observe that there are two different phases, which are predicted a long time back. Here, of course, it's not a phase transition. It is more like a crossover, uniform, non-uniform phase, showing interference effect. So now, furthermore, you look at different kind of quantum correlations. You can also infer about them as a function of temperature. So called discord, negativity, concurrence, many things. They all come out from the monogamy. 3 particles means monogamy. Those things you can infer, and all through light. So look at in far field domain, look at light. From there you can actually infer. Monogamy, just for the sake of mathematics, we define like it. Again, something which people are still studying. Many of you can take a look at it. All right. So I think I am okay. I have 3-4 minutes. So let me see. Monogamy. Monogamy basically means that suppose there are 3 particles. 2 particles are completely strongly entangled, like Bell state. the third particle cannot get entangled. So that is the word which brings in monogamy. So, okay. So now that also you can check through behavior of light in the particle domain. G2, photon-photon correlation, Andori-Brown quiz can be also computed. That also you can see how it behaves. Then this radiance witness, which tells you about the nature of the radiation, that also can be computed. So various kind of things about light can be inferred. Through that, the atoms who are radiating light, their entanglement structure can be probed by looking at light coming out of those kind of sources. Okay, so I think I'll stop here. Thank you. So now you can ask me questions. It is like carrying coal to Newcastle because I learned this thing from PRL. So I thought, let me make you interested in these kind of things, in PRL itself. Thank you.
Thank you, Professor, for the wonderful talk. Now we will take some questions. So I have one question by Professor R.P. Singh. So he's asking, in even an odd cat state, one is sub-Poissonian while other is super-Poissonian. So if Wigner function will be negative for both or only one?
No, they are negative for the both. So, for example, at the origin, as you see in the picture, these are basically sum of two Gaussians. If it's odd, wave function will vanish at the origin. That will show as the Wigner function becoming zero at the origin. Whereas in case of even, it will not be zero at the origin, but it will be zero somewhere else. But they will show, interference effect, and also particularly interference in the momentum domain. Zeros on the real axis. Odd, zero at the origin, even zeros away from the origin. In fact, that is how in the CAT code they detected the loss of the photon. The moment the photon is lost, even state, they deal with the even space only. Photon is lost, goes to odd one. Odd to parity measurement at the origin, immediately they know that there is an odd state. Ancilla state corrects it, brings it back to original one. I hope RPG is happy.
I hope so. So the next question is from Anindya Banerjee. He's asking, you have mentioned that a negative Wigner function can be transformed to a positive Wigner function in higher dimensions, but generally the negativity of the Wigner function is used as a measure of quantumness or quantum advantage. Can you comment on the implication in that case?
See, this is a very, very interesting question. See, for example, if you are in higher dimension, right? But if you have actually a plane, I go to 3 dimension, but actually all my points are lying on the plane. Then effectively I'm 2-dimensional, right? I can define my coordinate axis so that I'm in the XY plane. Everything is, all the points are lying on a line. I can draw a line so that they are there. Now, if I cannot do that, then I'm truly in 3 dimensions. Same thing happens here. This paper is a very nice paper by Srinivasan of Chaturvedi. I think Professor Oral is also author. I don't remember. So if you go to higher dimension, if you try your best to come down to a plane, then you can come to a plane, you can get a classical picture. If you cannot, then it will be truly quantum. Just like negativity. Negativity here in the higher dimensional space goes to extension in higher dimension. So I am still trying to understand. It's a very nice paper. Whoever asked the question, who asked the question, please read it. Very nice paper. And Professor Chaturvedi is in ISR Bhopal. We can actually call him. He will go by boss to PRL.
Okay. So there is one more question for Vardhan. So can you elaborate a little more on strawberry field?
Vardhan is expert on QS kit. So you pay us some money, we'll elaborate. Otherwise, why should he tell you? So Vardhan, I will get you connected with Gargi. She is our local expert. So I am actually beginning to see it from a distance. So it is somewhat like QS kit, but it's a Canadian company. So I am just beginning to learn. Our some students here, they have become good at it. I am actually learning from them. Optics kind of thing you can really do well. Photon, optical linear optics based quantum computing, you can do it. They are completely like QS kits.
Okay, sir. So there is one more question from Vineet Kumar. So he's asking, does that mean quantumness is dimensional dependent?
No, it is not. In some sense, yes. For example, You may call it negative, positive, or that negativity, if you don't like it as a positive distribution, you go to higher dimension. So in that higher dimension, everything is positive. Okay. See, somehow you wanted a distribution which will be positive because you want to use it as a probability distribution. So in that case, you have to go to higher dimension. So that higher dimensional extension is a measure of your quantumness. Also, if you are happy with negative things, call it quasi-probability like Wigner used to do, then you can stay in Wigner function, not a problem. Okay.
Okay.
Thank
so
you.
if there is no more question, let's thank the speaker once again. Thank you, Professor, for the wonderful talk.
Thank you. Thank you.
Now, for the next talk, we have Professor Anirban Pathak. He is a professor at JP Institute of Information Technology, Noida. And at present, he is leading a research group mainly focused on quantum optics and quantum information with specific interest on quantum cryptology. Today, he will be delivering his talk on quantum hacking. Never trust your optical elements. So presently, he is not here. So we will play his pre-recorded video. So I request the host to play the pre-recorded video of Professor Anirban Pathak. Okay. So the Anirban Pathak, Professor Anirban Pathak is here. So.
But you run the video, and I will address the questions.
Okay, sir. We are playing your pre-recorded video. So I request host to play the video.
Good morning, everyone. Before I start, I would like to thank organizer for inviting me to deliver this talk. Actually, Gautam and his students keep on inviting me in every edition of this conference, but I could never been able to physically reach at PRL for some reason or other. And this time also it's because of COVID-19. The lecture is happening in online mode, but still at least this is giving me an opportunity to talk in this conference. So once again, I thank Gautam, RP, and all their students for organizing this nice conference. So as the title suggests, I'll talk about quantum hacking with the intention to establish that if you are a quantum cryptographer, you should always question your optical elements, because there may be imperfections and that may lead to some kind of possibilities of hacking, some possibilities of attack. And it has often happened that you are trying to get rid of one attack. For that, you introduce a optical components, a circulator, and the circulator itself caused some new attack. So those ideas will be clear, but the talk is small and it will have a couple of parts. So in the first part, we'll start talking about what requires to establish quantum supremacy or advantages of quantum mechanics, so quantum computing or quantum communication. So we'll mention these as non-classicality. So non-classicality is something which does not have a classical analog. So it can be a non-classical state, it can be a non-classical property. So examples of non-classical state are squeeze states, anti-bunch, entangle. So they don't have any classical analog. So they can do things which cannot be done in the classical world, or the non-classical properties like collapse and measurements. So if you want something which cannot be done in a classical world, so you have quantum supremacy. So you must have some properties or some states which is not available in classical world. So we'll start with non-classical states. We'll show that this can be generated in many physical systems where matter and field interacts, and then we'll show that this can be used to design different cryptographic schemes, and finally to implement those cryptographic schemes you will require optical elements. So why optical elements? So in quantum information the basic unit is qubit, and qubit can be realized in superconductive means like transmon qubits. It can be used in ion trap, it can be realized in NMR, but the moment you talk about communication, it has to go from one place to other place. You cannot send a superconductive qubit from India to China or China to Austria. So you require optical qubits and photonic qubits. So, and then when you implement this cryptographic schemes, you will require many optical elements, and they may be imperfect. And the biggest advantage of quantum cryptography is the claim unconditional security. So this unconditional security is a bit theoretical, because in reality, when you implement, you have to use devices, and the devices can have imperfections. So finally, we are interested to answer these questions: why a quantum cryptographer should never trust the optical components used by him. So in two parts, first we are showing that we work on non-classicality, we use non-classicality design protocols of cryptography. Then we'll create a bridge by showing that to implement those protocols of cryptography, you need optical elements, and then I'll show that how optical elements can be used to design attacks. So before I go to the main technical part of the talk, I just quickly brief where we stand. So I don't show any picture of quantum supremacy experiment of Google, because that's on computing and we are more interested in communication. So this is more on sensing. A quantum radar has been built as it is claimed by China. This is a soccer stadium in 2010 Soccer World Cup. The BB fiber optic network was created and BB84 protocol was implemented to keep the information about the players' movement as much secure as possible. This is showing, the third one from the top is showing a satellite link between China and Austria. So a key was created between the satellite and China when the satellite was above China. Then another key was created between satellite and Austria when the satellite was above Austria. And then the satellite announced the XOR value of the key to China. And then China XOR it's with his own key. So it's China, key China, XOR key China, XOR key Austria. So key China is removed and he got the key available with Austria. So they have a key generated by quantum means, and then they use a video conference by encrypting it with the key. So the satellites are classical. They have a payload for doing quantum communications, and the similar kind of satellites are available with different countries, and mostly they are located in low Earth orbit. And India is also planning to do that, and PRL is supposed to be an important player in that, along with ISRO. And so it's interesting to talk at a PRL conference. And to complement with this status kind of thing, I must know that India has started a program called Quest, and it's also going to start a bigger program called National Mission on Quantum Technology and Applications. So students may feel excited that they will have big opportunities to work on state-of-art experiments in India itself. Now, as I mentioned, that to achieve any quantum advantage, you need a non-classical states, and non-classical state is one which does not have any classical analog. But that's a layman's definitions. Mathematically, we define it like if you have a density matrix rho, you can write it like P alpha, which is the global solution P function, ket alpha, bra alpha, D2 alpha. So this ket alpha is a coherent state. So when I can write it like a mixture of coherent state, then P alpha is positive. If P alpha is not positive, that means that I cannot express the state as a mixture of coherent states. So when P alpha is negative, that implement that I cannot write there's a state as a mixture of coherent states, and that is gone. Then the probability interpretation fails. We call it quasi-probability distribution, and then the state is considered to be non-classical. So this is the definition which will follow, but P alpha does not exist in all systems. P alpha may be ill-defined. It's not a very well-behaved function. So experimentally, I cannot identify P alpha, so we use many other things to identify non-classicality. Then we understand that non-classicality is important, but we have to measure. And in cryptography, I'm interested that if I increase the amount of non-classicality, should I get any advantage? So how do you measure non-classicality? There is no unique way. So one option is that you have a single mode non-classical state, you send it through a beam splitter, and you send a vacuum from the other port of the beam splitter. In the output, you will get an entangled state. You measure the entanglement using entanglement measure. So concurrence, negativity, etc. we use, and then we see that these measures are not monotone of each other. So that's a different problem, but remaining within one measure, I can see that if the increase in non-classicality helps me in achieving better security or things like that or not. But as I mentioned, that P is not directly measurable, so there are many weaknesses. So one such thing is a squeezing, anti-bunching. So these are all weaknesses of non-classicality and expressed in terms of moments of annihilation and creation operators. So first and of course, entanglement, higher order entanglement, Bell non-locality, steering, all these things you can manifest a kind of non-classicality. So these are called weaknesses because most of them are not measure of non-classicality. So how we do, we usually write a Hamiltonian, then say H, and then write H comma A, H comma A. So I get A dot, A double dot, etc. And then we use that either in Taylor series, that's called short time approximations, but we use a sophisticated method called Shane-Mandel approach, which gives me perturbative solutions. So this kind of interaction Hamiltonian we have, this shows in many physical systems. So I'll flash through because I don't have time to describe all the system. So here you can see that this is an optical coupler. So there are two fibers and the light is coming from the same direction. So this is called co-directional coupler. And here we have shown that anti-bunching, entanglement, quantum Geno effect, etc. So similarly, if the light propagates into opposite direction, then it's called counter-directional optical coupler. And in counter-directional optical coupler also you can see squeezing and entanglement. So this is showing and etc. So this is the optical systems you can see in Bose-Einstein condensations, double well, and many other systems. So as I asked here that where do you find non-classical states, where not? So just I'm flashing through some examples of our works where we have seen useful non-classicalities. So then this is a Raman kind of process. So how, if you are familiar with the second quantization, you know that A dagger A omega A is the free field Hamiltonian corresponding to mode A. Similarly, this is the free field Hamiltonian of mode B and so on. Then this is describing the interaction. So there are two kinds of interaction, that A is annihilated and B and C is created. So one photon in A mode is annihilated and one photon in B mode and one photon in C mode is created. Similarly, one photon in A mode and one photon in D mode is annihilated and so two bosons are annihilated and one motion in D mode is created. So then we see different kind of interaction. So this is a Stokes-Phonon entanglement. So Stokes mode is a photon, this is a phonon. So you can see that negative parts depict that photon-phonon entanglement. So this is showing Stokes anti-Stokes entanglement, pump anti-Stokes entanglement. So different modes can get entangled in Raman process. So we have studied and hyper-Raman process, degenerate, non-degenerate, BECs. This is showing some optical cavity. Then we have studied PT symmetric system. So the whole point is that non-classicality can be seen in many places, and this non-classicality can lead in many optical systems, and you can generate entangled states and such things and use it for quantum communication. So in quantum communication, there are many facets. So in general, we tell that most people talk about quantum key distributions, but quantum key distribution is that Alice and Bob, by using quantum means, some way establish a random sequence of zeros and ones, which has two copies. One is with Alice and one is with Bob, and that they later use for communication. So that's the key. So now key is required to be random. Now in quantum key agreement, both QKA stands for quantum key agreement. Both of them must have equal role in generating each bit of the key. So one of them will not be able to control what is going to be the key. So that's not the usual QKD. Then there is quantum secure direct communication and DSQC. So the idea is that is it essential that first I have to generate a key and then only I have to communicate, or there is a quantum means where I can communicate directly. So the direct communications protocols are interesting. So one example I can give you. So think of that you share, Alice and Bob shares an entangled state. So Bob creates an entangled state, keep one particle with him, say Bell state 0, 0 plus 1, 1 by root 2, keeps the first particle with himself and sends the second particle to Alice. Now Alice, if you want to encode 0, does nothing and sends back. So when it returns back to Bob, Bob measures it and get the same Bell states as he prepared. And when Alice wants to send 1, Alice applies X gate. So then 0, 0 plus 1, 1 becomes 0, 1 plus 1, 0. So a Bell measurement in Bob's end will be able to identify which communication Alice has sent. So it's some added security measure. This is called ping pong protocol. And this is an example of direct communication. So there is a two kind of direct communication, QSDC and DSQC. So in QSDC, or quantum secure direct communication, Alice, Bob at the end does not require any additional information to decode. But in DSQC, for each bit to decode, she requires one bit of information disclosure from Alice. That's called DSQC. But in all these cases, you see that Alice is only communicating and Bob is receiving. So if it becomes two-way, then it's called quantum dialogue. So quantum dialogue is a protocol in which Alice also communicate some information with Bob, and Bob do communicate some information with Alice. Now, each of them has now a control version. So there is a third party Charlie. Only when third party allows, then Alice and Bob can communicate with each other, be it a key. So there can be control QKD, there can be control QSDC, there can be control quantum dialogue. The control quantum dialogue is most general protocol, because if the controller is exploited, then it reduces to quantum dialogue. If one party does not communicate, then it becomes QSDC. If one party does not communicate and there is a controller, it becomes control QSDC. So we are interested in quantum dialogue of control nature. Then the users can be semi-honest. So semi-honest means they follow the protocol properly, but still they want to cheat. And so many different ways each are connected, and there can be hierarchy among the users. So we have designed something called hierarchical quantum secret sharing. So it's not possible to explicitly describe this protocol, but this map shows that there are different kind of protocols, and all are not restricted to QKD, and even all these things are not restricted to only for communication. So there is a class of a scheme called secure multi-party communications. So secure multi-party computations, in SMC we consider the tasks which require security, but they're not really communication, they're a kind of computation. So for example, voting. So in voting, somebody has to count how many number of votes have been casted for a particular person, yes or no. So there are protocols we have designed protocols for quantum voting. There are e-commerce, that there is a bank, there is a merchant, there is a buyer, and they communicate in a secure link. There are quantum auctions. So all these things falls under secure multi-party computations, and we can design schemes from them. So this briefs some of our activities. So the lower part shows the entangled steering and non-classical states in physical systems have been reported here, and then we implement them to implement hierarchical quantum communications, teleportations, quantum voting, control direct secure quantum communication. So without describing the schemes, we just want to leave a message. The message is that there are many tasks which can change the life of people can be done in a quantum manner. So for example, implementation of quantum voting can strengthen our democracy. Implementation of quantum auction, where possibility of corruption will reduce. So that can reduce corruptions too. So many things we can do. And just to note an example of quantum dialogue. So Professor Panigrahi gave the last talk, the talk before me, and this is some work with him that we designed asymmetric quantum dialogue scheme. And so these are showing some Pauli groups of unitary operations. So before I go into that, I just tell that, suppose just like in ping pong, you have a Bell state, and Alice and Bob shares one copy is with Alice, one qubit with Alice, and Bob has one qubit. Now Alice encodes his thing with the Pauli gate, say X gate, Y gate, Z gate, or identity. So if she wants to send 00, applies identity for 01. So just like dense coding operation, and send it to Bob. Bob do applies a similar operation and send it back to Alice. Alice does a measurement. So Alice, suppose Alice has sent J plus and Alice has got J plus Bell state, then Alice knows that the product of her encoding and that of Bob's encoding is identity. And now since she knows that what she encoded, she knows Bob's encoding. And she announces it. And once she announces it, the measurement outcome, then Bob knows the initial state, the final states, and his encoding. So Bob will also know what was Alice's encoding. So it's a two-way communication. It's called quantum dialogue. Now we thought about a asymmetric quantum dialogue in which one party is capable of sending more information and other party sends less information. So what kind of operations are allowed in which states? So there are different kind of Pauli groups, the groups which are created by mutual operations between the Pauli gates. And so if you are working with Bell states, so this shows that which gate can be used to do quantum dialogue and asymmetric quantum dialogue. So these are some glimpses of things that can be done with the non-classical states, especially with entangled states. And now we want to move to how to implement this. So this is something which Mitali presented in the last version of this particular workshop. And I just take it and just want to give you the message that there are 4 lasers and you put some polarizer. So this laser is giving you vertically polarized light, this is giving you horizontally polarized 45 degree, 135 degree. So four states that we used in DB84, and then you use PBS, etc. to mix them. And this is a scheme for implementation of controlled quantum dialogue. We don't need to understand the scheme at the moment. What we understand that there are polarizing beam splitter, there are half-wave plate, there are detectors. So this is how you have to implement. So ideally, when I present a scheme of quantum dialogue, it may appear secure. But when I really suggest a physical implementation, then many optical elements may come, and these optical elements may be prone to attack. So unconditional security claimed in theoretical schemes of quantum cryptography are subject to the realizations of the optical elements. And here is a summary chart that many devices use, like beam splitter, Faraday mirror, phase modulator, and a lot of attacks on detector has been reported. And some of them are reported on commercial products also. So to begin with, I mentioned an optical component, which is pretty interesting. It's called circulator. So if the light beam comes from port 1, it goes to port 2. And if it comes from port 2, it goes to port 3. So it's following this path. So now if it goes from port 1 and reflected back, then it will not come back to port 1 or interfere with itself. It will go to port 3. So keep this in mind. Now you see a Trojan horse attack. So from the Greek epics, you all know about the Trojan horse. So every optical element actually backscatters some amount of light, and that leads to this kind of attack. So first you understand this structure. So this is with Eve. Eve has a laser, and here is a beam splitter. So Eve splits into two parts. So one part goes directly to the detection scheme, so which is your reference thing. The other part goes through a modulator and then reflected, and then this is the circulator. So from circulator, it comes here, then it goes here and goes to Alice's port, and it's reflected back. But when it reflected back, it does not go to the same port. Because of the circulator, it comes down, and in the detection scheme, you can compare them and say determine the phase introduced by the Alice's device. So what it lead to? You see now that Alice has a protocol, and Alice has many optical components. So there is a connection, there is a variable attenuator which you use in fiber, there may be a detector, there may be a phase modulator PM, and when the light is reflected back, and looking at reflected light, you suddenly see that there are increase in reflected light, and you can find out the time, that at what time it returned back. So you can find out the component in the sequence from which component it has returned back, and then you can identify a phase and get partial information of what Alice's equipments are doing. So that leads to a attack. So the basic idea, I'll elaborate through some figure, is that Bob is sending, so Alice is sending through some encoding devices and the pulse is coming. Bob is sending back a stronger light which reflected back, and when it reflected back, if you consider it's a coherent state with intensity square root of mu in, so intensity is mu input, and so mod alpha square is the intensity, so it acquires an additional phase e to the power I phi a. So that leads to the information which you desired, and this is called Trojan horse attack. So I show another picture from a paper of Marco Lucamarini. So you see, this is a cleaner picture. So there is these are the devices. There is a laser, junction 3, intensity modulator, junction 2, beam splitter, air gap. And so when it will reflect back, who will reflect back first? So you start from this C. So C will reflect back fast, then J1, then the polarizing beam splitter. So from this intensity is suddenly increasing, and from this back reflected light, we can identify which component has worked and part of their effect. And so this is really implemented, and looking at these pulses, so you cannot get rid of this, means your optical components will reflect back some light and somebody can attack. So what is the strategy? The strategy is that, so at this point, Alice must apply a circulator. So nothing should return back to Alice's port. So only things will go from Alice's port So just return back. If Alice would have a circulator here, then the light should not have entered Alice's port. So something like this. Alice should have put a circulator. So the Bob sending light should go here. It should not have come to Alice's port. So this is one strategy, but circulators can even be attacked, and I have not included it, but Jacob Weinstein and his team had shown in BB84 a kind of attack which exploits actually the backscattered light from the circulator itself. So anyway, so here is a nice cartoon to explain the Trojan horse attack. So the boy is telling the girl, so you can consider them Bob and Alice, that I don't trust you. So the girl is surprised and asks why. So because the boy said that because you reflect light. But the girl says, that's why you can see my beautiful face. If it was not reflecting, then you could not see me. But Eve can also see you. So that's the problem. So whenever you have an optical element like this girl and she reflects, then that reflected light can be used by Eve to exploit and attack your system. And that's what is Trojan horse attack in brief. Now I show you a very simple attack. So as before, so there are four light sources, and they are creating 4 different polarizations of light for BB84 implementation, V, H, A, D, etc. So this is diagonal, this is anti-diagonal, horizontal, vertical. And now Eve sends a strong pulse with a vertical polarization. So each light, how much of this light will reach Alice's port, that will depend on the polarization. So vertical light with 100% intensity will cross through this vertical polarizer, and the intensity temperature of this laser diode will increasing light emitting diode. In this case, no light will come, so this will remain the same in the same wavelength, lambda 1, and that's H. So this will increase maximally, so this becomes lambda 3, and this is vertical. So in both these cases, 50% of the light enters the light source and changes its temperature, so it reaches to some other wavelength, lambda 2. So although I cannot do simultaneous measurement of horizontal, vertical, and 45 degree, 135 degree polarizations, but I can do a measurement on a wavelength. And knowing the wavelength, I know it's a horizontally polarized or vertically polarized, or it's in 45, 135 basis. So when it is in 45, 135 basis, I can apply a wave plate and a polarizing beam splitter and do a measurement. And since I know which one is prepared in which basis, I can make a copy and send it to Bob, and Bob will never be able to detect me. So that's a nice attack which actually uses Mallows law. So what is the solution? Once again, you put a circulator or an isolator here. Now, if we, instead of use these 4 sources, if I use only one source, will that help me? The answer is no. Even in that case, people can do a kind of attack. This kind of attacks are called injection locking. So injection locking involves signing a weak but stabilized laser pulse, which will work like a master laser, into a powerful but unstable laser called slave. So if you want to use 4 this states, horizontal, vertical, 45 degree, 135 degree, starting from one state, so that laser will be strong, and that can be treated as a slave by injecting a master laser. That's called injection locking. So injection locking is one possibility to control your laser and perform hacking by injection locking. The interesting part is that measurement device independent QKD schemes are thought to be the most powerful achievable technology at the moment. So even a MDI QKD has been hacked by doing injection locking. So the time does not allow us to elaborate on this thing, and that's not my purpose also, but I just quickly show you the device which was used to hack MDI QKD schemes by injection locking, and interested audience may look at this paper of this year's where injection locking has been used for. So the message is that sometimes your source is questionable, sometimes your detector is questionable, sometimes the optical elements are questionable, and all of them may lead to problem. So the conclusion is that you should not trust your optical elements if you are doing experiments on quantum cryptography. Now, we have not talked about detector so far. I just quickly show a kind of attack. So this is called APD normally works in quantum cryptography experiments in Geiger mode. So when it receives a single photon, avalanche works and it clicks. So now, if a bright light is seen, the bright light can bring it back to linear mode, and in the linear mode, it will not be able to detect a single photon. So in that sense, it will become blind. So that's called detector blinding. So when the detector is blinded, then Eve sends Bob a tailored light pulse that produces a current slightly above I threshold. So I threshold is the amount of current required by the detector to click. So if it gives, now Bob has a scheme to randomly choose horizontal vertical polarizer and 45 degree 135 degree polarizer. So how it is done? That's done with the beam splitter. If the beam splitter, from the beam splitter, it goes in this side, you have horizontal vertical detector. If it goes in this side, you have 45 degree 135 degree. Now the light has intensity less than just above ITH. So if the right basis is chosen, then the entire light will go and click on the detector. But if the wrong basis is chosen, in which Eve has prepared and Bob has chosen a different basis, then it will have less than I threshold and no detector will click. So then Eve knows that which detector is going to be clicked. If it is successful, so then when in the same basis the measurement is performed, the result will be same. So Eve technically will have a copy of the key. So that's a interesting attack. Now we come to another example. There is something called double click attack. So normally when you have two detectors and if both of them click, we ignore them, because if we know that if one click this is 0, the other one click it is 1. But when both of them clicks, what it is? So if I want randomly put that if this detector clicks, then it is means even if both the detectors click, sometime I call it 0, sometime I call it 1, or I consider the double click events, then the quantum bit error rate increases like anything. It increases up to 50%, and that's why we ignore the double click event. Now, do we help Eve by ignoring the double click event? Yes, Eve may send a strong pulse, that is a pulse having large number of photons of a particular polarization, say H, in say considered in BB84 kind of setup. This falls on Bob's polarizing beam splitters and get transmitted if Bob measures in HB basis. But if Bob makes a measurement using diagonal basis, a double click event would occur because the intensity is very high. So there is with a high possibility both the detector will click, and that will be discarded. So then you see that only those cases will be successful when Eve's basis and Bob's basis are same. So as and when the receiver makes a measurement using the same basis as Eve's, a normal event is detected. So Alice and Bob ends up sharing the same information with Eve. So solution, don't be afraid of double click and consider them too. Now, for coherent states, you all know that coherent states are not orthogonal to each other. So since the coherent states are not orthogonal to each other, you can design a POVM or USD attack and try to identify which qubit is your decoy qubit and which one is your signal pulse, because they have everything else is same. But since one has a higher intensity, so if you consider one as a coherent state alpha, the other one is a coherent state beta, they are not the same. So you can, since Kate alpha and Kate beta are not orthogonal to each other, so you can in principle apply USD attack on them. Coming back to another component, that's called beam splitter. So beam splitter is used so very often. So in a beam splitter, how much it will reflect and how much it is transmitted, that depends on the wavelength. So the splitting ratio of the beam splitter is wavelength dependent. That is, the center wavelength has a coupling ratio of 50-50. So this is showing that how with wavelength the coupling ratio is changed, and the coupling ratio is defined here. So attack, Eve can control the measurement basis by sending Bob photons with different wavelengths. If measurement basis can be controlled, then the key can also be obtained by Eve. So if she chooses a wavelength in which the probability of reflection is very high, then the basis, or suppose horizontal vertical measurement device is kept here, then with a high chance this will be measured in this. And when it sends a wavelength in such that it will be in this path with a higher probability, then diagonal anti-diagonal basis will be used. So with changing the wavelength, if can technically control that the measurement will be performed in which basis. So how to get rid of that? So to get rid of that, you have to apply both broadband filter as well as narrowband filter to restrict it to a particular wavelength only. So these filters are to be kept in front of Bob's station. Now, the detectors which are prepared, the detectors are not exactly analogous to each other. So for example, if you have single photon detector SPD0 and SPD1, and this is one efficiency and this is one its efficiency. The efficiency is maximum at T. So if the pulse reaches at T, then both the detectors are working with equal efficiency. But now, if can take a strategy that if can delay in some cases and if can. So if a pulse comes in T1, then you see the detector probability are different. So with the high probability, this detector will be clicked. And if it comes in T2 with high probability, this detector will click. So this was the case with the Clavis T and sound by IDQ, ID Quantic, and even that was hacked by this kind of schemes. So part of the information, part of the key can be hacked by a time shifting attack. So if simply shifts the arrival of each pulse sent from Alice by employing a variable optical delay line. For example, if randomly shifts the pulse from Alice to arrive at T1 or T2 through a shorter path or a longer path of optical line, this shifting process can partially reveal the bit value of Bob. If the pulse arrives at T1 and Bob's announces receipt, the bit value is more likely to be 0, and within the bracket it is 1 because if it reaches at T2, because you are using two detectors, one is for SPD0, so when this detector is called, I note it as 0. When this detector is clicked, I call it 1. So you see the difference in the efficiency at this time. So by changing the time of arrival, if can control that which detector with higher probability will click. But since this is probabilistic, so the entire key will not go to if, but some part of it will be with a certain probability, if will get some information which is not desirable. So we are at the end. So final takeaway message is never trust your optical devices. Always characterize them as much as you can do. So with this, we end this presentation. Thank you.
Thank you, Professor Anirban Pathak. Now we will take some questions. So if anybody has question, they can just raise their hand. So they can just raise their hand. We will unmute them and they can directly ask questions. So please raise your hand if you have any questions or doubts.
Can I ask one question?
Yes, please.
So if you characterize the optical devices according to the bias or its different performance under different circumstances, you can do a privacy amplification assuming the attack, right?
Yes. But there are limits. Means still you know that means only thing is that will give you a feeling that means what can be the attack and what measures you have to take. But unless you do that, then you are in bigger trouble. So that must be always mean that was the last message, means you should do characterization as much as possible.
Right.
It does not really solve all the problems. If detectors are, detector efficiency mismatch is there, means you just know that what problem is there and what can be avoided, but you cannot actually achieve the unconditional security claimed by theoretical thing.
Okay, so is there any other questions? So if there is not any other question, let's thank the speaker once again. Thank you,
Sarika,
sir.
Anindya.
Okay. Anindya?
Anindya is raising their, Anindya and Ayana raising their hand.
Please
Hi,
unmute them.
Professor Pathak, thank you for a wonderful talk. I had one simple question actually. Can you elaborate on this thing about where you can estimate which is your decoy pulse from the pulse trend? Can you just elaborate on that? Because that is one advantage of using the decoy state, right? Like you can dynamically characterize your channel and then like all the signals exist and everything. So does that mean that even decoy state QKD is not secure as such?
So there are many attacks on successful attacks on decoy state QKD, and there are proposal of circumventing those also. So I just mentioned that one possibility. USD is a very common attack. People discuss as USD. The idea is that you design a POVM, and when you design a POVM, you can distinguish between non-orthogonal states. So in case of when you use weak coherent pulse or coherent laser pulses as your signal and decoy, then the lasers are characterized, means if you write it as Kate alpha or Kate beta, then this complex parameter alpha or beta characterize your laser. And then inner product of alpha beta is not zero. They are not orthogonal. So since they are non-orthogonal, then there is a possibility that you can apply USD attack on them also. So in context of USD, I mentioned that means the other things are fixed. I mean, the thing is that your decoy pulse and your normal pulse must be same in every facet. So every facet means their frequency, their wavelength, everything will be same. Only difference is in intensity. And now the intensity of the laser pulse is mod alpha square. So mod alpha square or mod beta square. So this alpha and beta are different. Since they are different, they are non-orthogonal. And since they are non-orthogonal, you can in principle apply USD attack. So there are ways to circumvent or reduce the effect, but USD attack is applicable to those situations where you are using a laser as your signal as well as decoy, because they are different in intensity. So their alpha and beta are different, and inner product of Kate alpha and Kate beta is not zero.
Okay. Thank you.
So there is one more question from Ayan. Yes, sir.
Ayan wants to ask. Okay, fine.
No, sir, please, you can ask.
Okay, thank you, Anirban. Nice talk. Just wanted to know, suppose you have two boxes, somebody has made like Alice and Bob terminals. Okay, it's closed. And then ask whether this communication which I am doing between Alice and Bob, the communication, quantum communication, a quantum key distribution, whether it is secure. So what strategy you are going to adopt to tell whether it is secure, or how you are going to certify whether it is really secure or it's not secure?
So probably you will be never able to tell that it is completely secure, because the new attacks are designed everywhere.
But how you are then going to certify?
Only thing is that you can certify that this is secure against this X attack or Y attack. You cannot say that means it's secure against all possible attacks, because the newer and newer attacks are coming from newer and newer invented device imperfections. So unless it's a completely DI-QKD, and you know that DI-QKD is difficult to implement, you need the detectors to be 100% efficient. So unless it is DI-QKD, means it's difficult to ensure that, because even MDI-QKD has been attacked by injection locking. So when MDI-QKD was introduced, it was considered that means it will be the best thing at the moment possible with the present technology. But injection locking is used to, so then we realize that means what kind of laser has to be used and what is not. So things are dynamic, means it's changing with time, and that possibility has to be kept open. And means as a cryptographer, I cannot wait for somebody else to hack my system and then introduce a countermeasure. Means we ourselves has to try to find out all the possibilities and weakness. And weaknesses are in device imperfection. So the best strategy to characterize the devices as much as possible, and then see that means how those weaknesses can be exploited.
So let's discuss. So according to you, there is no meaning of certifying if it is not device independent quantum key distribution. Certifying the security.
Of course, there is a certifying, means because in the classical world also we certify. So we certify against the known attack. We can certify against the known attack. We can certify against the limitations already characterized by us. That we, before somebody else do that, we do it. But it does not circumvent the possibility that tomorrow there will not be a new attack. So that's the case with the cryptography. Means tomorrow somebody can come out with a new attack. So that we cannot disclose. Means we cannot claim that means even for futuristic attack this is secure. Means we can check with the existing attack and tell that means all this is secure against now attack number 1, attack number 2, attack number 3 discussed in literature and so on. But we cannot say that means if tomorrow somebody will not be able to create, there is no such no-go theorem which will conclude that no future attack will be possible, because ideally you can do it, but it's a realistic thing, means that devices has imperfections and new imperfections can be found out.
Okay, thank you, Anirban. And you can go ahead.
Sir, I have a question. Can I ask?
Yes, please.
If Ayan is not asking. Sir, it's a very simple and naive question. Actually, several attacks that you had mentioned, for example, when you're talking about using the reflection from the optical components, sir, these kinds of attacks would require an access to the generation or reproduction facility, meaning the attacker will have to gain access of the lab where the generation process is happening. So should we not think about securing the physical lab? Is this not a more trivial thing? Should we not just... Okay.
The solution I have already mentioned, that you put means in the exit port of Alice or Bob, you put a circulator. So that will circulator or isolator, that will solve the problem. But these are easy to understand that this kind of attack, Trojan horse attack, has happened because these pulses are going inside. Means that from Alice to Bob there is a channel, there is a fiber or something, and then Eve has access to that channel, and Eve can put his own pulses. So just think of a intercept recent attack. So Eve can always put, so you cannot stop that no light is entering Alice's port. So when light is entering Alice's port, it can be the light coming from Bob, it can become light coming from Eve also. But to stop the backscatter light, it's fine that you put an isolator or circulator. But this kind of attack has really happened and in physical devices, which Marco Lupomarini has shown. So these are good examples. Like using the Malus law, this was very easy. But there are most of the attacks are sending light in Alice's port by a bright light, and then you can do detector blinding. We have not discussed all sorts of detector blinding attack, but this is a port, and then you can use different kind of filter, isolator. So the whole point is that means all these things are happening because of optical devices, and then to get rid of the attack, you apply another circuit. So for example, to get rid of this Trojan horse attack, you put a circulator. And the paper which I have not discussed for some reason means they claim it to be confidential. So Jakob Weinstein, who is editor of this QINP journal, so they have done an experiment in Princeton that people have put circulator to avoid this attack in BB84, and they looked at the backscattered light of the circulator and get some percentage of the key from the backscattered light from circulator itself. So when you introduce a component to stop attacking the other component, that component may also lead to some new attack.
Got it, sir. Thank you.
Hello, sir.
Yes.
I have one question. So it seems that, securing each and every attack, due to optical components, you are adding an extra, some optical component to counter that. So,
yes.
Is there any, in principle, we can make or invent one scheme in which, okay, we have given optical systems, we are not adding any extra amount of optical system, but in principle, either by changing the scheme of measurement or by using the property of quantumness of light, we can avert these kind of attacks due to devices. In principle, can we do that?
No, because think about a more simple question. Means why we consider information as physical, means because you cannot dissociate information from physical entities. So when I am speaking, means if you are in the same room, we are creating a vibrations and then vibrating your ear membrane and so on. So the same thing is here. Means you cannot dissociate information from physical entities. And when you have your information is connected to physical entities, implement any protocol, you will require devices, and devices will never be perfect. So the best possible thing is to design device-independent UKD, and which will be free from almost all possible, means all known attacks. But then the requirement is that your detectors are too efficient. And that detectors you cannot make. So detectors are imperfect. So if you have perfect detector, then you can do device independent QKD and you get rid of everything. But your devices are not, your detectors are not. At the moment, we don't have technology to achieve perfection. So then imperfection should be there, but with remaining within the imperfections, then we have to use this kind of things, that privacy amplifications, error corrections, and increase the confidence on the key. Means even if you, and then we know the hollow bound, that how much error we can tolerate. So those measures we can reach properly, provided we can characterize our optical components used and make them a realistic measurements. Most of the times theory goes without considering that. Means we can calculate that under this attack, this is the hollow bound. But then I have to check that whether my devices allow me to remain below that. And if it is below that, it's quite well secured. But as RP was asking, when this is well secure against the attack I have considered, not against any futuristic attack.
Thank you, sir.
Okay, so if there is no more questions, so let's thank the speaker once again. Thank you, Professor Anirban Pathak, for delivering the wonderful talk. Thank you.
Thank you all.
So the next we have a student talk by Natasha Awasthi. So she is from the Dehradun Institute of Technology and currently working on the open quantum system. So she will be delivering her talk titled as Universal Quantum Uncertainty Relation Between Non-Ergodicity and Loss of Information. So I invite Natasha to deliver her talk.
Hello, am I audible?
Yes, you are audible.
Okay, I'm sharing my screen.
Okay.
Just a minute. Yeah, screen is.
Yes, but it is not clear. So can you use full screen? Hello?
Yeah.
Please use full screen mode. It will be better if you use your laptop. Because your slides are not very clear.
I don't have laptop at the moment.
Can you use landscape mode? Hi, Natasha.
Yes.
Use landscape mode.
Still not visible properly?
It is visible, but it is not clear, and the slides are very small. So you can rotate your phone so that it can convert into the landscape mode. Please on the rotate mode.
Yeah. Now?
Now it is clear.
Okay. So a very good morning to all of you. First of all, it's a pleasure for me to being the part of this conference once again through this virtual mode, and I'm very thankful to this conference organized by PRL. Okay, so this is the title of my talk, Universal Quantum Uncertainty Relations between Non-ergodicity and Loss of Information. This is the collaborator whom I worked with them when I was doing PhD. This is the plan of the Introduction to Open Quantum System, Universal Quantum Uncertainty Relation between Information Loss and Non-ergodicity, and concluding remarks and applications. Okay, so suppose we have a system so that we can control, and we have the rest part of the system called an environment is. So our basic task is to define how does the small part of the whole quantum system behaves as the time passes. Here the system could be anything. It could be like a single atom or a black hole or a planet Earth. But what else the system is the whole universe. So if you can depict from this picture that your system is closed, and here the picture itself act as a closed quantum system. The system plus environment act as a closed quantum system. You can think in such a way, suppose you have a cup of water on the table, which is interacting with the external electromagnetic. So some of the particles may coming into the water, going out of the water. So when you think of the system, when you think of the cup of the water alone, then you can define in terms of the Schrodinger equation that you are doing in your graduate level. But when you go one step further, then a question allowed us to ask that what is the most general evolution of a quantum system is, and the answer to that question is O quantum. That is the subject of my research work. Okay, so in order to understand the concept of whenever the system interacts with the environment, there arises some kind of noise. In order to understand the concept of noise in a quantum system, let's start with the concept of what a classical noise is. Okay, so imagine in such a way, suppose you have a bit which is stored on a hard disk drive attached to an ordinary classical computer. The bit starts to be in the state 0 and 1. But after a long time, in presence of this magnetic field, stray magnetic field, the bit will become scrambled, and we can say that after a long time in hard disk, the bit may flip with the probability p, and with probability 1 minus p, the bit remain unchanged. So what is really going on is that the environment contains magnetic field which causes the bit to flip. To figure out the probability for the bit to flip, we need to understand two things. So first, we need a model of distribution of the magnetic field in the environment. And the second, we need a model for how magnetic field in the environment will interact with the bit on the disk. So for a single stage process, the output probabilities are rated to the input probabilities through that is Qi equals to Eij Pi, like this. So if we summarize this key feature into one, we can say that there is a linear relationship between input and output. There is something called a positivity requirement and a completeness feature. So each of these key features are important because each of these key features are an important analogy in the concept of classical noise. Okay, so this is basically quantum operation. This is a tool to understand the evolution of a quantum system in a wide variety of circumstances, including the stochastic changes to the quantum state, for example, the Markovian process. So from the picture, we can depict that the first method, that is whenever the system interacting with the environment, the system coupled to the environment, is based on the idea of studying the dynamics as a result of an interaction between the system and environment. Okay, this method is concrete and easy, and we can relate to our real world. But unfortunately, it suffers from the drawback of not being mathematically convenient. So On the second method, we move to second method of understanding the quantum operation, which is equivalent to first. This can be overcome by this mathematical inconvenience by providing a powerful mathematical representation for the quantum operation as operator sum representation. And this method is abstract and we can use for our calculation and theoretical work. And the third approach is the approach to the quantum operation that is equivalent to the two via set of some physically motivated axioms that we would expect a dynamical map in the quantum mechanics to satisfy. Okay, let's start with this quantum operation picture. Suppose you have a bit initialized in your ground state. You perform some arbitrary evolution and you read out your qubits at the calculation. So what you have to do, you have to perform some unitary matrix here and you read out the readings. Physically, we don't handle such a unitary matrix. So what we have to do in order to generate this unitary, we have to generate the Hamiltonian. And your Hamiltonian act on the Hilbert space of the system here. But in reality, what happened? In reality, this unitary evolution will something look like this. If you had done your being a theorist or an experimentalist, you will find that there is some error in the Hamiltonian represented by this equation. And this error in the Hamiltonian not only on the Hilbert space of the system, but on some part of the environment that will generate an entanglement between the system and environment. That give rise to the concept of noise, or we can say that whenever there is the interaction between the system and environment, that give rise to the concept of noise in terms of dissipation and decoherence. So this is a previous slide. This is the quantum dynamics. This is the unitary evolution, and we assume that the Hamiltonian act on the Hilbert space of the system. But in reality, your state is represented here in terms of density matrix, and the error in the Hamiltonian act on both the space of the system and environment. Okay. Operator sum representation is the second method of running the quantum operation, which overcomes the mathematical inconvenience, which was providing a powerful representation in terms of operator sum representation. So this is the unitary evolution, your state transform like that. In the initial state, we assumed that our state to be the direct product state of the initial state is to be the direct product state of both the system and environment, initially independent. We assume that the density matrix of the system lies on the Hilbert space of the system and environment lies on the Hilbert space of the environment. There we perform the reduced density matrix by tracing out the environment part, and here we assume that the density matrix of the environment can be represented in terms of this eigenbasis like this, where the sum of eigenvalues is equals to 1. This is the operator sum representation evaluating the trace of the environment, and we obtained this operator in terms of these are known as Krauss operator. So these Krauss operators, why they're important? Because they depends on the time argument and the initial environmental condition, providing the.
Sorry to interrupt you. You have 5 more minutes.
Yeah. Okay, so these are the properties that an operator sum representation holds. And these are the property of operator sum representation. As I told you in my second slide, this classical noise is an important analogy to the concept of quantum noise. Okay, let's come to my work. Okay, so this is my work. This is our work, quantum universal quantum uncertainty relations between non-ergodicity and loss of information. So that it's impossible to isolate from surroundings subject to information loss due to dissipation and decoherence. So in modeling open quantum system, the simpler approach is to consider the environment to be memoryless. So the system environment is, however, more over than non-Markovian, and there are possibility of information backflow into the system, which can be considered as a resource in a quantum theoretic task. So in our task, what we have done, on the other hand, we consider an important statistical mechanical attribute of a environment, which is later in thermals called the ergodicity of the system. So a stochastic process is considered to be ergodic if the statistical properties of the process can be realized for a long time average realization. So whenever the time average state becomes equals to the ensemble average state, this is known as ergodicity. Any shift from this ergodicity can be represented like this. In our work, what we have done, we have determined the loss of information in terms of the distinguishability measure for the quantum state that satisfies the following properties. And on the second round, we connect this loss of information with this term called the non-ergodicity through this distance measure. So using the symmetry property in the triangular inequality, we arrive at the uncertainty relation between the non-ergodicity and the average loss of information satisfying these two properties. We restricted ourselves to the case of a two-level qubit system, that is a qubit state, in which the trace distance located at the antipodes of the Bloch's pair, that is the pair of state, consists of pure and mutually orthogonal state. So therefore, in case of this trace distance, the uncertainty relation can be read like this. In the third section of our work, we consider a spin bath model. So we consider a specific non-Markovian model and study the status of the uncertainty relation. So the system here consists of a single qubit, you can depict from this figure, interacting with centrally with n non-interacting spin. So the total Hamiltonian is governed by this dynamics in terms of this Pauli matrices. We determine the dynamical map from the central spin. One can refer to my paper. And what we observe that here we plot the information loss with time, keeping some parameters like n fixed. And we see that from the plot that with increasing the number of bath spin, the loss of information also increases. Similarly, increasing temperature, the loss of information also increases. Again, we plot the histograms for the vertical axis, that is the sum of the information loss and non-ergodicity with the increasing the system bath interaction strength with the number of bath spin. Say we fixed for vertical value and temperature is a parameter, and we see that from the plot that with increasing strength, the sum of the information loss and non-ergodicity decreases and finally saturates. So we can also see that with increasing temperature, the sum decreases and come close to 1, which is the lower limit. So this is the uncertainty relation between the information loss and non-ergodicity. When the information loss increases, non-ergodicity decreases. So these are the concluding remarks that in open quantum dynamics, the information exchange between the system and bath plays an important role. We have shown that the ergodicity follow an uncertainty which valid for distances measured like we use trace distance in our work. We have considered the trace distance between the pair of quantum state for a particular two-level system, that is for a qubit state also. And interestingly, we found that the system bath interaction strength and the limit of infinite number of spin in the bath and the uncertainty relation between the information loss and non-ergodicity based on trace distance saturates exactly at the large interaction strength. Moreover, we find that the uncertainty relation in this model goes close in the saturation value and it fails to saturate. The application. Thank you.
Thank you, Natasha, for the nice talk. Now, if anybody has question, they can write on Q&A or chat, or they can raise their hand. I request host to unmute them so that they can directly interact with the speaker. So, if there is any questions. So I can't see any hand raise here. So if there is no more question or there is no questions, let's thank the speaker once again. Thank you, Natasha, for the talk.
Thank you.
Now we have last talk of the session by Dr. Chitrabhanu. He is currently a postdoctoral fellow at National University of Singapore Center for Quantum Technologies. He is leading the science team at Center for Quantum Technology, working on the Singapore UK satellite-based quantum communication project. He will be delivering his talk on enabling satellite-based quantum communication. I would like to invite Dr. Chitrabhanu to deliver his talk. Over to you.
Thanks, Sarika. I'll be sharing my screen.
Yes, I can see you. Yes, okay. I can see you. Yes.
Cool. Thank you. It's always a pleasure to be part of the scope, because I was one of the initial convener of this scope. So it's given me really pleasure to be presenting talk in front of you. So thanks to organizers. I'm Chitrabhanu Perumangatt. I'm a postdoc at Center for Quantum Technology, National University of Singapore. And my topic is enabling satellite-based quantum communication. Our group at CQT is mainly focused on satellite-based quantum communication, satellite and ground-based quantum communication. And this is my plan of talk. So I briefly want to explain why CubeSats. CubeSats are a set of satellites which are really small. That means it is made up of cubes of 10 by 10 by 10 centimeter in size. So why CubeSat are useful for quantum communication? And I'll be just mentioning earlier Pathfinder missions from CQT. Later, I will be mainly explaining the latest results that we have demonstrated entanglement in space in a satellite called Spooky 1. This is our own satellite. If you see the previous thing, this is Spooky actually taken at space. The image is taken at space. And if time permits, I will be discussing our future missions as well. So quickly, why satellite for quantum communication? Is basically because we don't have a good candidate for quantum repeaters. So since the quantum communication is done by photons, obviously fiber is a natural choice because we have deployed fiber all over the world. But the problem is that there is big loss with distance for the fibers. This is considering the best and worst case or reasonable case scenario for fiber. The losses at distance of 2,000 kilometers are huge, and at that point you cannot revive any signal. On the other hand, the satellite to ground, the distance versus loss does not scale like this, and you can even get some signal out even with minus 50 dB for 2,000 kilometers. So for global quantum communication, satellite is a good choice. And thanks for Anirban sir to explain this quantum communication with satellite. That was a good introduction, so I don't have to introduce much. But satellites can be considered as a trusted node because it's difficult to assume that a satellite can be hacked locally. This is just an assumption. And moreover, you can have constellations of satellite. That means you can have satellite to satellite, and many satellites talking to each other like Starlink, and have a global quantum network. When I talk about satellite quantum communication, there are many possible scenarios: satellite to ground, ground to satellite, between two ground stations, and satellite to satellite. So you can follow this paper discussing all of these trends. Okay, so when we talk about satellite, obviously first biggest experiment happened was Chinese Mishra satellite. What they have done, they have a really big satellite, and they have an entangled photon source, they have a weak coherent pulse source, and they have two telescopes to downlink their quantum states. So they have done entanglement distribution between two ground stations, quantum teleportation between ground and satellite, also satellite to ground QKD using BB84 and entanglement-based QKD. So what is new in our case, we are not going for this kind of big satellites. So this is Mishra and this is our satellite. And don't get me wrong, our satellite cannot do the same things what Mishra is doing, but we believe that we can use this kind of small satellites to do quantum communication. So this was the first step towards enabling such quantum communication. So this is a nano satellite or CubeSats. This is 3U. That means in this direction it's 30 centimeter, and this direction is only 10 centimeters. Okay, a quick history. This was our much before Mishra. We have started these experiments initially with balloons in the atmosphere, and then we have launched our first payload in a small CubeSat. But this while launching, the rocket was exploded. But we got our correlated source. These all were not entangled source; it was correlated source. This correlated source were we could get this correlated source, and it was working. So that gave us some confidence. And in 2016, we sent this correlated source in another satellite. These satellites were not made by us. This was made by other collaborations. But we had our payload there. So this was a previous case, and now this is the Spooky satellite which I was talking about. So Spooky is dedicated satellite for a demonstration of entanglement in space. So this was built at CQT, and this is the experiment, quantum experiments. We have the optical payload is this small, it is 20 centimeter, and we have solar panels, avionics stack, antennas for the communication and all. So this was launched to International Space Station on 17th April of 2019. After 2 months, it was deployed from International Space Station, and ever since they are generating entangled photon source, and we are talking to it yet still. So this CubeSat has a mass of only 2.6 kilograms, and the maximum power it can consume is only 2.5 watts. Okay, I told you this is an entangled photon source. So since we don't have much power available, we don't want to thermally control the crystal. So though we choose angle tuning of spontaneous parametric down conversion. And this is a newer design for entangled photon source. You can see this paper for more details. There are two BBO crystals. These BBO crystals are type 1. The spontaneous parameter down conversion at BBO crystal is a type 1 SPDC. And so vertically polarized pump beam convert to two horizontal polarized SPDC photons. And a half-wave plate will flip the polarization of the SPDC photons, but not the pump. So the pump again generates the horizontal polarization, and this HH and BV overlaps, and there is a crystal which removes any kind of temporal phase, and you get this state, this bell-like state. So since there is a good overlap, even if there is a small tilt in the PBO angle, the state remains same. So we want to make sure that, so we measure the DA visibility, which is an indication of how good is your entangled state is over the BBO angle detuning. And you can see you have almost constant visibility over 100 microns. So even if in the launch, if it is tilted for 50 micron, it's still within the required visibility. Okay, the optical design is like this. So this is the whole thing. So when we do in lab, we use a optical table, but we don't have the optical table in the satellite. So we make it in a single bench, and this is a laser diode, and we move the beam using Russell prisms, and these are the BBOs. It's sitting on a flexure stage which can change the angle in one direction, and you remove the pump using a dichroic mirror, and this is a temporal compensation and split signal and idler using wavelength. So this is non-degenerate, that's why you can split by wavelength, and we measure the polarization of each photons using a liquid crystal polarization rotators. So we are generating and measuring the entanglement in Spooky itself. So we are not downlinking, sending any photon to ground yet. So in Spooky, the whole idea was to generate and detect entanglement with good fidelity. We didn't have any collection optics, so it was just bare APD, and there was no active alignment techniques. It's because of the space and power constraints. Okay, this was the deployment. So thanks to one astronaut in International Space Station, they have took a photo of this, and you can see the huge panels of ISS. And this is our Spooky ejected from the deployer. Okay, Spooky in orbit. So once it is deployed, next day we were able to communicate with this with Spooky. And generally, this is following an International Space Station orbit. So it has a 90-minute day. That means after 90 minutes, it comes back. And in a day, we generally have 2 or 3 good passes. Good passes means this passes through our ground station. And one pass is only 10 minutes. That means in 10 minutes, you have to upload the commands, download the data, and you have to make sure that the satellite is okay now. We had 2 ground stations, one at NUS and one at Switzerland, and we were using both of these ground stations. And the satellites was going through different illumination cycles. So in normal cases, the satellites, this is not the satellite temperature, this is the temperature of the payload. The payload temperature varies like this. So this is the time where it is in the Earth's shadow. But this is not a constant. When over a period of time, this gets shorter and shorter. It's called high beta angle. The beta is the angle between the sun's vector towards Earth and the satellite orbiting plane. So when it is 90 degrees, it's always, the satellite always sees the sun. That's why it always sees the temperature increases a lot. So we cannot operate at this point. We want to operate at this point. Even in that point, the problem is that it's really cold. It's only 10 degrees, and our lasers are not meant to operate at 10 degrees. So what we do is that we heat the whole payload. It's made of titanium, and we had only one sheet heater to heat the whole payload. So while heating, we cannot run an experiment because this was our maximum power. So we heat this over 1 or 2 cycles, and we reach the temperature what we want, and we run the experiment. How do we run the experiment? Before sending it to space, we have done a lookup table. This is laser temperature, and this is laser current. For different laser temperature, what is the DA visibility for different laser currents? It's because DA visibility corresponds to the entanglement quality, which is correspond to the relative phase in between HH and VV, and this phase is only a function of the laser wavelength. So if the laser wavelength changes, the phase changes. So we want to have this lookup table. So if you find that this is the temperature, we use this current and get the visibility there. Okay, so This is the result. Yes, entanglement prevails, and this is on the ground, and this is on the satellite. And the curves you see is generally called as bell curves. It's nothing but projecting one photon in horizontal, diagonal, vertical, and anti-diagonal polarization states, and sweeping the polarization of the other photon. And the visibility of these curves tells you how good is your entanglement. So you can see that the visibility almost says same. And from these curves, you can extract the Bell CHS inequality. So you can see that it's always violating the classical limit. So these 3 red points are the points where we have done this experiment after the high beta angle. That means after the high beta angle, the alignment still stays. So we still violate the Bell inequality with high margin. If you are interested, you can read this paper recently published in Optica. Okay, so this was about Spooky, and I think I have some more time. Okay, what is next? So Spooky, as I said, was just a demonstration.
You have 5 minutes left.
On the communication, it generates the entanglement in space, and we know that we have the capability, and now we want to take this into the next level. So the main thing is that you want to make this whole source and your detection system into a shoebox size, even smaller than the shoebox. It's a 2U volume. You want to make sure that everything is contained. That we are pretty sure that we can do that. Now we want to use that for quantum communication. So after that, we have worked on different sources. So these are one of our publication is that entanglement photons from position correlation. This is not only a development or engineering thing, it's interesting for science as well. So we convert the position correlation to polarization entanglement, and that also gives you a bright entangled source. And the later one is the broadband pump entangled photon source. So it can be broadband or it can be narrowband, but the entangled photon source is really bright. It has more than 1 million pairs per second per milliwatt. And it is independent of laser modes. That means even if the laser mode changes, the visibility of the state stays. So we have all of our ingredients. We want to use this in a satellite to ground quantum link. Okay, so this is what we are going to do next. And we are almost under the process of building these things. We will have a satellite, and in the satellite, we will have a source. And one of the photon, that means suppose idler photons, is detected using this partial tomographic setup. And other photon is sent to ground station. And again, the same setup is there in the ground station as well. So the good thing is that if you have this kind of setup, you can extract keys from the coincidence between these clicks on these detectors. So that's the goal. So this is the future. We have a collaboration with RAL Space in UK. So they will be providing the satellite.
Sorry to interrupt you. Two more minutes left.
Yeah, I'm almost finished. So the project is that they will be providing satellite platform, and we will be providing the quantum payload. And in this case, we will have a ground station at CQT and a ground station at RAL Space, and the satellite can exchange the keys here and here. As Anirban said, you can do an XOR operation, and we can have a secret key shared between RAL Space and CQT. I think I have motivated you for satellite-based quantum communication, especially using CubeSats. And since CubeSat is relatively cheaper, and you can do it in much lower timeline. So we are currently undergoing the process of building this satellite and the ground station. Thank you for listening. If you have any questions, you can ask. And this is the satellite before sending it for the launch. And this is our team. If you are interested to know much more about our group and our group activities, please follow this link. Also, if you are interested further discussions, I'm always available. You can email me. Thank you.
Thank you, Dr. Chitrabhanu, for the wonderful talk. So if anybody has question, they can write in the Q&A session or chat, or they can simply raise their hand. So I have first question by Professor Anirban Pathak. So he's asking, is temperature change happens due to the sunlight angle 2-3 times it passes over the NUS and 2-3 times over Switzerland, or total 2-3 times each of the 10 minutes? They have written their question in the chat section.
No, actually, I have two questions. One is that the temperature change is because of the angle with the sunlight, or it's for some other reason?
So generally, the satellite sees sunlight and shadow, right? It goes to the shadow and it sees the sunlight. So and it's heated up. It's as simple as that. But the variation I mentioned is that you have a satellite plane and the vector towards from sun to earth, and this is changing depending upon the season. So at some point, the satellite plane is actually perpendicular. So satellite always sees the temperature, sees the sunlight. So only source of temperature is sunlight. So it heats up, and we will not do the experiments during the time.
So you don't put some thermal controller or something externally controlled?
We have only a heater, and we have a thermal isolation. It's a partial thermal isolation. You cannot isolate for radiation. So. Yeah.
And the second question was that you told that means it comes 2-3 times for 10 minutes each for all the operations. So this is 2-3 times above NUS or 2-3 times with considering both the stations? So
it depends upon the days. Some days you will have a good path. That means the elevation has to be good to have a good radio communication. So generally you used to have 2 or 3 good passes in NUS and Switzerland. If you miss in NUS, we can catch the satellite in Switzerland.
Okay, so there is one question from Nigel. So he's asking, it appears that there is a periodic variation in DA visibility with temperature for a fixed current and vice versa. How do you explain this kind of variation in the visibility?
DA visibility, if you fix current and temperature, it's constant. But this is related to the laser we are using, right? So we are using a laser diode. We cannot use a laser system. It's a small laser diode. So this laser diode is volume holographic grating laser. So there's a hologram, and it sends back the signal. So because of that, when you change the temperature, the hologram, the period of the hologram changes, and it changes the wavelength of the laser. So because of that, you will introduce the phase to the HH and VV state. So that's how the variation visibility is changing.
There is one more question from RP Singh. So he's asking.
Yeah, I will ask. Okay. Sarika, I will ask.
Okay.
Chitra.
Yeah.
What size of telescope you are planning for ground station? And another thing, whether you would be using a laser ranging system or just telescope will be good enough. So size of the telescope and whether you will be using laser ranging system, and what will be the height of this satellite you are planning? 400 kilometers, 500 or 700?
Yes, this will be around 400 to 500 kilometers, and this will be in a low Earth orbit. And the size of the ground station is either 60 or 70 centimeters big. Ground station will be used. And regarding the laser, yes, we will have a uplink and downlink beacon for pointing and tracking.
So in satellite also you're planning to have some small telescope for guiding the signal, or just ground station you are having, you will be having this?
No, of course you should have a satellite, a telescope at the satellite. The telescope at the satellite cannot be big, so it will be a small aperture telescope, because
small aperture. How small it is, or how big
it may be a 8 centimeter telescope.
Just 8 centimeter is good enough for guiding.
So if you use a 8 centimeter telescope, the spot size of a Gaussian beam at the ground will be roughly 5 meter or so. That is sufficient enough to extract some the keys or get the coincidence.
And another thing, like, are you having some temperature control of your laser, or you are not having any temperature control for your diode laser you are using for down conversion?
In Spooky, we didn't have any temperature controls at all. So we all we had was only one sheet heater which heats up the whole payload. We didn't have any temperature control for the laser or the of even
generally
the
when you are heating, Chitra, what temperature you maintain? In shadow region you will have to heat. So what temperature do you maintain?
We used to heat it almost two cycles. So it's not only shadow region. We used to heat it to reach a reasonable temperature, because we saw that the
what
temperature.
is the reasonable temperature? Like 22 degree, 23, 25. What is the
40,
reasonable temperature?
So above around 17 to 25 is the reasonable temperature, because we have characterized our laser for that.
Okay. Okay. Thank you.
Okay. One more question: how one of the entangled photons will travel to satellite to ground station? So this will be using a telescope. So there is a telescope in the satellite, and the one of the photons will be sent to that telescope, and it will be downlinked to the ground station, to the ground using free space optical link.
Is there any other questions?
Laser diode is continuous. We are using a continuous laser diode. Yeah.
So if anybody has question, just raise your hand. Yes. Professor R.P. Singh is raising hand. I request host to unmute.
Chitra, what is the bin size, time bin size you are selecting for this checking entanglement?
Coming in, sir?
Time bin size. What is the time
Okay.
bin size you are selecting?
The coincidence window.
Coincidence window, yeah.
Yeah, the coincidence window is roughly 4 nanoseconds.
2 nanoseconds.
4 nanoseconds.
So it's 4 nanoseconds or 2?
So 4 nanoseconds. 4 nanoseconds.
4 nanoseconds. So
Yeah.
this is homemade electronics, or you use some like commercial TDC, time to digital converter?
No, this is a homemade electronics, and the coincidence is using an AND gate. So you have a signal from one APD and signal from another APD. You do an AND gate and you get a coincidence. So this is not enough in the next version. If you want to do full QKD, you need to have a good time to digital converter, and we have developed some of the time to digital converter. Some collaborators within the CGT will be using that. So in case of communication, quantum communication, we need to narrow down this much more to 1 nanosecond.
So 1 nanosecond you are planning to have when you are going to have this QKD mission, next mission, instead of 4 nanoseconds.
Yeah, 4 nanosecond was just, it's basically you have 2 pulses from the APD, right? So if you do an AND gate between these pulses, twice the pulse width will be your coincidence window. So the pulse, we were able to go up to 2 nanoseconds. So you have the coincidence window of 4 nanoseconds. Around 0.4 nanoseconds.
Okay, fine. Thank you.
Thank you, Dr. Chitrabhanu, for the wonderful talk. Now, next we have poster session. So I request everybody to check the poster session schedule from Scope 2020 website and join the Google Meet link by using poster schedule. And with this talk, we conclude today's session. I want to thank all our speakers for their time and participation. I thank everyone in the audience for being present here and asking wonderful questions. So after the poster session, we have a lunch break. Then the next session will start. And the chairperson of the next session is Satyajit Patel. So thank you, everybody, and have a good day.
Thank you.
Please be there for the poster session in the Google Meet.
This meeting is being recorded.
Hello. Is there anybody online? Hello. Hello. Is there anybody online?
Yes, sir.
Yeah, am I audible?
Yes.
Okay. Okay, great. So, but my video is not on, not yet on.
It will start at
Okay.
2:05.
Okay.
At a given time. Yeah.
Okay. Some permission from administration is required, no? From yours.
Yes.
Yeah. So I have to just share the screen, no? The full screen mode. That will be sufficient.
Yes.
Okay. So you are Shotto, you are the chair of this session, no?
Yes, sir.
Okay. So how will we would take the questions at the end of the my talk?
Yes, question will be there in Q&A session section right there.
Yeah. Okay. So what I will do means at the mid of my talk, I will stop for 1 or 2 minutes. If there is some question, I'll answer and then I will go back.
Yeah, sure.
Will it be fine?
Yeah. Actually, this is the protocol.
Okay, sure, good.
Yeah.
And can you just remind me just 5 minutes before my time is over?
Sure, sir.
Okay.
Hello, everybody. I hope you had a lunch. We will begin the next session within 5 minutes.
Shutta, can I just check for once the share screen things?
Sure, sir.
Host disabled participant screen sharing. It is yet, still it is disabled. Okay, now it's up.
Yeah.
And then
it is visible.
Full screen. It's visible, no?
Yeah.
Okay.
Perfect.
Okay, great.
Hello, everybody. Once I am again announcing that we will start our next session within 2 minutes. Okay. Am I audible?
Yeah.
Okay. So I'm starting the session. Hello and welcome to the fifth session of the Virtual Scope 2020 conference. I'm your session chair, Satyajit Patil, and this is the second part of quantum optics and quantum information. A few reminders before we start this session. The presenter's pre-recorded presentation will be played, or they can share their live screen using the share screen button at the bottom right of the window. I request all presenters to strictly adhere to the clock. The audience can use the Q&A widget to type your questions. of which will be answered at the end of the session. You can use the chat widget to communicate with other attendees and to comment on the presentation. So on those notes, let's start this session on quantum optics and quantum information. As the invited talk in this session, we have Dr. Manik Banik, who is currently an assistant professor at Indian Institute of Science, Education and Research, Thiruvananthapuram. He did his PhD in Quantum Foundation from the Indian Statistical Institute, Kolkata. His current areas of research are quantum information theory, quantum foundations, quantum thermodynamics, and causality in a quantum world. He will be delivering his talk on quantum advantage in shared randomness processing. With this, I invite Dr. Manik to deliver his presentation.
Yeah. Thank you, Shobita, for your kind introduction. Just
yes.
1 second. Let me share my screen. Yeah, is it visible?
Yes, sir.
Okay, so title of my today's talk is Quantum Advantage in Shared Randomness Processing. So, let's give some brief motivation. One of the main motives in quantum information theory is to find out informational task where quantum rules gives us advantage over the corresponding classical resources. But it is very hard in principle to find this advantage, and even it is harder to prove that this is really advantageous over the classical resource. For instance, if we look into the quantum computing algorithm, such as Shor algorithm, the advantage, quantum advantage is they are under the assumption that no classical algorithm can run this such algorithm first. So all this quantum this kind of advantage is not provable. It is believed under some assumption. But here today I will discuss one such quantum advantage. It is provable, and this advantage in shared randomness processing. So this is this is our recent work. It's a collaborative work. You can find this work in this archive. So they are my collaborator, Tomal and me. They are from ISI, Indian Statistical Institute. They are doing their PhD. This is Shumit. Shumit is now, he did his master's thesis just recently with me. Now he got the PhD position with Haradoki group, with Haradoki. Amit is doing his postdoc at Esenbos Center, and Shom Shankar is doing his PhD at Hong Kong University with Guilio Chirivella. Okay, so unfortunately, we are going through a very difficult time, this COVID pandemic. I hope all are in good health and sound spirit. Now, keeping this pandemic in mind, let us consider the following scenario. So let us two party, Alice and Bob, and they don't know each other. They are to buy. They want to buy some stuff. And there are two grocery shops, grocery shop 1 and grocery shop 2. So they want to buy some stuff from this grocery store. Now it may happen that both Alice and Bob end up in same grocery shop. If this happens, then this doesn't satisfy our physical distancing norm. In the same way, if both end up in grocery shop 1, this also does not satisfy the physical distancing norm. But if this is the case, that Alice ends up in grocery shop 2 and Bob ends up in grocery shop 1, or Alice in grocery shop 1 and Bob is grocery shop 2, then physical distancing norm is maintained. But now our question is how to maintain this physical distancing norm, because Alice and Bob doesn't know each other. So what we can do, we can think, okay, there is some referee, and this referee may be some local government who try to assist Alice and Bob where to go, in which grocery shop they have to go, maintaining this social distancing norm. Okay, and this assistant we can consider we can think it as some, let's say, some coin. And what is the rule? Rule is that, okay, if head is given to one of the party, Alice or Bob, he or she has to go into grocery shop 1, and if tail is given, then he or she has to go to grocery shop 2. Now, this government or this referee gives Alice and Bob an anticorrelated coin. What is meant by anticorrelated coin? Means if head is given to Alice, then tail is given to Bob, or if tail is given to Alice, then head is given to Bob. And accordingly, they follow this rule. And if they follow this rule, then the social distancing norm is maintained or satisfied. And moreover, in a long run, both these shop has equal business. Why equal business? In a long run, we will find that Alice appears in shop 1 as many times as Bob appears in shop 1, and vice versa. Means Alice appears in grocery shop 2 as many times Bob appears in grocery shop 2. So this is we call non-monopolization. What is meant by non-monopolization? Means both the grocery shop has equal business. So this is crucial for our purpose. Okay. So what is now this anticorrelated coin? So anticorrelated coin means coin state for each party is random. However, the state of two coins are anticorrelated. Means if one is head, another is tail. So there is some correlation. Correlation is in opposite order. That's why we call it anticorrelated coin. So we can consider them as shared randomness. So there are some shared correlation, but locally they are random. That's why it is called shared randomness. And in this particular scenario, in this buying this stuff from grocery shop, maintaining social distancing, we see that this shared randomness is actually a resource. Why is resource? Because it helps to maintain certain social distancing norm along with this non-monopolization condition. Now in quantum information theory, not only quantum information theory, much before that, even in classical information theory, people have identified this shared randomness as resource. For instance, Bennett, Brashad, they have shown that this shared randomness is very important in privacy amplification. And then Lazio Babai, he have actually shown that in simultaneous message passing model, shared randomness is a very useful resource. It is a particular kind of communication model. It is shared randomness are also important in key generation, cryptographic key, secure key generation, simulating Bell non-local correlation, very peculiar kind of correlation, this Bell non-local correlation. Then also in finding out the correlated equilibrium in Bayesian game. So there are lots of application of this shared randomness. Okay. Now let us consider this kind of scenario. What is the scenario? That okay, instead of 2 grocery shop, there are 3 shop actually. And Alice and Bob are given this correlated coin. Now the question is they have to maintain these 2 requirements. First of all, they have to maintain this social distancing norm, and second of all, the business should be non-monopolized. So the question is, will it be possible to maintain the social distancing norm as well as the non-monopolization condition? So now let's see, we can consider this kind of strategy. Okay, if head comes to either Alice or Bob, he or she go to grocery shop 1. Or if tail comes, then he or she goes to grocery shop 2 or 3 randomly. They decide it randomly. That means if some anticorrelated state is given, half HT plus TH, then if H comes, this first party go to 1 shop, and if T comes, it goes to 2 or 3 shops with equal probability. So finally, this will be their means Alice will go either shop 1 and Bob will at that time go to shop 2. Alice will go to either shop 1 and Bob will at that time go to shop 3, and so on. So these 4 possibilities are there. So now you see, in none of the case, Alice and Bob ends up in same grocery shop. So social distancing norm is satisfied. But non-monopolization condition is not satisfied. Why? Because you see, this occurrence of grocery shop 1 here is 4 times. Where grocery shop 2 and 3, they occurs only 2 times. So grocery shop 1, they have more business. So it is a monopoly. Grocery shop 1 has a monopoly. But we don't want this. We want a non-monopolization condition. So with this kind of classical coin, we find that, okay, social distancing norm can be satisfied, though social distancing norm can be satisfied in 3-shop scenario, but non-monopolization condition cannot be satisfied. That's why our question is, can quantum break this monopoly? This is our main target to discuss. And we have shown that yes, it is possible. And to answer this question, we actually formulate a resource theory of shared randomness. What is meant by resource theory of shared randomness? So any generic framework of a resource theory actually constitute these 3 elements. First, we have to identify this non-resource or free state or useless state. Then the free operation, those are not costly operation, and then resource conversion condition. And for the last half decade, people have find in quantum information theory that resource theory is a very useful language to quantify the resources, both in classical as well as quantum. For instance, if we look into our old thermodynamics, that can be cast as a resource theory. This thermal state means state in the bath are the free state, thermal operation are the free operation, and there are some particular criteria in quantum scenario, thermomeasurization criteria, or in classical thermodynamics, this is the second law of thermodynamics, means entropic criteria that governs what transformation is allowed or not. And in this resource theory, what are the resource state, resourceful state, a thermal state, states which are not thermal are the resourceful state. Means if such a state is there, it's available, then we can actually treat it as resource. Why? Because using this thermal state and using this athermal state, from this athermal state, we can actually extract work that we can use for some task, or we can run some engine using this. Okay. So now our aim is to construct a resource theory of shared randomness. So first of all, it should be random and there should be some correlation. So if we consider these two parties, Alice has some random variable X, Bob has some random variable Y, then this joint probability distribution on this random variable X and Y we will call it free state if they are just product form. There is no correlation. This X and Y are independent. These are our free resources. What are the free operation? So Alice doing something on her random variable X, some post-processing operation with her random variable X, and Bob doing some post-processing operation on his random variable Y, that will be considered as free operation. Communication is not allowed, because if communication, due to with the help of communication from a resource free state, they can actually obtain a resourceful state. So communication is not a free operation in these scenarios. It is only local operation. For instance, in classical scenarios, such local operation we can characterize by local stochastic matrices. What is a stochastic matrix? It's nothing but a most general mathematical description of a mapping from a probability vector to another probability vector. And in quantum scenario, what are our free operation? Our free operation are local CP operation. It's technical term, completely positive operations. Means what Alice can do with her system. Alice can do some measurement, or she can apply some unitary rotation or unitary operation on her part. Any arbitrary measurement locally and any unitary operation, but no communication is allowed. This is important. So this is our free operation. And then the resource monotone. What is meant by resource monotone? Means what gives the what determines the resource conversion under this free operation. So it turns out that this particular quantity, it is entropic quantity, it is called mutual information. Mutual information turns out to be a resource monotone. But it may happen that there may be not a single monotone, there are lots of many monotones. Like in thermodynamics, thermomeasurization condition is lots of monotone is there. Okay. So now we will see that this resource monotone means mutual information is a faithful resource quantifier. Why it's called faithful? When it is called faithful, if it is non-zero for every resource state and zero for all free state, then it is called faithful quantifier, resource quantifier. But however, we will see that it cannot sufficiently characterize resource conversion. Okay, with this, keeping this in mind, this generic framework in mind, let us consider a simple example. It is a two-coin state space. Let's Alice variable X is only two valued, H and T, and same as Bob's variable Y. So what is the generic state? So a generic state is then this kind of state. H on Alice side, H on Bob side, H on Alice side, tail on Bob side, and some probability distribution. So it is a probability distribution, P of HH, P of HT, P of TT, TH, and P of TT. And we can represent this C2 in this canonical form, where it is a vector, V is a vector in R3, all are positive number and sum of them should be less equal to 1. This is the condition. Okay, so now if we geometrically look into that, then the state space will look like this kind of object, three-dimensional object. Now what is this point? This point is when x is equal to 1 and all yz, all other quantity are 0, yz are 0. So this is this corresponding state, CHH. Similarly, CTT will be our XYZ, all the three quantities are 0. So it will then this point, CTT. Okay, now look into that. This HH, TT, TH, HT, all of them are free state because they can be written as product probability on H 1 times probability on H on both side 1. So it is a factorized form, product form. So all of them are free state. Now look into this line, particular line, CHH and CHT. Now in this case, you see from Alice part we can take this CH common, and then there is a probability distribution on H and T on both sides. Again, it is in product form. So these are also free state. Point lying on this line are free state. But if you consider this red line, CHT and CTT, they are convex mixture, then you cannot write it as product form. So it is a resourceful state. This line, point lying on this red line or point lying on this green line are the product resourceful state. Okay, so this is the we call it, let's say, alpha correlated line or alpha anti-correlated line. Now let's say consider this particular state, C delta. C delta is 1/3, 0, 1/3, 1/3, T. Look into this particular representation. So where this state lies in this picture, this state lies in this particular surface. In this particular surface, y component will be 0. Y component will be 0. It will be lie on the XZ plane and at the middle of this, because all of these are 1/3. Okay. Now we can see if somebody asks, okay, if we are given this particular point, so C half 2, what is C alpha? C alpha is equal to half HH plus 1 minus alpha TT. Now what is C half 2? C half 2 will be half HH plus 1 half TT. So whether from C alpha 2 we can obtain C delta 2 state. We can check this has more mutual information than this particular state. And it is possible to go from this state to this state by using free operation. And one of the two possible free operation are written here, this local stochastics. But if we ask the converse question, can we obtain C half from this C delta 2? Obviously it cannot be, because our targeted state has the C. This is the C alpha 2 is the targeted state. It has more mutual information than the initial state. So under free operation, we cannot achieve here. We cannot go there. Okay, good. But we ask this particular question. What is this question? The question is, if we start from this C half state and we want to reach into a C alpha state. C half state is this one, let's say, particularly this middle point. From this point, we want to go another point in this line which is not at the middle. Alpha is some other value than half. Can we go there under free operation? Mutual information immediately doesn't put any constraint because mutual information of this final state is less than the initial state. So it seems that okay, we can go there. But if you check it, it is not possible. There is no such free operation, means locally stochastic matrix is there, operation is there, by which you can obtain this non-equal probability alpha correlated state from an equal probability alpha correlated state. It is not possible. That establishes that mutual information is not a sufficient resource quantifier. So these are the state on this yellow line, green line, and the red line. Okay. So this is the theorem what I have just explained. Now, what is in our quantum scenario? This quantum coin state we can consider. What is our classical coin state? Classical coin state is a two-dimensional state, a head and tail. A quantum system we can consider any two-dimensional system like spin-half system or polarized polarized light, and we consider bipartite spin-half system, two spin-half system. Here also you see two coin we consider. One is with Alice, another is with Bob. Now we consider one quantum system with Alice and one quantam system is with Bob, and both of their dimension is 2. Means they are two-dimensional quantum system. So this is their corresponding Hilbert space. And what is their free operation? Free operation we have already defined in quantum scenario. Whatever operation Alice can do locally on her part and Bob can do locally on his part without any communication. So now let us define this by this symbol, sigma c symbol, sigma c2 to d be the subset of CD coin, d-dimensional coin that can be freely simulable from a two-dimensional classical coin. Like from a two-dimensional classical coin, we cannot achieve a completely correlated six-dimensional classical coin which is nothing but a dice. It is not possible because the latter one is more mutual information. But some state can be achieved. Let us denote that subset by sigma c 2 to d. Similarly, we define the subset as sigma q 2 to d. So, d-dimensional classical coin state that can be locally simulated or freely simulated for a two-dimensional quantum coin state. So, this is sigma q2. Now, what is our main contribution of our paper? We actually proved that sigma c is a proper subset of sigma q. So the state that can be simulated in using classical two-dimensional coil is a strict subset of quantum. So quantum has some advantage for any d greater than 2. So in the next part of my talk, I will try to explain this theorem with some example. So in the meantime, I think I can pause for a few seconds. If there is some question, I can take it. If there is any question, you can please ask.
Sir, we will take questions at the end of this talk.
Okay, it's fine. Okay.
Yeah, continue.
Okay, so now in rest of my talk, I will try to actually understand this theorem. This theorem, how I present it, it looks very mathematical, but I will try to present the same theorem in a more operational way. Okay, so quantum advantage, that is our aim to discuss. Now, in a d-dimensional case, each coin are d-phased coin. Now, in two-dimensional means it is head and tail. D-dimensional case, it is d different phases are there. So, f can take values 1 to d. Now, we denote a alpha anti-correlated state, means it's denoted by C, not alpha D. It is defined as like that. That this correlated term, all the correlated term, if Alice getting phase F and Bob getting phase F, their probability is always 0. But all the other term, Alice getting some phase and Bob getting another different phase F prime, always non-zero. This is a alpha not correlated state. And alpha not correlated equal state is when all the anti-correlated terms are equal. That is called alpha anti-correlated, alpha not alpha, means d-dimensional not alpha state with equal probability. Okay. Now, in our 3-shot case, if we have this particular kind of shared randomness, a 3-dimensional shared randomness like this, then we achieve our scenario. What is the scenario? The scenario is, you see, none of this party, Alice and Bob, will end up in same shop, and all of the shop has same occurrence probably. So both the social distancing norm as well as non-monopolization condition is satisfied if such a coin is available. Similarly, if there are 4 shops, this social distancing norm as well as non-monopolization condition will be satisfied if Alice and Bob share such a 4-dimensional state, this particular state. If this is available, then they can satisfy both this requirement, social distancing as well as non-monopolization. Now, our result established that if we start with some 2-dimensional classical coin, any arbitrary 2-dimensional classical coin, it is not possible to reach here using local operation, means locally stochastic matrix, or you cannot reach here. But now we'll see. So this is the chart what I have said. If you start with a 2-dimensional classical coin, and you want to reach in a 3-dimensional coin, you cannot make all of them zero. This correlated term, all of them are 0, and anti-correlated term, all of them are 1/6. That is not possible. You can achieve up to this. All of them are 1/8, and one of these correlated term will be 1/4. So our aim is to maximize this, all of this quantity, making them equal. So that turns out to be 1/8, but one of these correlated term at that time will turn out to be 1/4. So social distancing norm is not satisfied. Similarly, if we start with a 2-dimensional classical coin and want to achieve in 4 shock case, then again, all of them, we can achieve up to 1/15. But where we want to reach 1/12, we can reach up to 1/50. Now I will show that actually in quantum theory, we can achieve this. For that, Alice and Bob share this singlet state. This is a correlated state, means peculiar kind of quantum correlation. It is their entangled particle. So Alice and Bob share this entangled pair. And Alice performs some measurement on her part, and this measurement is described by this way. So this is a peculiar kind of measurement, 3-outcome measurement, but this is not projective measurement. Because though each of these POVM are rank 1 operator, they are not projector because there is a 2/3 factor. So this is nothing but a sick POVM. So in 2-dimensional case, our state space can be described by a block vector. Now you consider a great circle in this block vector, and you consider this 3 direction. This is the geometrically this measurement what I have written as equation. So this is called trine POVM. So it is easy to memorize. This is the symbol of this Mercedes, this trine POVM. Okay, Alice as well as Bob both perform the same trine POVM, and it turns out that our targeted coin state, this C3 EQ, that is obtained. You can it can be checked. If we just do this, apply this bond probability rule, it can be checked. In case of 4 game, in case of 4 shock case, our measurement same state they are shared, but measurement has to be modified. In that, instead of trine POVM, they have to perform SIC POVM. SIC is called symmetric informationally complete POVM. Both Alice and Bob have to perform the same POVM. So this establishes a quantum advantage. So some targeted task that you cannot achieve with classical coin, but can be perfectly achieved with the quantum coin. So it establishes quantum advantage over the corresponding classical resources. So in other words, quantum achieved this social distancing, breaking the monopoly. Okay. So now this singlet state is very fragile because it means even a thermal noise, little bit thermal noise will destroy this entanglement. Now the question is, can we make even this state is little bit imperfect? Can this quantum achievement will be there? Means what is mean by that? Operationally, that means in classical case, in 3-box case, 3 shock case, this quantity can be go up. Some quantum resource, we can obtain quantity more than 1/8, then we can say, okay, it is quantum success. We haven't achieved the perfect success, but we are achieving better than the optimal quantum classical success. And similarly for for shock case, if the success probability is more than 1/15, then again quantum success is established. Now, instead of the singlet state, let us consider a noisy singlet state. It is some with p probabilities, it is singlet state, and 1/p probability, some white noise is there, some thermal noise is there. Okay. Now, it turns out that we have actually shown that if this p quantity is greater than 1/4, you see, if p is 0, then it is completely noise, no singlet is there. If p is 1, then it is perfect state. Now it says, our result shows that if p is just greater than 1/4, in 3 shock case you will get achievement over the classical resources. And for 4 shock case, you will get achievement if p is just greater than 1/5. So you see, your this quantum achievement, quantum advantage is achieved with enormous noise. Still, quantum advantage is there. And more fundamentally, in this particular range, the states are not even entangled, because they will be remain entangled when this p value is strictly greater than 1/3. But below 1/3, they are still showing quantum advantage. Naturally, the question is, what is the resource then? We are not using quantum entanglement, but still we are getting advantage over classical theory. What is the resource? Then what gives us that advantage? We actually answered this question. This is a technical part, but what we have proved that non-zero discord. In that state, discord is non-zero, and we can actually prove this theorem that non-zero discord is necessary for advantage over classical coin in this 3 and 4 shock case. Now, this point is quite important because discord is a particular kind of quantum correlation which captures quantumness beyond entanglement, and there are lots of research in this quantum discord where it is advantageous. There are lots of results reported, but in many of those results there are lots of doubt or lots of question are still there. But in our case, we have mathematically proved that, at least we have proved that discord is necessary one. Of course, we are not saying whether it is sufficient or not, that is a different question. But what we can establish that discord is a necessary resource. Now, another scenario we can consider that, okay, what we have considered that referee share this coin state between Alice and Bob. Now we can consider a different scenario that Alice herself prepare a coin state and one part she sends to Bob. So that means shared randomness distribution. So for sending this one part to Bob, there must be some channel from Alice to Bob. Now in classical world, that is described by some classical channel, and quantum scenario, it is some quantum channel. So again, we can, in shared randomness distribution, we can ask whether quantum channel gives some advantage over the classical channel. Again, we find some affirmative answer. For example, let's consider qubit depolarizing channel. So what is qubit? In case of qubit, the state space, you can think it as a block sphere, and what this depolarizing channel does, depolarizing channel symmetrically shrink your state space. It will be like that. And how much shrink will be there? That is governed by this parameter beta. So beta is a number between 0 to 1. If beta is 1, there is no depolarization, means it is a perfect channel. But if beta is 0, then it is a completely noise channel, because all these blocks sphere will map to this central point. So beta characterize the noise parameter in this particular example. Similarly, you can think as a dephasing channel. So dephasing channel, this is the mathematical definition of this dephasing channel. Geometrically, you can visualize dephasing channel like this. So it is making your block sphere into an ellipsoid, and this width of this ellipsoid will be again governed by this beta parameter in this dephasing channel. Again, beta parameter here also, it can be 0 up to 1. Okay. Now, what we have established, we have shown that dephasing channel is advantageous over the classical binary channel. Now, we take, let's say in classical case, we take a perfect binary channel. Means that has classical capacity 1 bit. We have shown that if this beta parameter is just greater than 3 by 4, then it is advantageous even than a perfect classical channel for 3 shock case. And if this beta parameter is strictly greater than 7 by 10, then it is advantageous in the 4 shock case. Similarly, for depolarizing channel, we find that okay, if this beta parameter is strictly greater than 1/4, then this depolarizing channel is advantageous over this perfect classical binary channel. And similarly, if this beta parameter is strictly greater than 1/5, it is again advantageous in 4 shock case over a perfect binary channel. Now, quite importantly, this depolarizing channel, when beta, so now in quantum case, how to characterize a channel means how good a channel is. Channel means some communication means. So there are different questions, different way we can look into how good a channel is. At least 3 good quantifier is its classical capacity, its private capacity, and its quantum capacity. Now, if this beta quantity is strictly less than equal to 3 by 2 for depolarizing, or beta quantity is strictly less than 1/3 for depolarizing channel, then its quantum capacity is 0. So it cannot carry any quantumness. Of course, it may have some classical capacity, but its quantumness is 0. But even our result showing that even this channel has quantum capacity 0, still it can exhibit some advantage over the classical channel. So this depolarizing channel in this particular range, you can think, okay, it is like a classical noisy channel because it doesn't have any quantum capacity. But what our result established, no, you cannot think like that, because a perfect classical channel, what success they will give, enormously noisy depolarizing channel will give more success than that. And moreover, this particular range, the classical capacity is also much less than 1 bit. So if you have a classical channel of 1 bit, what you can achieve in case of, if we have a quantum channel of capacity, classical capacity much less than 1 bit, we can do something better than a corresponding classical point. So that's what I have said. A quantum channel can exhibit advantage in shared randomness distribution even when it does not have any quantum capacity. Okay, so far
Dr. Banik,
yes,
Dr. Manik,
please.
You have 5 minutes more.
Yes, sure. Thank you.
Yeah.
I'll take 2 minutes only.
Yeah.
So far I have discussed this our theoretical result. We are trying for some experiment. So these are my collaborators in this experiment. Kaumudi, Marcus Rambek, they are experimentalists. Shom Shankar, he is one collaborator in this theory paper. He is now in University of Hong Kong. And Mary Jacqueline Romero, she is our lead experimentalist. So we are trying to do this experiment. Due to this COVID scenario, our experiment is got little bit delayed, but we are hopeful very quickly we will come up with this experiment as far as what they have informed us. And our aim is to establish this quantum advantage in this shared randomness processing using polarized entangled photon in a noisy scenario. So with this, I end my talk with this quotation from Lenin. So thank you. And if you have any question and comment, I'll be happy to discuss.
Okay. Thank you, Dr. Manik, for a very nice talk. Now we are open for the questions. If anybody have questions, they can raise their hands or type in the chat box. So I'm picking up one question from RP Singh. Yeah. If it can be generalized for M parties and N shops, that is their question.
Yes, it is a good question actually. So N shop, we actually, you see, let me go back to my slide. My slide is still shared, huh?
Yes, sir.
So what theorem I have actually, we have established. Yeah, look into the theorem statement. In that theorem, we have actually shown that this quantum is advantageous over classical for any arbitrary D. Now D is equal to 3 corresponds to 3 shop game, D is equal to 4 corresponds to 4 shop game, but D is equal to 5, 6 onward I haven't discussed. But what this quantum advantage is established for any arbitrary D. But of course, the number of players is limited to 2 only. If more number of players will be there, that is good question. We think little bit on this direction, but we haven't, in that particular paper, we haven't come up with any result. In that case, probably this Z kind of state, W kind of state, we believe will show more interesting feature in shared randomness processing.
Okay, now we have one more question from Pooja.
Yes.
She's saying, what is difference between dephasing and depolarizing channel?
Okay, Pooja, you can see I have dephasing means it is shrinking the Bloch sphere uniformly from all directions. In case of dephasing, you see this Z line. If it is a dephasing along Z direction, the Z line remain intact. All other direction, non-uniformly it is shrinking. So it is mapping a Bloch sphere into ellipsoid, and in case of depolarizing, it maps the Bloch sphere into a shrink Bloch sphere. Yeah.
Okay. There is one more question from Anindya Banerjee. I am reading. Thank you for a wonderful talk. I have one question. Can you please elaborate on the operational meaning of a quantum discord? What does it mean to have a quantum coalitions beyond entanglement?
Yeah, so this is again a good question, but unfortunately, at least for the last 15 years, one of the main research direction in quantum, in the area of quantum discord is to give answer what is the operational meaning of quantum discord. Of course, there are some partial answer like in state margin, but not a very good intuitive meaning we don't know so far. But operationally means the state is not entangled, it is separable state, but still it contains some particular kind of correlation that is not available in classical world. I can only say in this way. So it is a bipartite state. We know what is the definition of entanglement. If a state is not entangled, then it is separable. Now discord states are they can be separable also, but still they capture a particular kind of correlation that is not available in classical world. In that sense, discord capture quantumness beyond entanglement. That cannot entangled state cannot capture. And operational meaning of discord, some work are there, state margin or some particular theorem is there, but it doesn't give a complete answer, and it is beyond the scope of my talk to here to discuss this state margin kind of things here.
Okay. Is anybody interested to maybe one more question? Okay, if anybody wants to ask a question, they can simply raise their hands. So the host will unmute you and you can enjoy the one-to-one interaction with the speaker. Okay, I hope there are no more questions. Let's thank the speaker once again.
Thank you.
Yeah. Now we are moving to our next talk. The next talk is from Sanjukjta Kundu, who is currently PhD student under the supervision of Dr. Radek at the Institute of Experimental Physics, University of Warsaw, Poland. She will be delivering a talk on a self-referenced hologram of a single photon beam. I invite Sanjukjta to deliver her presentation.
Hi, can you hear me?
Yes.
Okay, so I will share my screen now. So you can see my screen, right?
Yes, it is visible.
Okay, thanks. Okay, sorry. So good afternoon, everyone. I'm Sanjukjta Kundu, a PhD student of Dr. Wawkiewicz in Institute of Experimental Physics, University of Warsaw. And I'd like to thank the organizer for giving me a chance to present my work at your conference. And yeah, this is a sad case that for the pandemic that is going on all over the world. So let's see how things pan out. So today I'll talk about self-reference hologram of a single photon beam, which involves the characterization of the spatial structure of single photons. So now the question is, why are you interested in spatial structure of single photons? Well, photons are well known for being information carriers since they have many possible degrees of freedom. So among them, spatial degrees of freedom can be useful as realizing many quantum protocols. For example, free space quantum communication or quantum computation, quantum imaging. In such a scenario, what happens if we want to use the spatial degrees of freedom to extract information? We have to retrieve the phase of the single photons, and that is not trivial. It has been a challenging task actually for over the years, because these photons have this indeterminate global phase. So earlier, this has been tackled by tomographic approaches or weak measurement approaches, although these approaches lack the precision that can be provided by interferometric techniques. Okay, so a few years back, a group from our university came up with a cool idea, and their idea was based on Hongu-Madden interference. So what they did is that they overlapped their photon with an unknown spatial structure with a reference photon of flat phase profile. So, but this scheme has a downside. If you see that this reference photon has to be identical in all degrees of freedom to that unknown photon, except the spatial one. So experimental preparation of this unknown photon can be experimentally challenging. So we came up with a simpler idea here, and this is based on single photon can interfere with itself, and we don't need any reference photon here. Also, I would like to add one more point, that in the previous scheme, in the manuscript, they actually claimed that it's not doable with classical holographic technique or a holographic technique to retrieve the phase due to its indeterminate global phase. But here we are, we succeeded in doing so, and we have a paper in archive now, manuscript. So this is our scheme. We represent a modified Mach-Zehnder interferometer. What we did is we place a spatial filter in one of the arms. So when the incoming beam enters the Mach-Zehnder interferometer, when it goes through this arm, after passing through the spatial filter, its phase becomes flat. So that's how we create our reference photon, and then we overlap these two beams in the single photon sensitive spatially resolving camera. So after obtaining around, I think, 10 million of photon, we got our recorded interferogram, and later on we retrieve our phase from this interferogram. So this is our experimental setup, which comprises of mainly 3 parts. The first part is to preparing the heralded single photon source with the unknown spatial structure. Second part, where we prepare our reference beam, and third part is detection or measurement. So to prepare the heralded single photon source with a spatial phase profile, first we generate a pair of down-converted photons here via spontaneous parametric down conversion in the nonlinear crystal, and we use one of these photons to herald the others. So what we did is that we registered these photons, either signal or idler, to APD, which creates very short electric pulses, and we send it to trigger our camera, and thereby heralding our other signal. And to add a phase onto it, we place a faceplate, and that's how we generate our heralded single photon source with a spatial structure. So for preparing the reference beam, if you remember from the slide of the scheme, this is the same interferometer here. And the spatial filter is realized here via a pinhole that we placed it in the Fourier plane of a 4F imaging system. And that's how we create our reference beam, and then we overlap it in the camera. Okay, so here comes the detection part. So whenever every photon illuminates the intensifier, it has a chance to eject a photoelectron, and which in turn generate a macroscopic charge equivalent. And and that creates bright phosphor flash on the backplane. In this bright flashes on the phosphor screen on the backplane of the image intensifier, and then we image it via Rayleigh lenses to the SMOS sensor. So these bright flashes are actually corresponding to heralded single photons from our experiment, that you can see that you can discriminate it from the background. And then we considered a stack of frames, and then we summed over all the positions, and then we got our recorded interferogram here. So I would also like to say one more fun fact that we faced in our experiment while heralding our source. So to herald the source, whenever we saw that whenever there are two signals, triggering signals, going to our camera to trigger it, too close to each other, more than 300 kilohertz actually in our case, the gating module was started working randomly. And that's not what we want here, because then we can't get the heralded single photon. So to overcome this problem, we added a FPGA. And what it does, it was discriminating the second signal, second triggering signal, which comes too close to the first signal within the 3 microsecond range. So that's how we make sure that our the source is indeed heralded single photon, and it was maximizing our photon count rate as well. Yeah. So to retrieve phase, we use the standard Fourier off-axis holography technique, which takes us from the interferogram to the reconstructed phase in some following steps. So if you can notice carefully that we have added an extra linear phase here. It's just for the sake of our analysis purpose. Yeah, so I will quickly say what the Fourier off-axis holography technique is. I think you all know. So we took the Fourier transform of our interferogram, and due to this extra linear phase, you can see that this separates the phase dependent and independent part, and then we erase the phase independent part and half of it, which contributes actually same. Which contains the same information of the others. So from it, we took the inverse Fourier transform, and then we extracted the phase from the argument of it. Yeah, so that's how we get our desired phase. Well, we also removed the extra linear phase in this process before retrieving the phase. So this is the interferogram corresponding to the phase mask when you used 1D quadratic phase, actually a cylindrical lens here, and this is the corresponding retrieved phase. To reconstruct the uncertainty, statistical uncertainty for phase and amplitude, we used a Monte Carlo simulation. What we did is that we repeated the phase retrievals in thousands times, and each time what we did is that we draw the photon number of every single pixels from Poissonian distribution, considering the mean from the data we got from every pixel. So then after getting the phase reconstruction thousands times, we can get our mean phase and the uncertainty. So basically, we saw that the uncertainty is below 2 pi by 50 in the region of maximum visibility. It's actually in the center of with a radius of 50 pixels. These are another two examples what we measured. One is 2D quadratic phase, and another one is spiral phase. And these are the corresponding retrieved phase for it. And these are in good agreement with the theoretical results. Yeah. So in conclusion, I'd like to say that our self-preferencing technique, interferometric technique, doesn't need any reference photon, and which makes our method more robust and straightforward to implement actually. And also, as you see in previous slides, that we reconstructed the 2D phase as well, and it's not only limited to the one-dimensional phase reconstruction here. And our method is applicable to any pure states, including the orbital angular momentums as well. So I would like to acknowledge the team member who worked with me in this project. I would especially flag up Victor Shadowiak, who contributed the equal work as me. And thank you. Any questions?
Thank you, Sanjukta. We have a couple of questions here. First one is from Ali Anwar. He's asking how do this scheme? 1 minute. 1 minute. Okay. How do this scheme work for some structured light? Did you check it with a photon with a different phase?
Yeah, see, here is the spiral phase. If you see, this is a wave mode, LG01 mode. Yes, we checked it. So, and what is the specific question that how we did it?
Yeah.
Yeah, so yeah, this is an interesting question. Yes.
Yes.
Okay, so what happened in this case, if you see that this higher order spatial due to this higher order spatial frequencies, if we place the pinhole here, if you see in the here, so it will not pass any light, right? If it's a 0-1 mode, so there is no light in the center, so we have to move it transversely to maximize the transmission to pinhole. So that's how in case of this higher order spatial frequencies for structured light. Okay, so we checked for 3. One is 1D quadratic, second is 2D quadratic, and third is for LG01. So it worked.
Okay, hope that's the answer to your question, Ali. Another question is from anonymous attendee. Okay, what do you mean by spatial phase, and what is the meaning of hologram of a single photon? What for it can be used?
Yes. So first of all, as I said, that spatial phase means the transverse positions of the. If you consider the wavefront, it's the wavefront. How you shape it is basically we are shaping it, the wavefront of the photons. So that's what I mean by spatial phase here. And this is the spatial degrees of freedom, because we have several degrees of freedom, right? Like temporal domain, or in like here we consider the spatial domain. And also when it's spiral, it's also a spatial phase, right? A spatial phase in case of wave modes. So this is also this also falls into the spatial phase structure, single photon. And the hologram is, as you see, like it's the interferogram that we got here. So it's like the phase hologram. So this is a phase mapping, the wavefront. So since we are mapping this wavefront, that's why you call it hologram actually.
Okay, and there one more question was what for it can be used?
Okay, so I think I told you in the beginning that it's over the years it has been very challenging to retrieve the to use the spatial phase, because this single photons has this indeterminate global phase. So that's why these people were using tomographic techniques, or this weak measurement approaches. And so this is a fundamental thing that seems like fundamental photons. And also since it's simpler, we can probably use it in quantum imaging and quantum communication. And we are also thinking that if we can check it in terms of, in case of mixed state, because we have done it in only pure state, in mixed state or entangled states, or in fact in matter wave interferometry. So we are thinking about it.
Okay, thank you. I'm asking host if there are any questions from the other platform, YouTube. Meanwhile, anybody have a question, please raise the hand.
Yeah, sure.
Yeah, there are no questions from other platforms also. So thank you, Sanjukta, for a very nice. With this, now I invite Professor Andrew Forbes to deliver his talk on structural light from lasers.
Okay. Introduced at the public lecture, so I don't think it's necessary to read my biography again. And anyway, biographies are extremely boring, right? So my talk actually has got nothing to do with quantum optics. I decided to give a talk on lasers because last year my postdoc gave a talk on some of our quantum work. So I hope that you're not too disappointed that this is not a quantum talk, but I will show you one slide of a quantum paper that you can read if you're interested in what we do on it. So just to remind you, if you were not here yesterday, I'm at a university in Johannesburg. It's the University of the Witwatersrand. It's the #1 university in South Africa. It's produced 4 Nobel laureates. And a little bit to the left of this great hall is the School of Physics where my lab is. And my lab concentrates on structured light. And we do structured light in 3 different areas. We do it with classical light, which is what I spoke about yesterday. We do it in the quantum realm with entangled states, like you do in your lab in India. And we do it inside lasers. And today's talk is about how to do it inside lasers. But if you want to know how to do it outside lasers, then we've written sort of a tutorial type book that you can go and read, and we'll give you all the tricks that we know about how to create structured light. So I'll go back to my cartoon of yesterday, but because this is not a public talk, I'm going to go into a little bit more detail this time around. But just to remind you, this is how I like to describe what we do. We are given some initial beam, maybe it's a Gaussian beam, and we'd like to convert it into something else, and we just want to work out, how to do that. And once we work out how to do it, we can then think about how to implement it. So before I go inside the laser, let me just summarize how this might work outside the laser so that you have some idea of the principles of laser beam shaping. So in my opinion, you can do laser beam shaping in one step only if you're prepared to sacrifice something. So the first thing that you might sacrifice is the efficiency of the process. So for example, let's say I have a Gaussian beam and I would like to convert it into a orbital angular momentum beam. So I'd like a nice donut with a spiral phase. Well, I can do that in one step perfectly, but then I need to have amplitude and phase control. Now, some of you already create orbital angular momentum, and you might say to me, no, you can do it just with a spiral plate. That's not true. If you only use a spiral plate, you get many radial modes, so you don't really get what you want. If you don't want the radial modes, you need amplitude and phase control. On the other hand, you can do it in a lossless manner in one step, but then you must sacrifice your freedom. Like in sacrifice, maybe a solution step. Everywhere clear that that's what's going on. And here is a nice image taken from the University of Glasgow. It is the mode sorter that sorts orbital angular momentum. And all I want to show you here is that there's actually 2 elements. One at the beginning here that unravels the ring to a line, and a second one to correct the phase. And so you see that even when you're looking at detection systems, if you want to do lossless shaping, you need 2 steps. Okay, so that's a little bit of the fundamentals behind the cartoon that I showed you yesterday. Of course, we all know in reality that the situation is much more complicated, right? So here are some of my favorite papers on how to structure lights. Part of it's in scalar modes, part of it in vector modes, many different techniques. We've written a little tutorial on how to do this with spatial light modulators, but you can do it with, metasurfaces, interferometry, Q plates, even glass cones. You can do amazing things just with glass cones and generate all sorts of exotic light. So what I showed you earlier is absolutely true, but sometimes the situation is a little bit more complicated than how we make out. All right. So we know how to shape light outside the cavity. How could we do this inside a laser? That is the subject of today's talk. So let me give you my 1-slide tutorial on what a laser is. Okay. So here it is. Here's my cartoon. So to make a laser, you only need 3 things. The first thing is you need a medium that has the potential for optical gain. That means that you give it a photon, it gives you more photons back. That's number 1. Number 2, materials don't do that under equilibrium conditions. So we need something to get the material all hot and bothered, get it out of equilibrium. So we need a means to excite the medium, an excitation system. And the third thing we need is that we know from Einstein's equations that to get stimulated emission, we need lots of photons around. And so the way we keep lots of photons around is we put a box around this gain medium. Of course, the box is made of mirrors because we're dealing with the lights, and we call this optical box a resonator, a laser resonator. So those are just the three things that you need. Of course, putting them together could be rather complicated, but in principle, that's all you need. And what I want to discuss is what can we do inside this box in order to change the structure of the light that we get out. So if I want some particular structured light as the output, what would I have to do inside the box to make that work? So this problem actually has been addressed already, 60 years ago in the very, very early days of lasers. And so the first thing we could do is we could use amplitude control, so a lossy one-step process, to control what we get out of the box. And hopefully this little video plays. The idea is that, let's say you wanted Hermite-Gaussian modes. Well, because a laser is a competition of gain and loss, if I introduce very, very high loss at some places, I can prohibit some modes from lasing and prefer others. So for example, if I put a high loss wire inside the cavity, I can make the Hermite-Gauss modes fit in between the wires, whereas the Gaussian mode would not. And so I can force the laser to laser on the Hermite modes. So this is using wires and stops and funny apertures. By introducing losses, I can force one mode to win over the others. Okay. You can do the same thing, but from a gain perspective. So here's a very nice result from the Münster group that they did very recently. And what they did was they didn't have any amplitude mask inside the cavity. They used a DMD, a digital micromirror device, to structure the gain. In other words, to have gain in only certain places. And they made those places look like Hermite modes. And sure enough, what happens? The laser lasers on those modes because that's where it sees the gain. So rather than increase the loss, they increase the gain. So you can do cool things just with amplitude. To show you some of our own work on this, here's a little cartoon of a laser box with two mirrors, shown here on the right and the left. And I can change the curvature of those mirrors so that on each round trip, I have some magnification. I could make the field bigger, or I could demagnify and make it smaller. So what would happen in the context of structured lights? Well, then I would get structure within structure, because every time I go around, I get structure inside the original structure. And we have a phrase for that in the physics world. If you have structure within structure at many dimensions, we call them fractals. And so you can do some calculations and show that, in fact, as you zoom into the optical field that you would expect, zoom in once, twice, 4 times, 8 times, you would see the same structure repeating. And so it was predicted about 20 years ago that inside a laser, you should see fractal structure. And we've extended that theory also to the longitudinal domain, not just the transverse domain. So you can build a laser to test this idea. And I wanted to show you what a typical laser would look like inside our lab. So they would not be commercial lasers. It's lasers we build. So here you see one on the bottom. Above it, you see the cartoon of what it looks like in the paper. In the lab, this is what it looks like. You see the mirrors, mirror 1 and 2. You see the gain medium, the excitation system. So everything I told you, those 3 things are all there. And now you run the laser, and this is what you see. So as you move from one mirror at Z0 towards a very special plane inside the crystal, you start to see fractal light forming. So this is very strange because the fractals don't come out of the laser. They actually exist inside the laser. And you can do all sorts of tests to confirm that indeed this is actually what's going on. And how does it all work? It's really just the magnification of the mirrors. And as you change the apertures that you use inside the cavity, you can change the structure of the fractal light. And so what this does, it confirms that this theory of 20 years ago, in fact, is true. And you can read all about it either in the papers or you can read it in a popular account that we wrote about a year ago. Okay, so using using amplitude control, so just, apertures and blocks, we can generate all sorts of exotic light from lasers. Now, what about the phase control? What if we didn't do amplitude, but we changed the phase? So this is a problem that was addressed in the 90s and early 2000s by many excellent researchers. And what they showed was that you could put a phase element. In those days, they used diffractive optical elements inside a cavity. And by changing the phase, you could change the type of structure that came out. And my favorite example of this is by Frank Rorowski. Hopefully you can see the little video clip. And he designed a laser that would give a lambda sign as the oscillating mode. Now, I don't think he ever actually built this laser. I think this was purely a numerical calculation, but it's still a very nice example. So let me explain to you how this would work, because I've already explained how you would shape light outside a cavity yesterday. So let me explain the physics behind how you would do it inside a cavity. So imagine this is my laser. It's a very simple two-mirror system. And imagine the light is going to come out here on the left. And I'm going to pick some optical field, some structured light that I want. So what should I pick? Well, I can pick anything I like, but I'll pick a super Gaussian beam. So you see the blue curve is like a super Gaussian shape. And the purple is the phase. I'll pick a flat phase. This is an arbitrary choice. You can pick whatever you want. Okay, now how does this technique work of having a phase element? The idea is that you propagate this field backwards to the other mirror. And you see what you have. Okay, you have some weird shape now because of diffraction effects. And you have some weird phase. So the purple is now the unwrapped phase that you would get. And now what? Well, if you give the mirror the conjugate of this phase, what will happen? Well, then the field that you wanted propagates back to the mirror. It sees the conjugate. And so it will come back on exactly the same path that it went out on. And that means that it will return to what it was when it goes forward. And so from a laser perspective, as I go from one complete round trip around this cavity, I get back to what I started. And so you can see that that will repeat all the time. And that is the definition of a mode of a laser. And so you can confirm experimentally that that works. So here's an example from our lab. And so in fact, it is the super Gaussian beam that I just showed you. And indeed, if you make a mirror with this weird phase shape, and it looks like this actually in the design, then you can generate structured light directly from this cavity. And so I want to give you a practical example of why you would want to do this, because not everybody in the audience plans to become an academic one day. Some of you probably want to work in industry or maybe start your own company. So this particular example of the flat top beam was for a real applied project. So here's a very, very big laser. It's about the size of a small car. It's a big CO2 laser. And it goes on a gantry and it's used to remove paint from aircraft. And now, if you look at the beam from this laser under normal conditions, if I put an aperture inside it, I can get a nice Gaussian beam. That's what you see on this top panel. The M squared or the beam quality is very, very good, but the energy is very low because I make the volume small. If I open up the aperture and let all modes laze, well, the beam looks awful, and so the beam quality is very bad, but I have lots of energy. So this is always the trade-off in lasers. Usually, if you want lots of energy, you have a big aperture, but then you have lots of modes, no control. So when you come to the paint removal, so in this picture on the right, the paint is white and it has a green undercoat, and then it has a metal surface like the silvery color. And you can see that if you use the beam with lots of energy, then you start to damage the material while you still haven't removed the paint. And this beam at the top is no good because it doesn't have enough energy. So now you can use this idea of structuring the light from the laser by designing a custom mirror. And this is the custom design of that mirror. You can do some simulations. You start from noise and you watch the laser mode converge to what you want. So you know that the design is going to work. Then you can make the mirror and test that it is what it is. And this is the mode from the laser. And when you use this new beam, you can see now that as I increase the number of pulses on this material, you get nice, clean paint removal from the aircraft. And so this is a practical illustration that's previously you would have had lots of problems, and now you have very nice, clean beams. Okay. All right. So, that was quite a process, right? Because you have to design this phase and then you have to physically make the mirror. So something that we did quite a little while ago now, about 7 years ago, is we said, look, why don't we, rather than have a physical diffractive mirror, why don't we just put a spatial light modulator inside the laser? So my back mirror becomes a spatial light modulator. And now I can simply calculate a hologram and program it on the device. And what will happen? Every time I change the hologram, I will get a different beam from the same laser. So if you've ever built lasers, you'll know that trying to align them is quite a tricky game. But in this laser, you don't have to do any alignment after the first go. So you align it once. And now if you want a different beam from this laser, all you do is program a different hologram. And a hologram is just a picture on your computer. So we call this a digital laser because you can digitally control the properties of the device. Of course, it only works at low powers because spatial light modulators don't handle high powers. So it's no good for high power applications, but it's a very good test bed to see, does your design work? And what will the laser's performance be with that design? If you really want it for industrial applications, you have to push towards higher power. The group in Stuttgart under Thomas Graf have been doing a lot of really cool work over like a decade in this field. And here they've structured sort of radial gratings or azimuthal gratings in order to get radially polarized and azimuthally polarized beams at very, very high powers. And you can see that they're reaching somewhere in the order of a couple of kilowatts, which is the state of the art today. All right, so you can get to high powers if you push it. In our group, what we've been trying to do is to say, well, what if we started at low powers, but we passed the beam through an amplifier? So an amplifier is like the laser, but without the box. So it's just the gain medium and you get it excited, you pass the light through it, and you put some energy in, you get more energy out. And that's what you see here. We put a little bit in, and then it steadily increases in power as we increase the pump. And what we're interested in knowing is whether we can increase the power of a structured light beam without destroying the structure. And in these examples, we were modeling and measuring by experiments what happens with vector beams inside amplifiers. And something really cool happens. It turns out, and I'll mention it only quickly, that you can go in with a pretty bad vector beam, and by tuning the way you do the amplification, you can correct the weightings of the two scalar parts so that the vector beam that comes out is actually better than what it was going in. And that's what we try to show in this high order Poincare sphere, that I can start at some point on the sphere and I can move around the sphere by changing the way I do the amplification. All right, so if you've been paying attention, and I know this is a little bit fast, it helps when you do this talk in person because then you can gauge how the audience is following. But if you've been watching, you would notice that so far, I've only used one element inside the cavity. It might have been a mirror, it might have been a spatial light modulator, it might have been an aperture, but it was always one element. Whereas outside the cavity, I told you that if you use two elements, you could do it even better. So the question is, would you have anything at all to gain by using two elements inside a laser cavity? So the answer is yes. So here's my cartoon of a box. And this time you see I've got phase element number 1 on the left and phase element number 2 on the right. Now these could be glass plates inside the cavity, or they could be on the mirrors. That doesn't really matter. That's part of the implementation. But imagine I modulate the phase at 2 places. What is the gain that I get? Well, the gain that I get is that now I can specify the field at 2 places inside the laser. You know, previously I could only define the field that came out of the one mirror. But now I can define the field at the other mirror differently to the other side. And why would you want to do that? Well, remember I told you that when I wanted a really nice beam from my laser, I had to put in an aperture and make the gain small. So then I got a great beam, a nice Gaussian, but the energy was very small. On the other hand, if I had a large mode oscillating, then the mode looked terrible, but I had really high energy. Look at the energy difference. Here it's 250 millijoules, and here it was 6.3 joules. That's about a 20, 25 times difference. So if I could specify the field differently at the two mirrors, maybe what I could do is specify Gaussian at the output, but a high, large mode beam at the gain medium, so that I get the best of both worlds. I get all the energy from the big beam, but get it all into a good quality Gaussian beam. And so we designed a cavity to do exactly that, where at the one end we have a flat top beam to extract all the energy from the gain, and at the other end, the output end, we have a Gaussian beam. So we can calculate the two phases to do that. We can model the situation and measure and confirm that it's working. And you see here that, okay, the experiment is a little bit noisy compared to the theory, but I think we can agree that the match is good for the flat top and for the Gaussian. And then when you build the laser, indeed, you get these sort of nice Gaussian beams coming out at the one end instead of what you would have got like some weird beam. And so this is an approach towards high brightness lasers because you can get lots of power in a good beam quality. Okay, so there are ways to control the light with these phase and amplitude methods. But you know, lasers are really exotic structures, and only your imagination limits what you can do with them. So let me give you some examples of other cool things that you could do. So here's some very nice work by a group in Illinois. And what they did was they had two flat mirrors, and they put little microspheres, the same microspheres you would use in your optical trapping and tweezing. They're about 4 to 5 micrometers in diameter. They were glass spheres. They put them inside this little cavity, and then they got it to laze. And what happened was that every little microsphere acted like its own little laser, so that they could get hundreds and hundreds of different modes according to the size and position of the spheres. And in between the spheres, they claim to see fractal structures at the joins of these spheres. So you see, it's not just the curvature of the mirrors and the phase elements, you can do other things inside cavities as well. Now, probably like me, most people from the group that we're talking to like to use orbital angular momentum, like we just saw in the student talk, generating a nice phase structure of a single photon of an orbital angular momentum mode. Well, we know that outside the cavity, we can easily generate an orbital angular momentum mode if we just pass a Gaussian beam through a spiral plate, and we could implement the spiral plate, say, with a hologram. So then we would generate a vortex beam. So the question is, would that work inside a laser? Could you generate orbital angular momentum directly from the laser by this technique? So it's a little bit tricky. So to understand why it's tricky, look at this. Here are two vortex beams. The only difference between them is that one has got a plus, I think they actually plus and minus 3. So one has got a +3 charge, the other one a -3 charge, okay? But look at the intensity. They have the same size, same divergence, everything is the same. And so the laser can't tell the difference between these two modes based on losses. And so what the laser says, well, in that case, I'm going to laser on both. And if you add up these two together, you get petal patterns. So now the laser says the following. Okay, I'm going to laser on petal patterns, but there's actually two types of petal patterns. There's the sine and the cosine, all right? Because that's just the same pattern, but just rotated a little bit. And so now we have the following case. There's two ways I could get a ring of light. The way I want it is to take the cosine plus I of the sine, because then cos theta plus I sine theta gives me the orbital angular momentum that I want. But the other way is that if I got cos squared plus sine squared, that would also take away the petals and give me a ring of light, but there would be no vortex phase. So the laser that gives a ring of light could be a vortex beam or it could not. So how could you tell? Well, it's easy. What you can do is the following. You could take some points on your ring of lights. Let's say points 1, 2, and 3. And let's say that points 1 and 3 are from the same petal family. Let's say the cosine family. So we would expect, because they're definitely from the same petal family, there should be fringes. And now we can compare it to petal number 2. So petal number 2 would be from a different family, let's say the sine family. If there are fringes between number 1 and 2, then it means it's the same beam, so then it must have orbital angular momentum. But if it's an incoherent mix of those two, there'll be no fringes. And when you do the experiments, you see fringes at the bottom between 1 and 3, and no fringes between 1 and 2. So this means that the laser is not lasing on an orbital angular momentum mode. In fact, it's just an incoherent mix of the two modes. And so you have to be very careful when you say that you have orbital angular momentum from a laser. A ring of light doesn't guarantee it. So the message is that you have to do something strange inside the laser in order for it to give you orbital angular momentum. And here are some of my favorite examples. At the top row, you have some solid state lasers. I'm going to talk about one or two of them in a second, doing weird stuff to get it to work. In the middle row, some fiber laser systems. You can also do some cool things in fibers. And the bottom row is on-chip OEM lasers. So let me give you one example from each category to show you what you might do. So here's some really nice work from the Kim group in South Korea. So all they did, very, very simple, they built a laser just like the ones I showed you. And then they realized that the pointing vector of an orbital angular momentum beam is spiraling. And so it has a slight skew angle. And so they said, oh, well, then if I take a glass plate and I angle it just precisely, then for one skew angle, the Fresnel loss will be higher than for another one. And so I can, by adjusting this plate by just a few degrees, I can actually make one-handedness of the laser have a higher loss than the other one. And so I can force the laser to be in only one mode. And that works. So just with the little glass plates, they could get orbital angular momentum from their laser. Jian Wang's group in Wuhan. Wuhan's not a very popular place to be at the moment, but he combines free space and fibers using spatial light modulators. And by programming the holograms, he can force one mode inside the fiber to laze. And so now he can tune the OEM by tuning what that mode is on the spatial light modulator. And he can tune the wavelength by just tuning the Bragg gratings inside his fibers. So he has a tunable fiber system to give you different OEMs. I think the band is about 10 in OEM and about 30 nanometers in wavelength. So a very nice tunable system. And very recently, by the CNRS group in France, they showed that you could make a topological structure that sits on a chip. So here you see them as these little sort of flower-like petals. And what happens here? So what the novelty of their work is that they engineer the topology to be switched by the spin state of the light. So to say that in a simpler way, if you excite these, then you get nice helical structures that are also the same handedness. And if you, so in other words, say a clockwise L+1 mode, and if you excite it with the opposite circular polarized light, you get the opposite helicity in the OEM. So they can tune the helicity of the OEM by tuning the state of polarization that they come into their structures with. And here you see some experimental images, the interference grams, confirming, in fact, that this really does work. So that's really cool. So I'll show you in the next two slides some of our own work in this direction. So we decided that it should be possible to use geometric phase inside a laser. No one had done that before at that point. And so what we did is we put a Q plate inside a cavity together with a wave plate. So now as I change the charge on the Q plate, so the Q plate is a geometric phase element that also controls the phase. I could control the orbital angular momentum that comes out of the laser. So here's an L1 beam and here's an L10 beam directly from the laser. But then the cool thing about this laser is that you also have the wave plate. Because if you've ever worked with geometric phase, you will know that you need to control the polarization that the element sees. Now, if you think about it, I've got two elements, a wave plate and a Q plate, and I can rotate both elements. As I rotate the wave plate, I change the state of polarization. And as I rotate the Q plates, I change the relative phases. So what does that mean? Well, it means that on the high order Poincare sphere, how many degrees of freedom do you need to move around a sphere? You just need two, right? A rotation in this direction, a rotation in that direction. And so it turns out that by rotating these two elements, you can generate beams everywhere on a high order Poincare sphere. And so these are experimental images coming directly out of the laser by just turning these two elements. Now, if you go to the equator of a high order Poincare sphere, you get the cylindrical vector vortex beams. So for example, one example would be radially polarized light. So that would sit over here on the sphere. And here you see the experimental images that indeed this laser gives radially polarized light out, and you can confirm that by a whole bunch of measurements. So this laser, because it's based on geometric phase, if I turn the plates to some position, I can get pure orbital angular momentum modes, plus or minus. And then if I turn the wave plates, I can swing around onto the equator and get all the polarized, all the vector beams that I want. Okay, so anywhere on the sphere is possible. The only problem with this device is that it was based on liquid crystals. So liquid crystals are fairly large. They're sort of 10 micrometers, the pixel sizes. And so the type of OEM that you can get is limited. And also the power handling ability is also limited. So what we did recently is to move away from liquid crystals to metasurfaces. So here you see a nanostructured metasurface. And what this nanostructured metasurface does is that if you come in with scalar non-structured light, it generates arbitrary superpositions of orbital angular momentum. And so we built a laser with this intracavity metasurface. So here's a cartoon of what it looks like. Take a moment to look at the cartoon. You'll see that it's just the cartoon that we showed you earlier on. I have two mirrors. I have a metasurface inside the cavity. In fact, this was a second harmonic generation cavity. So it was a cavity inside a cavity. And so now, because I have nanostructures, I can go to very high OEM. Because I can position them very, very well, I can get very high purity. And because it's a nanostructured surface, I can make things very small or very big. So I can bridge this bulk to compact design. And so you can go and read about this now, our recent paper on the subject. And now I can show you that, in fact, it works. So on the right, you see a little movie, hopefully, if it's running on your screens, that shows the evolution from noise to the orbital angular momentum mode. And you see that eventually after about 1,000 trips, it's stabilized. And so this confirms that the mode should work. And experimentally, because this metasurface allows us to have arbitrary OEMs and vector superpositions of it, we designed one of the examples to give us a beam that lased on L10 and L100 at the same time. And so here you see experimental images as I move around the Poincare sphere, but now it's an asymmetric Poincare sphere. I can tune from 10 to 100 from exactly the same laser without changing anything. And I sometimes get asked, why would you want to do things like this inside the cavity? And so the reason is that if I were to generate these beams outside the cavity, I would get lots of rings. So you see here, lots and lots of rings because of the radial modes. But inside the cavity, I can suppress these radial modes. And in fact, I can do some analysis. I'm not going to go through the details. It's not so important. But I can measure how much energy do I have in the P0 mode for my given L mode. And I can show you that inside the laser, it's entirely pure. All of it is in the P0, this blue peak. Whereas outside the laser, I have a big distribution across many, many radial modes. So lasers can give you the purity you want with the power that you want, or from a compact source. Okay. Now, the idea of going to nanostructures opens up the ability also to go to other exotic geometries. And so, although I've spoken primarily about Fabry-Pera resonators, I want to show you just two examples of other beautiful work of other groups. So this is a group in Vienna, and they've used a random media. So it's a random laser, but by doing some structuring of the pump and the polarization of the pump, you can structure the output from your random laser. So you can go from sort of complete randomness all the way through to really nice concentrated beams. So you see this notion of structuring the light can take many, many different forms. And here's an example from the Creole group. And here they're using protected states in topological insulators. So basically their laser is like a ring of some strange shape. And then the lasing light moves around this ring. And if you look at the bottom example, you see what they do is they deliberately introduce a defect into their ring. So here it's like a square ring, and they introduce a defect. And if you do this in a normal laser around the ring, then you don't get very bright lights. But in a topologically protected state, it means that it's robust to any perturbation. And so here they show that, oh, look, the light is much, much brighter. Why? Because they're using topological photonics to introduce this robustness to noise and perturbations and so on. And so even though there's a deliberate defect in their structure, their laser still works really, really well. So the hope is that if you use these topological approaches, you could still build your conventional laser, but now you could make it less sensitive to all the aberrations and problems that you might typically find as you go towards higher powers. All right, I'm coming to the end of the talk. I know it's been quite a lot of material, but hopefully you've been following me along. And if you have, I probably have left you with the opinion that you need very complicated structures, either as a liquid crystal or a metasurface, or here as a topological structure. You need really complicated structures if you want to get structured light from a laser. So I want to end by dispelling that notion, okay? So have a look at this little diagram. If you look at the top, don't worry about the bottom so much. I'm not going to go into that in this talk. Have a look at the top. Do you see that it's just the simple two mirror system that I showed you before? So here at this box has got a curved mirror at the top and a flat mirror at the bottom. Okay, so curved at the top and flat. And then as we move across from left to right, the only thing that's changing is the length. So I'm just making the box longer as I go across. And what happens? So what we're trying to show here is that, well, if you think about the laser mode not as one complete coherent mode, but as rays bouncing inside this box, then you can draw which rays would be stable and which would not. It's really like a high school geometry problem, you know, how to align them up. And so you can see that the shape of the bounces look different as I change the length, and the number of bounces look different. But because it's all from a single laser, it's all the same coherent mode. So what this means is that this laser, if I adjust the length really accurately, it should give out rays of light. And here you see some pictures, actually, experimental images of that. But although they look like separate rays, they're actually just one beam, but one beam of separate rays. So you can build a cavity like this, and the cavity is nothing more than two mirrors and a gain medium, nothing else inside it at all, no special elements. But the length is very carefully adjusted. You build the experiment, and now you can measure. So here we have measured inside the laser, shows the little beams bouncing back and forward. Here overlaid are the two mirrors, and you see this is like a W-type trajectory. And what it means is that you can get this multiple ray output, and you can control these rays, you can label them, you can polarize them. And what it means is that you can generate very exotic, multi-dimensional structured light from an extremely simple laser. And if you'd like to know more about that, here's our nice sort of not cartoon, an artistic version of the laser on the cover of Optica. And you can read about it. It came out about a month ago or so. And just to give you a little bit of quantum stuff at the very end of this talk, because you have multi-dimensional structured light, because I can polarization mark every path, I can go to high dimensions from this simple laser in classical lights. And so I can generate directly from these lasers GHZ states, but classical versions of the GHZ states. And this work is under review, but here I show you the fidelity, the measured fidelity of all 8 of these GHZ states. So this is an 8-dimensional space directly from a laser, and you see that the fidelities are all around 90%. And all it was is 2 simple mirrors and a little bit of a gain medium. All right, hopefully that note inspires you to go and play with lasers a little bit if you have not already done so. Let me conclude now by saying that in my group, we work in quantum, in lasers, and in general structured lights. And if this talk has been a little bit fast on the laser part, you can read a recent review on structured light from lasers. And if you want to know a little bit more about the general work that we do, maybe you saw the June issue of OPN, or there I've summarized what I understand about structured lights. And on the quantum side, we have a nice little tutorial type review quite recently that also summarizes everything we understand about high dimensional quantum mechanics with structured lights. Because I'm in a quantum session, I thought I should just show you a picture of our most recent work. So I'm not going to talk about it at all, but in this month's issue of Laser and Photonics Reviews, you can see our most recent work on high dimensional quantum secret sharing, reaching 11 dimensions across 10 parties. But if you came for a quantum talk, I'm afraid you're not going to get one, so I apologize for that. Okay, well then to finish off, I always like to thank my collaborators, because we love to collaborate and we do a lot of it. And so, we've not yet collaborated with groups extensively in India, only in Chennai, but we would like to increase that if we could. My students, of course, do all the work, as I said yesterday. And once again, thank you very much for listening.
Yeah, thank you, Professor Forbes, for a wonderful and informative talk. Now we will pick up few questions. First one is from RP Singh. Okay, here a comment as well as a question. Wonderful talk. Can you compare meta surface and topological material when it comes to making structured light?
So topological materials are also usually done on chip. They don't have to be, but they are usually small on-chip type structures. And the design principle is different. So you're using topological photonics, topological insulation ideas, protected states. Metasurfaces are really just a way to implement arbitrary amplitude, phase, and polarization control that may not be possible in other implementation methods. For example, diffractive optical elements typically only do the phase. So in my world, I use metasurfaces just as more robust, more power resilient versions of phase control of light. Whereas topological photonics, which we don't do in my group actually, is much more sophisticated and gives you a lot more design freedom.
Okay, there is one more question. Can you elaborate ray and wave duality?
Just repeat the last part, elaborate on?
Ray and wave duality.
Oh, right. So the idea is that if you've ever looked at a laser beam in your lab, what you probably see is like a blob of lights, maybe a Gaussian beam or some strange beam and so on. But if you tune the length of the cavity with the correct curvature, you can force the laser to jump into a mode where it actually looks like rays bouncing back and forward. And so this is called ray-wave duality because it now looks like the laser is giving out lots of rays, but actually it's one coherent mode, one wave. It's still a wave, but it looks like lots of rays. So you have the freedom to manipulate it as rays or to manipulate it as one paraxial beam. And this is called ray wave duality. If you read our Optica paper, we've got a very, very long supplementary information that gives a long tutorial on how this works.
Okay. There are actually two questions from Pranav. He's asking, could we not simply reduce energy of the rectangular beam using ND filters and scrap the paint?
Yes, you could do that. But then what would happen is that it would take longer for the process to work. So the way the process worked is that even with that high energy, you couldn't do it in one shot. So you require many shots, typically about 20. Actually, even if you could get the energy up for one shot, the production people don't like that. It's too risky because one shot, if something goes wrong, it doesn't work. But 20 shots, you have a little bit of a better average, you know? So yes, what would happen is it would just take much longer. And so then the whole production would slow down. So that's why you want as high energy as you can have and to make it run fast.
Okay.
Forbes. Hello, Satya, can I ask a question?
Yeah, sure. Go ahead.
Okay, Forbes, thank you for giving another wonderful talk. So my question is, so you said some of the donut shape came directly from from the laser light. So you said it's not be necessary that it can carry an orbital angular momentum. So then how will be its phase structure? Can I call it as a Hermite, or is it a Hermite-Gaussian beam?
What it is a superposition of two Ligier modes, but one, the odd and the even, so a sine and a cosine. So if you look at any typical laser textbook, they will not talk about orbital angular momentum because e to the I L phi is not really, you can't have imaginary terms. So the LG modes come in a sine and a cosine form. And what you want is those to be coherently added to get OEM. But if they don't, so you see this ring, if they incoherently added, then you just have the sine and cosine, no OEM, but a ring of light.
But what about the phase? So we can't.
There's no. So the phase would be flat around the ring.
So then we can call it as a Hermite-Gaussian beam.
Well, I don't know if you could call it that because you have an incoherent sum of two modes. It still looks like a ring, but I'm not sure. It's not that you have two LG modes coherently added to give you, like, say, a Hermite mode. No.
Okay, then what about the generated petal structure from that directly? From that laser. So how will be the phase structure of that beam? It will be a flat surface, or
so the petal structure. Yeah. So the petal structure is you get a petal structure when you have a coherent sum of two OEMs of opposite handedness, right? Yes. So like, let's say you had +2 and -2, you would have a beam with 4 petals. And the phase structure would jump from 0 pi, 0 pi, 0 pi, like that.
Okay, thank you.
Yeah, one more question from our audience. What is the application of fractal laser light?
Of fractal laser light, yes. That's why on my slide I said for no use at all. So at the moment we don't have any immediate application of it. But you can dream a little bit. And one of the dreams might be to say, well, maybe since we have structure within structure, and we already know that structured light plays a big role in better resolution and imaging, would it be possible to image at different levels or different dimensions if I had structure within structure, so imaging with fractal light? I don't know the answer to the question, but that's a dream, possibly, right?
Okay, I missed follow-up question from a Pranav. He's asking, how is it that individual beams are moving at an angle while the entire beam is moving without diverging?
Is this the ray wave beam?
how is it that individual beams are moving at an angle while the entire beam is moving without diverging?
Yeah. Okay,
yes, Satya.
All right. Okay.
Yeah,
so
yeah. This is in context to the rays.
All right. Okay. So, well, you can think of it like this. It's not the same actually, but you can think of it like this. Think of it like the Hermite modes. It's one mode. It's one beam that has a certain divergence, but you can each of the little peaks. You can also track them and see where they're going. Right. So you could think of them as like rays. This is not the same situation. Each ray is going at a very fixed angle. So it's not like they're random angles. They're very fixed. So the whole beam has a divergence given by these angles. I could split off one of those rays and treat it separately. Of course, I would have disturbed the whole beam. It would be like taking one of the peaks of the Hermite mode and sending it somewhere. I would have disturbed the whole beam, but I could still manipulate each one. Yeah, and the angles of those rays are determined just by the curvature and the separation distance. So it's very easy to calculate those things.
Got it. Thank you.
Okay. Is there any question? Please raise the hand.
Satya, I have one more question.
Yeah.
May I ask? Sir, you had talked yesterday about OM of electrons. And then you talked about something very intriguing and interesting where even though the electrons are carrying an OM, each individual electron is moving in a straight line. So I just can't wrap my head around that. How is this happening? So there is no acceleration, obviously, because they're moving in a straight line. But how is it that they're moving in a straight line, but the net effect is something twisting?
Yes, so one way to think about it would be the famous Miles Paget likes to do this thing where he holds some. Have you ever held like spaghetti? You know, you hold spaghetti when it's hard, so before it's cooked, and then you twist it, give it a twist. And what happens is the spaghettis, they all spin out. I don't know if you've done this.
Right. I follow what you're saying. That is how I was thinking it.
Yeah, so each one is going at an angle, and that's related to the skew angle of the pointing vector. And
exactly.
Every ray is slightly
so that would imply that the beam is always going to diverge. And therefore, that is why we observe these beams diverge.
Yeah. Yes.
Okay. Thank you.
I hope there are no questions. So let's thank the speakers once again. Thank you, sir.
Thank you.
The next talk is from my colleague Sarika Mishra, who is currently a PhD student under the supervision of Professor R.P. Singh here at PRL Ahmedabad. She will be delivering a talk on generation of polarization entangled photons through quantum interference. I invite Sarika to deliver her presentation.
Thank you, Satyajit, for your kind introduction. So I'm sharing my screen here. Through quantum interference. So here is the wait. I don't know what is happening. My slides are not moving.
It's not changing.
Yes, it's not changing. Right now it's changing. Okay.
Yeah,
so
it's changing.
Okay. So here is the outline of my talk where I'll talk about what is quantum entanglement and how we can generate this entanglement and how we can prove the entanglement. And at the last, I will show some of my experimental setup and the result, and then I'll conclude my talk. So what is entanglement? So the simplest meaning of the entanglement can be understood by this pictorial representation. So if two persons, A and B, are linked together in such a way that they are, whatever happens to the one person, it will directly affect the other person, then you can say that these two are entangled. So this unique correlation was first introduced by Erwin Schrödinger in 1935. So suppose you have two subsystems and they are created from the same source, or they have interacted in the past once. So because of that, they will establish a strong correlation between them. And even if they are separated by a large distance, the correlation will be maintained. So in this process, these subsystem will lost their individuality, meaning that each subsystem cannot be represented individually. The measurement performed on one subsystem will reveal the information about another subsystem. So mathematically, the combined state of these two subsystems is entangled if we cannot write as a direct product state of two subsystems, meaning that they are not separable. So here I am giving two examples so that you can distinguish between the entangled state and product state. So in the first example, you can see here, you can easily separate out these two subsystems. So you can say that it's just a product state and not an entangled state. But in the second example, you can see here, it is impossible to separate out B. So you can say that this state is entangled. Now, suppose I want to measure the spin up state of subsystem B, then the whole state will collapse to give the information about the subsystem A with 100% probability. So you can see here, I am projecting the state of subsystem B, but as a result, I am getting the state of subsystem A with 100% probability. So this shows the entanglement between A and B. Now this entanglement can be between in any physical degree of freedom. So it can be in polarization entanglement or vital angular momentum entanglement or spin entanglement, etc. So here we will talk about polarization entanglement. As we all know that polarization entanglement is one of the pillars for quantum information, for example, quantum QKD, quantum key distribution. So for the polarization entanglement, we have 4 Bell states here, depending upon the HV basis. So you can see here for the psi plus minus state, the result will be HV or VH. And for phi plus minus state, the result will be HH or VV. So since in case of psi plus minus, they both the photons are orthogonal, so you can say that this is negative correlation and this is positive correlation, since both the photons have same polarization. Now we know what is entanglement and how we can write the entangled state, but how we can prove that the given state is entangled? So if there is any entanglement, then if you transform your state from one basis to another basis by unitary transformation, then the correlation must adjust for that transformation. So for HV basis, if I talk about HV basis, so you should also get the correlation for DA basis as well. So it will ensure you that your state is entangled. Now there is another way. So to check the entanglement, we use the Bell inequality test. So this is just a mathematical expression. So it involves the polarization correlation measurement, where E is the correlation coefficient. So you can see from E alpha beta. So for positive correlation for HH and VV, the E has value +1. And for negative correlation, E has value -1. So in general, the Bell inequality S has value less than 2. But if your state is entangled, then for certain polarization angle values, you will get the S value of 2√2. This is the maximum value of S. So you can say that you can see here clearly that your Bell inequality is violated, which is greater than 2√2. So if you are getting the S value greater than 2, then you can say that your state is entangled. Now, how we will generate this entangled state? So the most popular technique to generate entanglement is spontaneous parametric down conversion, where a pump photon, when the pump photon interacted with the second order nonlinear crystal, it will create 2 photons, signal and the idler. So in this case, signal and the idler has orthogonal polarization. So in this process, energy and the momentum is also conserved. So because these two photons will generate at a two diametrically opposite point. And if you consider all the points of diametrically opposite points, then you will get a ring kind of structure, which is also known as SPDC ring. So first ring is for H polarized light and the second ring is for V polarized light. And these two intersection point will give you the state psi is equal to half HV plus exponential I phi VH. Now, where this phi terms is coming because of this birefringence property of this crystal. So because of this property, both the polarization will face the different refractive index, and because of different refractive index, their velocity will be different. So it will create a phase difference between two photons. Because phase difference and path difference are directly proportional to each other. So because of the path difference, there will be phase difference as well. So it will not give you a maximally entangled state because of this phase difference. So to compensate this phase difference, we have two solutions. Either we can use a specific phase compensating crystal, or we can use an interferometric technique. So in this interferometric technique, am I audible, right?
Yes, you are.
Okay. So in this interferometric technique, what we will do is we will just separate out these two photons and then again combine these two photons, superpose these two photons in such a way that there should be no phase difference or there should be no path difference. So this is how at the output you will get two photons, two entangled photons. So now I'll talk about the interferometric technique, which is here I am using a two photon interference, which is also known as Hongomandal interference. So as we know that when one photon enters into the beam splitter, it has two possibilities. Either it will reflect or it will transmit. But if the two photons entering onto the beam splitter, each input mode of the beam splitter, then there will be four possibilities. Either they will anti-bunch and exit from the two different output ports, or they will bunch together and exit from the same output port. So there will be two anti-bunching terms and there is two bunching terms. Now, let's assume that your two photons are identical in all degree of freedom. For example, polarization, frequency, spatio-temporal mode structure. So if they are identical, then these two terms will be cancelled out and you will get only bunching terms. Now, how we will detect these two? How we will detect in the experiment? So what we do is, after the down conversion process, these two photons are entering onto the beam splitter, and at the output port of the beam splitter, we have connected two detectors which will detect the photons, and these two detectors are connected by the correlator to give the coincidence count. So when both the detector will register one photon, it will give one coincidence count. And if only one detector register one photon and there is no photon in the other detector, you will get zero coincidence count. So this is the graph is showing the same what I have said here. So you can see here at this point we are getting zero coincidence. It means this is the case, second case, where these two photons are only showing bunching effect. So you can see only one output port you will get photon, and in the other output there is no photon. So they will give zero coincidence count. So it ensures that your two photons are coming at the same time. So you can see here where at the time of indistinguishability there is no phase time difference, and if they are distinguishable there is a path difference and you will get maximum coincidence count. And if they are partially distinguishable, you will get some coincidence count. So our task is to find this point so that we can compensate the phase difference between two photons. So this is just the mathematical expression of the beam splitter, whatever I have said earlier in the previous slide. So you can see here, this is the input state of the beam splitter A and B. And you can calculate the output state by using this unitary transformation. So you can see here we are getting four 4 possibilities, and if they are identical, here I and J is the physical properties of the 2 photons. So I and J can be your polarization, frequency, OM, orbital angular momentum, anything. So if I is equal to J, you will get only 2 terms. So these terms is also known as noon state, where N is the number of the photon. So here is the experimental setup of my experimental setup for 2 photon interference. So you can see here a half wavelet pump. I have used a laser of wavelength 405 nanometer, and when it passes through this type 1 VBO crystal, it will create 2 photons, and these 2 photons are passing through these 2 different paths. And at one path, at one of the arm, we have introduced the delay stage so that we can ensure the same time of arrival. So we have to find that point, and then both these photons are combining again onto the beam splitter, and the output port is connected to the SPCM, single photon counting module. It will detect your photon counts. So you can see here at this point, we are getting minimum coincidence. So we can say that at this point, there is a no phase difference. So we have now we have find that point. So we will fix our delay stage at this point, and now we will generate entanglement. So we will use this half-wave plate to generate entanglement. So
Sarika, you have 5 minutes.
Okay. So I have 5 minutes. No, I have 20 minutes left. So I started at 4 o'clock. So I think I have, okay. So you can see here.
5 minutes more.
Okay. So from the output of the beam splitter, there is anti-bunching part and the bunching part. So for now, first we will talk about anti-bunching part. So you can see here in anti-bunching, both the photons are going to 2 different output ports. So what we will do is we will change the polarization of one of the input port into H. So you can see here at the input port we have 2 orthogonal polarization. Now it will either reflect or it will either transmit. So every time we have 1 photon here and 1 photon here. So whenever we measure 1 photon here, it will give the state of other photon with 100% probability. So we will fix the polarization state here, and we will scan all the polarization state for the other photon. So this is the mathematical calculation for the coincidence detection. So this is the visibility plot we have got. So we have got very good visibility, almost 97%, and we are getting visibility for DA basis as well, which is important. So we are getting 95.7% visibility, and we have calculated the Bell inequality, which is 2.69%. Now, if we talk about the bunching effect, so in bunching part, both the photon will go into the same direction. So now for the measurement, we have to again separate out them. So we have again put 1 beam splitter so that both the photon will get separated out into 2 different arms. And again, we will do the same process, same measurement process. We will fix 1 polarization state here and scan all the polarization state for the other photon. So again, we are getting a very good visibility. In this time, DA visibility is less than the previous one. So it is 86.97%, and hence the Bell inequality is also less than the other one, which is 2.45%. Now, with the help of psi plus minus state, we can also generate phi plus minus state. How? So this is the psi plus state, and this is the phi minus state. So if we can change the polarization of our ideal photon into orthogonal polarization, then you can see here we will convert into the H, and the H is converted into the V. So you can see here we have put 1 half-wave plate here. Now we know in each output port there is a mixture of H and V photons. So if we rotate our polarization into 45 degrees, so it will convert H polarization into V and V polarization into H. So here HV, and again now you will get the correlated photon HV. So the result will be HH or VV. So we have converted these two. So this setup is for psi minus state. Similarly, you can make setup for psi plus state for bunching effect. So we have got very nice visibility for psi plus and psi minus as well. So you can see here for DA visibility and for HV visible for the HV basis, we were getting excellent visibility. So I have calculated the Bell inequality. So for phi minus, I was getting 2.6294. Bell inequality, and for 5 plus I was getting 2.4035, so which is violating our Bell inequality. So we have used a SPDC process to generate a pair of entangled photon. Then we have used an HM experiment, Hongo-Mandel interference experiment, to compensate the phase difference between two photons, and we have successfully generated all the 4 Bell states. Thank you.
Thank you, Sarika, for very nice talk. We will pick up few questions.
Okay.
If anybody have a question, please raise hand.
Hello.
Okay.
Hi.
Yes.
Hello.
Hello.
Yeah. Anindya here. Okay. So basic question. If you compare your setup to like more common setups for generating entangled states, where you use like either an interferometric setup, like say a Saniac single crystal setup, or say a 2 crystal setup, how would your setup compare in terms of fidelity of the states produced or the efficiency and all that compared to like the more common setups that are used?
Okay, so in this setup, there is a loss of photon, as we know, as you can see here. So for this setup, we are only considering this part, and we are not considering this part for psi minus state. So obviously there will be a 50% loss here. So in this case, there is a loss. So I have not done Sagnac interferometer technique to generate entanglement, so I don't know about that. But definitely there is some losses. But this technique is helpful if you have no other options, like if you don't have phase compensating crystal to compensate the phase.
Okay.
Yes.
Anybody else?
Yeah, here, RP. Sarika?
Yes, sir.
In the last slide, you are showing like Bell inequality violation, yes, parameters. It is.
Yes, yes.
For states, it is 2.69. But
yes.
2.4. Why this kind of like 0.2 difference exactly in this psi minus plus and phi minus phi?
Okay, so actually this part I have done before lockdown, and this part I have done after the lockdown. So I have to rearrange again the setup. So there might be some alignment error or something.
So you are expecting it will come out to be almost same as?
Almost same. It should be almost
because
same.
Of some experimental imperfections.
Yes, one thing here, when we are introducing one half-wave plate, so if the angle is not exact, then also you will get less Bell inequality.
Okay, fine. I thought, yeah, there is some systematic
yes,
problem.
one problem with half-wave plate, because it is not accurate, so there will be some mismatch. Always there will be some mismatch in angle of the half-wave plate.
Okay, thank you.
Okay.
Yeah, one last question, if it is there any. Okay, I guess there are no more questions. So let's thank the speakers once again. Thank you, Sarika.
Thank you.
With this talk, we conclude this session. I want to thank all speakers for. Yes.
Hello. I had one more question. Oh, this is related to like it's a follow-up question with RP sir actually regarding the Bell values. Can you just go to that slide where you write the Bell values, Bell violation value?
Sorry. Okay.
Yeah. It just seems that your Bell values like it's quite strange because both psi minus and phi minus have higher values, but both the plus ones have again lower values. So
yes, because for generating phi minus phi plus, I have used one half-wave plate. So one point is that might be I have not used the exact angle of hover plate, and second thing, these two state I have generated at the two different time. So I have aligned all the setup again. So that is the second case. If at the same time I have generated all the four bell state, then there was a possibility that all the bell inequality comes equal.
No, I was asking a separate thing actually. See, psi minus and phi minus both have similar values, and again psi plus and phi plus have similar values.
Yes, they should have similar values because I am transforming my psi minus state into the phi minus state.
Oh, okay, fine.
And psi plus state into the phi plus state.
Okay.
Yes.
Thank you.
Yeah. Okay. Thank you, Sarika. With this talk, we conclude this session. I want to thank all our speakers for their time and participation. I thank everyone in the audience for being present here and asking wonderful questions. We will now have a short break till 4:45, and next session will start at 4:45, and whose chair will be Tanya Sharma. Over to you, Tanya. Thank you.
Hello and welcome to the third session of today in the Virtual Scope 2020 conference. I am your session chair, Tanya Sharma, and this session is titled Fiber, Lasers and Ultra-Fast Processors. A few reminders before we start the session. The panelists can either play their pre-recorded presentation or share their live screen using the Share Screen button on the bottom right of the window. I request all the presenters to strictly adhere to the clock. The audience can use the Q&A widget to type your questions, as many of which would be answered at the end of the session. You can use the chat widget to communicate with other attendees and to comment on the presentation. Now let's start today's session, Fiber, Lasers and Ultra-Fast Processors. Firstly, we have Dr. Apurv Chaitanya. He did his PhD at Physical Research Laboratory, Ahmedabad. He is now a researcher at School of Engineering and Sciences, Tecnológico de Monterrey. His research areas include multi-particle quantum plasmonics, generation of vortex beams, to name a few. Without further delay, I welcome Dr. Chaitanya to the spotlight to share his screen for his talk on lattice plasmon mode assisted planar chiral circular conversion dichroism. Over to you, sir.
Yes. Can you hear me?
Yes, we can.
Okay. Thanks for the introduction. I am Apurv. I'm right now in Tecnológico de Monterrey. I'm an assistant professor there. This project is in collaboration with Tecnológico de Monterrey, Max Planck Center for Extreme and Quantum Photonics, University of Ottawa. So this is where the particle was fabricated. The metasurface was fabricated here. The experiments are being done at Max Planck Center, Max Planck Institute for Science of Light, Erlangen, Germany. So this is the outline of the talk. I'll be giving a brief introduction of what chirality is, types of chirality, how to detect chirality. Then we'll be moving to the topic of today's talk, that is circular conversion dichroism, CCD, in metasurfaces. Then I'll be coming to what is the motivation, results, discussions, and conclusions. So chirality usually refers to the intrinsic sense of handedness of a three-dimensional structure. So chirality is derived from the Greek word chir, which means hands. So hand, as we know, has a mirror form. Our left hand is the mirror form of our right hand, and the mirror images are not superimposable. That's why we say that it is chiral. So the mirror image is called enantiomer. So left hand is the enantiomer of the right hand, and right hand is the enantiomer of the left hand. So it's not only a hand which is chiral. We have many chemical molecules which have mirror symmetric forms, and we also find this in nature. So there are snails also which exist in right and left-handedness, and even our ears have intrinsic handedness to it with it. So one is mirror symmetric with respect to other. So then let's quickly go into what are the broad classification of chirality. So chirality can be broadly classified as 2D chirality and 3D chirality. So here the structure can be considered as 2D structure because the thickness is really small. So the thickness is very small compared to the wavelength of light. Because of that, we consider this as a 2D structure, and this is a helix. So helix, it has a depth also, it has a thickness, so it is a 3D structure. So the difference between these two is that you see that this is a counterclockwise rotating helix, and this is a copy of that. Similarly, this is a copy of this structure. So this structure is called a gamedia. So this is a anti-clockwise rotating helix. So let's say that it is a left-handed helix. So this is also a left-handed helix. Similarly, let's call this as a left-handed gamedia. So now what happens is that when you look from the other side, so now I'm flipping the sides. When we look from the other side, this gamedia, this helix, which was a left-handed helix, remained a left-handed helix, even though when we rotate it, when we look from the other side, it remained the same handedness. But in case of gamedia, the left-handed gamedia became a right-handed gamedia. So that is the difference between 2D chirality and 3D chirality. So the 3D chiral structure, which is the helix, has a intrinsic sense of handedness. So if it is a left-handed helix, it remains a left-handed helix irrespective of where you look at it from. You look at from this side or this side, irrespective of where you look at it from, it has a inherent handedness and it never changes. But in case of a 2D structure, it depends on where you look at it from. So it doesn't have an inherent handedness. So if you look at from here, it has one handedness. If you look from the opposite side, its handedness flips. So because of this property, the 2D surfaces, 2D particles are not truly chiral because it doesn't have an intrinsic chirality. So what we call is it has a pseudo chirality. It is pseudo chiral. So we can in 2D structures, once we put a substrate like this, we break the symmetry along the z-axis. So you come from air, you have the structure, and then you have substrate. Because of which you break this symmetry. Now this structure can be considered as a 3D structure, and it can have some kind of chirality. But that is not the topic of our talk today. So now let's also see what is other types of classification, that is intrinsic chirality and extrinsic chirality. So again, let's look at a helix. So this, if we say it is a left-handed helix, and if we consider a mirror plane like this, in the other side you have a right-handed helix. So irrespective of where you have this mirror plane, it always flips sign. It is always non-superimposable. So this is not superimposable on this left-handed, on its original structure. The mirror image is not superimposable. But look at this case. So you have a structure like this, and if you consider a mirror plane like this, now this is the mirror image of this, but they are both identical. So they are both superimposable and they are not chiral now. But if you lift the structure with respect to the mirror plane like this, then you make it chiral. Now this is a mirror image and it is not superimposable. So this kind of chirality, which arises because of the geometry between the plane and the observer, between the mirror plane, the observer, and the structure in question, this kind of chirality is what is called extrinsic chirality, because it is not inherently chiral. It is chiral due to some kind of manipulation from our side. Now the question is, why do we even care about chirality? So in nature, both forms of enantiomeric forms are found in varying proportion. So the problem is that they all do not have the same kind of properties that we are looking for. The classic example is thalliumide tragedy. So this molecule, this chemical structure called thalliumide was administered to pregnant ladies who were having morning sickness. But the problem was that one of them had the desired effect, and the enantiomeric form, which is the mirror symmetric form of this thalliumide, had adverse effect on the pregnant lady. So in fact, it led to the children born out of the lady who had the enantiomeric form have limbs which are not fully grown. So this is the reason why quantitative and quantitative understanding, estimation of chirality is really, really important, because it has adverse effect as well. Now the question is how to detect chirality. So of course, if it is big structure like snail or hand, we can just look at it and understand that which is right and which is left, which is the chiral form we can clearly understand. If it is very small, we can of course use microscopy. But we can also use another technique, because we know that circularly polarized light has handedness. So it exists in right circular polarization and left circular polarization. So this RCP and LCP, which is right circular polarization and left circular polarization, they respond differently for RCP. They respond differently for a chiral structure. So these effects are called what is called chirooptical effects. So if you have a right hand, if you shine RCP, and if you have left hand, if you shine RCP, the transmission, the scattering properties will be different. This is just as an example. Okay, so now let's come back to the thing which we are looking for. So remember, this is a 2D structure, gamedia, and once you look it from the other side, the handedness get flipped. So it is also, it can be also assumed that once you shine RCP through this gamedia, you get some transmission, and once you shine it from the opposite side, you get some other transmission, because once you look from the other side, you're seeing the handedness as flipped. And this is called asymmetric transmission. So this is also a chiroptical property. This is called asymmetric transmission, which is the difference in transmission when you come from the either side of the structure. And this can also be seen like this. So if you have a gamedia, and if you come with RCP, you have some transmission, and the same gamedia from the same side, if you come with LCP, it has some other transmission. So this can also be can be an indicator of asymmetric transmission by not coming from opposite side, but coming from same side itself, but coming with different polarization. Both has same effect. So this thing, we should note that it is exclusive to 2D structures, because if you have a helix, if you come from this side or this side, it will have same kind of properties for RCP, right circularly polarized light. So asymmetric transmission is exclusive for 2D structures. So now, by now, we are convinced that asymmetric transmission implies that it is 2D chiral. So only 2D chiral structures can give asymmetric transmission. So the conventional wisdom is that 2D metasurfaces which are chiral can give asymmetric transmission. So if you consider a metasurface with gamedia, so right till now we were talking about just one of them. If you make a lattice like this, a periodic arrangement like this, then what we have observed is that if you shine RCP, it has a transmission. If you shine LCP, it has some other different transmission. So the difference in two has been plotted here. So this is what is called asymmetric transmission. So we see a clear signature of asymmetric transmission. So the thing to notice here is that, so all these wavelengths, there is no asymmetric transmission. It's all zero. Asymmetric transmission is zero. And for these wavelengths, beyond some particular range, you have asymmetric transmission. So another thing we did is that we rotated the individual gamedia with respect to its axis with an angle theta. And that is plotted along the y-axis, and what is plotted along the x-axis is the wavelength. And what is plotted in color scale is the difference between transmission of L, which is transmission with LCP input and RCP input. You see that for some particular wavelength, for particular rotation, so let's see this 20 degree. At this 20 degree, the asymmetric transmission is zero at this wavelength, and along this line you see that the asymmetric transmission is mysteriously zero also along this line. So even though this is a chiral structure, it means that by rotating some arbitrary degree, what we can achieve is that we can make asymmetric transmission zero. So this is kind of interesting, because our conventional wisdom is that a 2D metasurface which is chiral has to give asymmetric transmission, but it is not giving at some particular wavelength. So this is what puzzle does. So our motivation is it a 2D chirality is a sufficient condition? Of course it is not. You see that it is 2D chiral, but still it is not giving asymmetric transmission. So we wanted to investigate it further. So what we did is we started with the simpler structure, which is the assembly of 4 nano antennas, which has a dimension of 100 nanometers, and the width is around 20 nanometers, and the thickness is around 20 nanometers. And we arrange it over a periodic lattice like this. Then we try to measure the transmission. Now we see that LCP and RCP transmission exactly fall on top of each other, making the asymmetric transmission exactly zero. So this was expected, because you see the structure itself is achiral. Once you place it in a lattice, then nothing is going to change, right? Now we rotated it along 45 degree. Each individual structure we rotated at an angle of 45 degree, and again, not to our surprise, we saw that it is asymmetric transmission is zero. This was also quite expected. But to our surprise, when we rotated it at 22.5 degree, then we saw that this is again plotted the transmission of RCP and LCP, and you see that there is huge asymmetric transmission at certain particular wavelength, and similar that of the case of gamedia, you don't have any asymmetric transmission for all this longer wavelength. So this is what puzzled us, and we wanted to investigate this further. And the questions were what we wanted to answer is that why is it absent in all this wavelengths, and why it is very strong in some particular wavelengths. Okay, so this is again the two cases where this and this both are giving asymmetric transmission. So this is achiral, this is chiral. Even though this is achiral, when it is just rotated at 22.5 degree, you have very strong asymmetric signal, asymmetric transmission signal. Okay, so the thing we should again emphasize is that there is no asymmetric transmission here, and there is huge asymmetric transmission at this 2 wavelength. To understand this, we did a study of input angle versus wavelength. So we change the input angle like this, and that is what is plotted here, input angle versus wavelength. And what is plotted in the color scale is the transmission for RCP and LCP. And you see that in these regions, it is all same. There is no much change for RCP and LCP in all this region. Where the huge change happens is along these lines. A defect kind of structure arises, and along these lines is where we get very high asymmetric transmission. And that these lines actually corresponds to this in one of the graphs. So this graph is for at incident angle 0 degrees. So it is a line. It is a line section of this plot. So we note that these are the regions where asymmetric transmission is huge. So if we look at more carefully, we understood that these lines are actually what is called the Rayleigh anomaly. So once you have a periodic arrangement of plasmonic structures, so these plasmonic structures, they don't scatter individually. The scattering is coupled with each other, and they have a hybrid coupling mode. So this happens near the Rayleigh anomaly conditions. So this that are the conditions where we get very high asymmetric transmissions. So it depends on the periodicity of the lattice. So depending on the periodicity, you can shift these peaks. That's what we have seen. Now this defect, so this actually corresponds to 1-0 mode, which is a, so as I said, they couple the plasmonic structure. Once put it in a lattice, they have a lattice mode which is propagating along the surface. So this mode actually corresponds to a mode which is propagating along this direction, and these two lines actually corresponds to a mode which is propagating diagonally like this. Now we understand that once you rotate the structure,
sorry to interrupt you. You have 2 minutes left.
Okay. So now we see that it is along this direction. As we go along this direction, when it is rotated at 22.5 degree, the structure sees it differently. If you go like this and if you go like this, there is a difference, right? So when once you shine with RCP light, it has some mode propagating, and once you shine with LCP light, it has some other mode propagating along this direction. So this difference in modes actually results. These modes have different losses, and these different losses results in asymmetric transmission for RCP and LCP. Okay, so I would stop here. So, okay, let me go to the conclusion slide. Okay, so we have found that a structure like this does not give asymmetric transmission at 1-0 order, but once you rotate it, it exhibits asymmetric transmission at 1-0 order, also at 1-1 order. So the thing to note is that these structures are achiral. The individual structures are achiral, but still it shows asymmetric transmission once you make the structure, once you make the lattice itself chiral. Yes, thank you.
So Apurva, nice talk. After a long time, I could hear you online only, but it was good to see you and listen. So just wanted to know what is this Rayleigh anomaly and how it is affecting this asymmetry.
So yeah, we can understand it like once you have a periodic arrangement of any structure, it will support grating orders, isn't it? So the Rayleigh anomaly happens at the grating orders, at the wavelength at which the grating orders occurs. So let's say that when the wavelength is very, very high compared
Rayleigh
to the
scattering, it has Apurva, it is related with some Rayleigh scattering, like when wavelength is less than the, like particle size is very less than the wavelength or something. Some size has to do with that, like grating order or grating size.
Yeah, grating order, yes. So it is the grating order. When the grating order is comparable to the wavelength, then it supports grating orders, right? So at the grating orders, at the wavelength at which the grating orders is supported, at that wavelength, we have what is called Rayleigh anomaly conditions. It is the diffraction edges. So this is the condition.
Okay.
this is the condition where we have this Rayleigh anomaly.
Okay, this condition.
Yes.
Okay.
So it depends on the index of the so we have this periodic arrangement of structures, right? So there is an index in which this medium is submerged. So it is a product of index times the periodicity. So if n is the index, n times the periodicity is the Rayleigh anomaly condition.
Okay.
Yes.
And it has to do with
Chaitanya.
wavelength of light. Okay.
Yes. Yes.
Okay. Thank you, Dr. Chaitanya. Now, if anyone wants to ask any question, please raise your hands or you can write them in the QA box. We have one question in the chat. Sandeep wanted to ask what is Rayleigh anomaly, so I think that has been answered. Next question is, does it depend on crystal class? So I'm going to ask this question. Does it depend on crystal class?
I'm not sure what is meant by crystal class, but it depends on the chirality of the lattice. So if the individual structure, the 2D lattice as a whole, if it has a chiral nature, and it has to support the surface lattice modes. So that is why we didn't see for the higher wavelength. So for the higher wavelength, the wavelength is bigger than the periodicity. So when the wavelength is very big, we don't support the lattice modes. So you have to support lattice modes for this kind of chirality, chirooptical phenomena to occur.
Well, I have one question. In the concluding slide, you said that though it is not chiral, but like in the concluding slide.
Yes.
Yeah. So I can see that it is extrinsically chiral, like as you mentioned that if we would rotate it, then it will become chiral. Because the mirror image would not overlap with
yeah, but remember, this is not truly chiral structure. So this is a 2D structure. So 2D structure, you are not making the geometry. You are looking still from the normal incidence. Remember, in the other case, you had to lift it out of the plane to make it extrinsically chiral, right? Now we are not doing anything like that. We are still in the same geometry as before, but you just rotated the individual structures with respect to itself. Okay, so this is a 2D, completely 2D.
Even if it is 2D, like you took a ring kind of a thing, cut into half. Even if it is like a circle, like a 2D semi-circle, and if you would lift it to some angle, and then you will take the mirror image.
Yeah. So that is extrinsic chirality. So again, let me tell that. So if this is the U-shaped structure that we were talking about, even if you rotate it at any degree, it will not make it chiral. So what you require is you have to lift it out of the plane with respect to the observer. So that we are not doing here. So here we are just rotating it with respect to its axis. We are not lifting it out of the plane. We are not making it a 3D structure. By lifting it out of the plane, you are making it as a 3D structure, right? So 3D structure, of course, can have some kind of chirality. Here it is still a 2D structure itself. You are not lifting it up. You are not exposing the depth of the material to the light. You're just rotating it with respect to its axis. So this is the difference between. Yeah.
Hello, Chaitanya. Nice talk.
Thank you.
Yeah, I just wanted to ask that the crystal classes, does it depend on the crystal? I mean, the anomaly, does it depend on the crystal classes? I mean, the various crystal class, does it? I mean, the anomaly, it varies on different crystal classes or not? I mean, if it is BCC or FCC like structure, or it is triclinic monoclinic structure, does it depend on this or not?
Yeah. So yeah, it depends on the refractive index and the periodicity. So if you have some periodic arrangement of something and that periodicity matters, also the refractive index in which the periodicity, the structure has been immersed. That is what I said. So if it has a refractive index n and the periodicity is p, so p times n is one of the conditions for Rayleigh anomaly and all the multiples of that.
But in different crystal classes, periodicity is obviously there, but the packing is different.
Yeah.
Right.
So
that's why I asked this question, because periodicity, suppose you have the similar kind of periodicity. I mean, periodicity is there, but still you have different packing fraction. Then does it affect that
Yeah,
anomaly?
it will affect because it's not only so let me go back there quickly. I don't know. Yeah. So here you see this theta is also there, right? So theta is the incident angle. Okay. So depending on not only on the periodic structure, depending on all the as you said BCC, FCC, depending on the structure also it will have different theta values also. So here I have considered a linear arrangement, a 2D structure, but if you consider a 3D structure, I think this expression has to be modified. But we can say that it also depends on the crystal structure. Yes.
Okay.
We have one more question from Shubhit. He says, what about the other angles? And there is a follow-up question that says, is AT observable in other angle of structure orientation?
Yes. So we talked about 22.5 because that was the region where we had highest asymmetric transmission. Yeah. So that's a good question. I actually didn't show those results. So yeah. Okay, I can tell like this. CD doesn't happen only when theta is, so this theta is 0 and 45. For all other angles, we can see asymmetric transmission. So, and it is maximum highest at 22.5, right? So if it is 0, that is when it is not rotated, it is not, the structure as a whole is not chiral. And when it is rotated at 45, again, it is not chiral, right? So all the 0, 45, 90, all this multiple. So it is a 4-fold symmetric structure. So it has 4 times of rotation in all those angles. It will not show asymmetric transmission, and all other angles in between these angles, it will show huge asymmetric transmission, and maximum is shown at 22.5.
Okay, Apurv, I have a follow-up question. So this 22.5 is approximately 90 half of 45 or 90 by 4. So you have 4 antennas here in each of your crystal lattice. I mean, each of your lattice. So if you increase that into a pentagonal kind of structure, so this 22.5 can, is there any variation? Will be that kind of correlation can I expect?
Yeah, you can expect it. It is a function of the symmetry of the structure. You see, this is a gamedia. It doesn't have a, so here, it's not like even for 0 degree. So even when it is not rotated, remember, even when it is not rotated, it has a, so it is not rotated. Even then it has a asymmetric transmission, right? So it depends on the crystals, not just crystal, the individual structures chiral property. Did I answer your question? So it depends on the symmetry of the individual structure itself. So again, remember, even though the structure is chiral, at some angles you don't have any asymmetric transmission, right? So it depends on the individual structure and the chirality of the whole lattice as a whole. So even though the structure is chiral, you can arrange it such that the whole lattice behaves as if it is achiral. That's what this graph shows. At this regions, the asymmetric transmission is.
I would like to interrupt you. Actually, we are quite ahead of time.
Okay.
So I hope you have satisfied Subit, and I would like to thank you for this interesting talk.
Thank you.
Okay, so we now have Dr. Adhi Abdul Rahim. He did his PhD in Physical Research Laboratory in Ahmedabad and is currently working as a postdoctoral fellow in the Nonlinear Photonics group in INRS CMT. His current research mainly focuses on the demonstrations of mode-locked lasers and frequency comms using on-chip integration photonic platforms. So I welcome Dr. Adhi to the spotlight to share his screen for his talk on mode-locked lasers based on integrated on nonlinear device. Over to you, Adhi.
I'm audible? I'm audible?
Yes, you're audible.
Thanks to the organizing committee, Gautam sir and also RP sir. So my name is A. Adhi. I'm a postdoctoral research fellow in the group of Professor Roberto Morandoti at INRS EMT, Canada. So today I'm going to talk about mode-locked lasers based on an integrated nonlinear waveguide. In this talk, I will discuss the basics of mode locking. Then I will discuss one interesting mode locking scheme, that is the nonlinear amplifying loop mirror laser configuration. Then I will show the generation of a different mode-locked pulse profile from the nonlinear amplifying loop mirror laser configuration. It is the passive mode locking scheme. Also, I will discuss some of the theoretical simulations, and I will end up with my conclusion. So before going to that, let's see what is the difference between the continuous wave and the pulses of light. So if you see the continuous laser or a CW beam, if you see its irradiance over time, so this will be having a constant irradiance over time. But if you see in the spectral domain, that is the Fourier transformation of the its time domain, so it will have a narrow spectral profile. On the other hand, if you see the long pulse, it will have the bandwidth that is called the pulse width. But if you see it in the spectral domain, it will have also a spectral bandwidth, which is order of a few gigahertz to a few terahertz. Similarly, if you see the short pulse, which is highly localized in time, such as the few femtosecond or attosecond pulse, then if you see the frequency domain, then that's why its spectrum will be very broader. So then how we will achieve the mode locked pulses? How we achieve the pulsed laser. So achieving the mechanism for achieving the pulsed laser is called the mode locking mechanism. So for let's see how we can achieve the mode locking pulse. We can see a simple laser configuration, which is by the plane cavity plane mirrors, that is referred as the resonators, and a gain medium with an appropriate pumping scheme. So this laser cavity, this resonator will have the cavity modes, which are the possible standing wave inside the laser cavities. So the below figure shows the gain bandwidth of the laser, and the arrows are the laser cavity modes excited by this laser gain bandwidth. So if the gain bandwidth is very broader, then it induces multiple cavity modes. So we have seen if the gain bandwidth of the laser is broader, then it can induce multiple cavity modes. But all these modes are generated independently by the stimulated emission via the means through the initiated by the spontaneous emission. So all these modes are not necessarily will be in phase, or the modes will be randomly distributed in phase. So as a result, if you see its irradiance or intensity in time, so the average power will be constant over a time, and it will be having a fluctuation around the in the instantaneous value. On the other hand, if you see the if the cavity modes are in phase, then at that instant, then it will rise in its intensity, and it will enable a pulsed laser. So this is called the mode locking, because all the mode are trying to match in phase at certain instant. And basically, the mode locking redistributes energy into its coherent sideband. And there are two mechanisms. One can lock the cavity modes. One is via the active mode locking by introducing the any modulator like acousto-optic modulator or electro-optical modulator inside the laser cavity that will switch the laser state on-off state, and it will enable the mode locking or the synchronized pumping scheme. In the passive mode locking scheme, one can use the saturable observer inside the laser cavity, or one can use the optical Kerr nonlinear effect to induce the passive mode locking scheme. So compared with the active mode locking scheme, passive mode locking scheme are widely used. It can generate a very short and fast optical pulse train, which are also very quite stable. Okay, so in this talk, I will discuss only the passive mode locking scheme. So there are several compact laser architecture have been developed to passively lock the cavity modes. These passive mode lock lasers find interesting important application in various fields of science and technology. It is widely used in like optical communication, optical sensing, and micromeasuring, and so on. The key element to achieve the passive mode locking is the saturable observer. So therefore, various material have been developed, studied to achieve the saturable observer. to have a wavelength independent, to have a high modulation depth, and to have a low saturation threshold. And till now, there various material have been proposed or method have been proposed to achieve the passive mode locking, and few of them are shown here using topological insulating material, using carbon nanotube saturable absorber, using graphene-based passive mode locking scheme. And also, this is the another scheme which uses the Kerr nonlinearity from the microring resonator, which also enable the short optical pulse by the passive mode locking. Interestingly, there is another configuration which passively lock the cavity modes without requirement of keeping any saturable absorber inside the cavity. That is the nonlinear amplifying loop mirror laser configuration. This is shown here. Let's see how this nonlinear amplifying loop mirror laser configuration works. So this nonlinear amplifying loop mirror laser is a norm laser, has a two stage. One is the amplifying stage, which consists of an amplifier and an isolator. It is a unidirectional loop. And another is the nonlinear amplifying loop mirror stage, which consists of amplifier and a nonlinear medium or nonlinear single mode fiber. It is the bidirectional circuit loop. So when the light propagate inside the clockwise direction, the light first amplified by the amplifier, then enter inside the nonlinear loop. On the other hand, so nonlinear medium. On the other hand, the counterclockwise beam first enter inside the nonlinear medium, then it enter inside the it gets amplified by the amplifier. So this nonlinear medium induce an intensity dependent nonlinear phase via the third order nonlinearity or the Kerr effect. So as a result, when it recombine at the beam splitter, so it actually make an intensity dependent power splitting. So this mimic the behavior of the saturable absorber, because the saturable absorber also will have the intensity dependent transmission function, transformation function. Okay. So so using this nonlinear amplifying loop mirror laser as quite give good advantages because it can generate pulsed laser from femtosecond to nanosecond in a stable and robust optical pulse time. It is it will be a high efficiency. It provide a high efficiency in a compact architecture. Okay, so there are different optical pulse profiles which are suitable for different applications. For an example, if you have the Gaussian pulses, these are essential for laser micromachining. And if you have harmonic pulses, this is used for optical communication and optical clocking. Similarly, if you have square wave pulses, this can be used for high-speed signal processing, optical switching, and chaotic pulses are used in a random number generator and secure communication. So interestingly, if you see the norm laser configuration, this also can enable different mode locked pulse profiles in the architecture by replacing with the appropriate nonlinear element as well as engineering the laser cavity. For an example, if you see here, the microring resonator based norm structure can generate transform limited Gaussian pulse. And if we replace with a highly nonlinear single mode fiber, then it can generate higher harmonic pulses. Similarly, if we engineer the dispersion of the cavity, then one can generate rectangular pulses. However, generating a versatile range of optical pulses from a single norm laser configuration required precise control over various parameters, such as we need to control the gain, loss, and we need to engineer the nonlinearity as well as the dispersion of the laser cavity. So the generating a versatile range of optical pulses from a single setup is highly challenging. So here, our motivation is to generate different mode locked pulse profiles from one setup. So this is the experimental setup. This is the norm laser configuration. So we used appropriated element to achieve the our motivation. So here we use SOA. SOA is the semiconductor optical amplifier in the nonlinear amplifying loop mirror stage. And in the amplifying stage, we use erbium doped fiber amplifier. So this amplifier used to compensate the loss induced by the cavity. So we use a highly nonlinear spiral waveguide as the nonlinear element inside the nonlinear amplifying loop mirror stage. So this is the schematic of the spiral waveguide, and this is the cross-sectional SEM image of the spiral waveguide. The spiral waveguide has the 45 centimeter long, and which has the cross-sectional area of 1.45 into 1.5 micrometer squared with a high nonlinearity. So this spiral waveguide induce a large nonlinear phase shift via the third order nonlinearity or the Kerr nonlinearity over the short propagation length. This norm laser, now it has a wide range of dynamics from a single setup. So we operated the laser initially at the chaotic region, and this is the RF spectrum observed from the chaotic region. So which suggests that the cavity has the length of around 30 meters. The laser shows different dynamic region, and the dynamic region can be controlled by dynamical states can be controlled by two way. One is by controlling the gain parameter via the SOA current, and another one is via the tuning parameter via the phase by the polarization controller or the effective nonlinearity. So in order to understand the different dynamical state generated from the norm laser configuration, we have developed a delayed differential equation tailored to the figure-8 laser configuration. So this is the system model governing the delayed differential equation for the norm laser, and where G is the cumulative saturation gain, which is normalized, and kappa is the total amplitude attenuation, and chi is the linear phase attenuation, and where phi is the phase shift induced by the spiral waveguide, that is the nonlinear element inside the nonlinear amplifying loop mirror stage. So we use SOA gain as the tuning parameter or the control parameter. Then we actually plotted the bifurcation diagram. Bifurcation diagram gives the solution at a different SOA gain parameter from the delayed differential equation. So which shows that the norm laser actually has a different dynamical region. We can see here, one can see mode locked lasers and chaotic region and fast oscillation, square wave pulse and modulated square wave pulse, where the fast oscillation is nothing but the sinusoidal like pulses and quasi-periodic pulses, and many dynamical state it can show by varying the SOA gain. In addition, this bifurcation diagram also shows a kind of hysteresis behavior with its dynamical states with forward and backward swipe. It means if we swipe the gain parameter from one direction, and we will not get the same dynamical state if you go with the backward direction, which mainly arises because of the generated the state also depends upon the initial condition. So the initial what region it is operating. So in order to okay, so this is the temporal profile from the different dynamical region, which shown in the bifurcation diagram. So we can see the temporal pulse profile. If you plot over a time period, it shows the intensity. It varies a mode locked pulse. So over the gain, it shows a different pulse profile, such as a mode locked pulse, higher harmonic pulse, square wave pulse, and fast oscillation. This is kind of sinusoidal like pulse, and so on. So if we slowly increase the SOA gain, so one can switch different dynamical pulse profile from single setup. So this is what our simulation shows for the nonlinear spiral waveguide embedded norm laser. So this is the experimental result. So by slowly varying the increasing the SOA gain, we initially reach the mode locked region. Then further by slowly increasing the modulating the cavity parameter, such as the tuning parameter via the the effective nonlinearity of the cavity by the polarization controller or the SOA gain. So one can attain various pulse profile. So we can see here by the tuning parameter, we observe mode locked pulse and harmonic pulse, square wave pulse, as well as the sinusoidal like pulse. In addition, different pulse. So here I have shown only a limited pulse, but it can generate multiple pulses like a chaotic and quasi-periodic, as well as the stepwise function, and many pulses, many region it can show. Yeah. So among all, the square among all the generated square wave pulse are very interesting. The square wave pulse, basically the origin of the square wave pulse explained by can be explained by two mechanisms. One is the dissipative soliton resonance, and another one is the nonlinear polarization rotation. So in order
Sorry to interrupt you, Dr. Adhi. You have 4 minutes left.
Yeah. Okay. So in order to identify the origin of the square wave pulse, we have recorded the optical spectrum, autocorrelation, and aura spectrum. So let's see what mechanism is related to the origin of the square wave pulse. If the square wave pulse is generated from the dissipative soliton resonance, then it shows a Kelly sideband in its optical spectrum. However, if you see the mode-locked pulse or square wave pulse or the fast oscillation, so we will not. It doesn't show any Kelly sideband. It means the generated square wave pulse or any mode-locked pulse is not related to the dissipative soliton effect. Similarly, if the square wave pulse is originated from the nonlinear polarization rotation, then the originated square wave will be the group of very short pulses, which is order of the femtosecond. So if you see it in the autocorrelation trace, then it shows a very short spike in the autocorrelation trace. However, if you see the autocorrelation trace, the square wave doesn't show any spike, which means that the generated square wave also not belongs to the nonlinear polarization rotation. So from this, we can conclude two measurement. We can conclude that the origin of the square wave pulse neither belongs to the dissipative soliton resonance or the nonlinear polarization rotation. So this is the aura spectrum. This aura spectrum indicates that the generated mode-locked pulse profiles are very stable, and it has the low time. It has the timing jittering of order of picosecond and small noise figure. So in order to identify the origin of the square wave pulse, so then we work it on the our theoretical model. So this shows that our theoretical model also explain very well on the origin of the square wave pulse. So we can see that this figure shows the amplitude response of the norm with the as a function of intensity with the different SOA gain parameter. So the green corresponds to the SOA gain parameter 1.5, and black is the 2.5, and blue is the 3. So the gain parameters are normalized values. And if you see the right hand side, so the right hand side figure map the intensity between the n+1 cavity round trip and the nth round trip cavity intensity. And where this solid line is the amplitude response of the norm laser for the corresponding gain parameter, SOA gain parameter of around 3, and where this gray line is the line where the intensity of n+1 cavity round trip equal to the intensity of nth round trip. So this figure indicates that there is an amplitude fluctuation between there is a fluctuation between two intensity values, that is the 0.5 and 1. So there is a periodic switching between two intensity values, which means that this periodic switching arises mainly due to the instability. So in our case, this instability is called a Ricardian instability. So that comes from our theoretical model, hold the same similar response of the Ricardian instability. So, and if you see the generator square wave pulse, this square wave pulse will have the periodic 2 pulses. The periodicity will be twice the cavity round trip. And also the duty cycle of the generator square wave pulse will be the 50% duty cycle. Unlike in other cases.
Time is over. Can you wrap up quickly?
Yeah, the next, it's end. Yeah. So the square wave pulse also will have the 50% duty cycle. Unlike the previous cases like dissipative soliton resonance or the nonlinear polarization rotation, the duty cycle will varies. So if you see our experimental square wave pulse, this also will have the harmonics of periodicity 2, as well as the 50% duty cycle. So in conclusion, we have demonstrated a passively mode lock laser based on a nonlinear amplifying loop mirror laser stage, loop mirror laser. It enable different mode locked pulse profiles. One can call it is a kind of optical waveform generator. And we have also developed a theoretical model based on a delayed differential equation, which also explain our experimental observation. And this paper, this work can be found in this paper. It's a highly reconfigurable hybrid laser based on integrated nonlinear waveguide in Optics Express. And thanks for your attention.
Thank you, Dr. Adhi, for a nice talk. And if there are any questions, I would request you to answer them in your chat. And yeah, okay. So now I would like to play the recorded video for Professor Frank Weiss. He received a BS in Engineering Physics from Princeton University and MS in Engineering in Electrical Engineering from the University of California at Berkeley, and the PhD in Applied Physics from Cornell University. Before PhD, he worked on advanced integrated circuits at Bell Laboratory. Since receiving the PhD in 1988, he has been on the faculty in Applied Physics at Cornell. His research areas include generation of vortex beams using plasmonic quadtrummer, nanoclusters, and fiber lasers that generate ultra-short light pulses. Without further ado, I would like to play the recorded video and
Excuse me,
Ms.
Sharma, can I interrupt you? I can give the talk live. I supplied the recording only as a backup, but it's up to you.
Okay. So without any further ado, I welcome Professor Frank Weiss to the spotlight to share his screen on the spatio-temporal mode locking in fiber optics. Up to you. Over to you.
All right, so first share my screen. And then I should do this, right? All right, good afternoon, everybody. It's a real pleasure to speak at your meeting. I particularly appreciate the opportunity to speak at student groups. I hope and trust that that means that students have been inspired or learned something from our papers. Of course, we'd all be happier if we could meet in person. As you can tell, I guess, I'm sitting in the basement of my home because even though the virus is under control here, we're still supposed to work from home if at all possible. And along those lines, of course, we're very concerned about the cases in India, and we hope that it gets under control soon. So the talk is on spatiotemporal mode locking and fiber lasers, and in a way, following on the talk by Professor Forbes, this continues a theme of controlling light in multiple dimensions. Here's what I have in mind for the next 40 minutes. I'll give a brief introduction to the elements of nonlinear wave propagation that are related to mode locking. I'll give what I should call a progress report on spatiotemporal mode locking. This is something that's only been done for a couple years, and I'll pass on the basic features of it, but we should be very clear, this is far from finished. So it'll be appropriate to talk about possible future directions, and there are many of them. I should give credit. This work was led by a terrific student, Logan Wright. Pavel Sidorenko and Hamid Purbayram did some of the measurements of 3D fields that I barely will talk about today. And Dimitri Christodoulides is a theoretical collaborator from CREO. Okay, so I'm going to take 5 minutes or so to do an introduction to nonlinear wave propagation. Obviously, some of you are experts in this. You can just take a nap or rest for a few minutes while I do this, and then we'll come back. We all learn in undergraduate electromagnetism that the index of refraction of a material depends on frequency. So the phase velocity of a wave depends on frequency. And as a consequence, if we launch a short pulse, which has a broad spectrum necessarily, it propagates in a dispersive medium, two things happen. One is the pulse broadens, which I think everybody knows, and the peak power decreases. But at the same time, the pulse picks up a frequency sweep simply because of the difference in phase velocities. So we call this a frequency sweep or a frequency chirp. And the chirp can be up or down. Here's what happens with anomalous dispersion, which is the case for wavelengths longer than 1300 nanometers in silica, which is the basis of optical fiber. We say intuitively that blue leads red, but we also find it useful to think in terms of the phase that the pulse accumulates. The frequency is the derivative of the phase, so the phase is the integral of the frequency. And for anomalous dispersion, the phase is an upside down version of the pulse. On the other hand, at normal dispersion for shorter wavelengths, we say red leads blue. And in that case, the phase is a copy of the shape of the pulse. So that's what happens in dispersive propagation in one dimension. What about nonlinearity? Every material has a cubic nonlinearity. The real part is N2, the nonlinear index of refraction. This is a small number, and it modifies the index of refraction that we're all used to by adding a term N2 times I. So what does that mean? If we have a pulse of light with this intensity profile, the index is a copy of the pulse. Of course, it's sitting on this large background, but we just look at the time varying part. The phase is proportional to the index, and the frequency is the derivative of the phase with respect to time. We take a minus sign because physicists like to do wave propagation as e to the negative I omega t. Well, this nonlinear propagation produces a frequency sweep or chirp, but now it's not monotonic. You see the frequency goes down or to the red, then up to the blue, and then back to zero. This is called self-phase modulation. The wave changes the index of refraction of the material and then feels the change that it induced. And this can happen because the effect is essentially instantaneous when it's caused by the bound electrons. And this is called the Kerr nonlinearity, or the bound electronic Kerr effect. Well, that's what happens when a wave propagates by itself, but a similar effect can be induced by a second wave. So if we have one pulse with intensity I1, that can change the properties of a medium, and then a second pulse, I2, can feel it. It will undergo the same frequency sweep. It will accumulate the same frequency sweep as a result, and this is called cross-phase modulation. Like self-phase modulation, it produces new frequencies, shifts to the red and shifts to the blue. And importantly for our purposes today, it couples different waves. These can be different polarizations, different modes, whatever, and they can be coupled by this process. The simplest equation that governs dispersive and nonlinear propagation is called the nonlinear Schrodinger equation. It's shown here. The way to understand this is it says that propagation, dA dz, depends on two effects. They both have an I, so they're both phase modulations. There's no gain or loss in the equation. This is the dispersion term. Beta 2 is the dispersion coefficient. And this obviously is a nonlinear term. It has an intensity times a field. Either dispersion or nonlinearity would cause a wave to decay ultimately. So when you put those together, of course, a wave will generally decay even faster. However, some interesting things can happen. If we have anomalous dispersion, then the phase through the pulse profile looks like this. Remember, it's an upside down version of the pulse. The nonlinear phase is always a copy of the pulse. So if we have the right shape and the right amplitude, this phase can perfectly cancel this phase. So there's no phase accumulation, and this is called soliton formation. If there's no phase accumulation, the pulse propagates completely in a steady state. The simplest pulse shape that does this is hyperbolic secant with amplitude A0, pulse duration tau p. And in fact, if you tell me the dispersion of the medium and the nonlinear coefficient of the medium, I can tell you the product of the amplitude and the pulse duration that will make a soliton solution. So in contrast to dispersive propagation, a soliton propagates without picking up any frequency sweep and without spreading out at all. So this is remarkable scientifically. And of course, this is a possible dream for telecom designers. So that's the case in passive fiber. The name isn't commonly used, but almost all of the practical mode lock lasers used today are based on soliton formation. The easiest one to understand would be an erbium doped fiber laser, as we heard in the previous talk. Erbium emits at 1550 nanometers. So the dispersion is anomalous. The fiber has anomalous dispersion and positive nonlinearity, so solitons can form in the passive fiber in this laser. Now, it's a laser, so it has gain and loss. So the soliton has to be perturbed on every round trip by the gain and loss, but it's still a soliton. The highest impact short pulse laser still is the titanium sapphire laser. In its simplest version, it consists of a titanium sapphire crystal, prisms or chirped mirrors for dispersion control, and then mirrors. The prisms or chirped mirrors provide the anomalous dispersion. The self-focusing is in the gain medium. So you see here we can have solitons, but the ingredients aren't even all in one place. So the soliton is an average soliton of the whole cavity. Well, just as a pulse spreads in the time domain owing to dispersion, a beam spreads in the spatial domain owing to diffraction. Again, this is something we usually learn in undergraduate electricity and magnetism. The mathematics of these two situations are exactly the same. What about nonlinear propagation as far as the space domain goes? Well, we have an index. Again, it's the index that's ordinary, the usual index, plus a small number times the intensity. If the intensity is a function of position like this, as would be the case for a Gaussian beam, what happens? The index also is a function of position. And the way to think about this is the index is maximum at the center, minimum at the edges. So the induced phase modulation makes the medium act like a lens. And so a beam can cause itself to focus. This is referred to as nonlinear self-focusing. Well, just as nonlinearity and dispersion can compensate each other to make a temporal soliton, you might expect that nonlinear self-focusing and diffraction could compensate each other to make a spatial soliton. That would be a beam that propagates forever without spreading out, despite the presence of diffraction. Mathematically, that balance occurs at what's called the critical power, and the number for glass is about 5, for ordinary glass, is about 5 megawatts. So in principle, a 5 megawatt power beam would propagate perfectly stably by balancing diffraction and self-focusing. However, in 2 dimensions, that balance is completely unstable. And this is an interesting feature of nonlinear wave physics in general. Dimensionality, the effects of dimensionality are qualitative, not just quantitative. You can do this with a beam that's in 1 dimension, which would be in the form of an ellipse, a long ellipse, or a stripe. But in 2D, the wave either diffracts or collapses. Okay, so that's for 1D propagation and free space propagation, 3D. Let's talk about waveguides for a moment. We can make a single mode waveguide with an index profile that looks like this. It only supports a single transverse mode. What are the transverse modes? They're the solutions of Maxwell's equations for the dielectric boundary condition. Just think of an eigenmode that propagates without changing shape at all. We can make one that only supports a single mode. In terms of a ray picture, that's a ray that just propagates straight down the axis of the waveguide, or the fiber in this case. In general, if we make the core of a waveguide bigger, then the waveguide will support multiple modes. And I won't go through the mathematics, but I don't think you'll be surprised to see that the modes will look something like this. They'll have different shapes, all of which satisfy the dielectric boundary conditions. The ray picture can be useful here. Each of these ray paths corresponds to a different mode here. And you can see they have different lengths. And that's an easy way to understand how different modes have different velocities in a multi-mode waveguide. The index profile can be a step, or it can be continuous or graded. And today I'm only going to talk about graded index fiber. I won't talk about step index fiber after this. So why should we study propagation in multimode fiber now? It's not the newest topic. Interestingly, before about 7 years ago, there were literally about 5 publications on nonlinear wave propagation in multimode fiber, partly because the problem is complicated with all the different modes, partly because people devoted themselves to understanding wave propagation in single mode fiber. This has been an enormously profitable activity over the last 25 years. And of course, it led to the internet, which is how we're doing our meeting today. So there have been some tools developed to cut through some of the mathematical complexity of dealing with so many modes recently. So that helps us do the work. There's a field focused on the propagation of waves through disordered scattering media, etc., and how we can control those. That's referred to as the optics of complex media. And it has made some remarkable progress in the last few years. Of course, people are interested in making waveguide lasers or amplifiers for transmitting energy and also for high power lasers. And in telecom, all of our telecom now is based on single mode fiber, but the capacity of the systems is being reached. The only degree of freedom that hasn't been used yet is the spatial domain, spatial degree of freedom. So people are looking at whether we can put more information into multiple modes of a multimode fiber. You had a part of a day in your meeting on ultra-fast science, so I know you're aware of this. I want to point out that the field of ultra-fast science is almost entirely built on mode-lock lasers. At least 3 Nobel Prizes have been given for aspects of ultra-fast science and therefore building on mode-lock lasers. In the beginning, by the way, I was a graduate student in 1984 working on ultra-fast spectroscopy. That's how I started. And not long after that, Professor Zawale at Caltech used short pulse lasers to look at the transition states of chemical reactions, not just reactants and products, but what happens in between. And as an example, he showed that a diatomic molecule doesn't dissociate by just separating. The 2 atoms go like this as they go away. That's what's shown in these curves here. So qualitative new information after we'd studied chemistry for 100 years. Of course, another example is frequency combs. We can think of a short pulse train as a comb of frequencies in the frequency domain, which ideally are equally spaced, and a frequency comb completely controls the position in absolute frequency of each tooth on the comb, which is an exquisite degree of control on an electromagnetic field. How do we get mode locking to occur? This follows on the slides from the previous talk. We want to get constructive interference at one point in the cavity. By the way, each of these curves is a different longitudinal mode of the cavity. If they were drawn accurately, they would go to 0 to satisfy the boundary condition at the mirrors. So they have to have an integral number of half wavelengths between the 2 mirrors. If those are in phase, they interfere constructively. Away from that point, they interfere with some degree of destructive interference, and the result is a pulse that forms. And that propagates back and forth in the cavity. So that's a simple, now we haven't said how you do that, but that's what happens in mode locking. All of the lasers on Earth almost do this with a single transverse mode, which is what I show here. I want to introduce the concept of saturable absorption. This is a helpful thing and an important thing in mode locking in general. All we mean by this is some device or system that has increased transmittance with intensity of light incident on it. Imagine you have such a device, which I call SA here, and we have 2 pulses incident on it. The big pulse will be transmitted more than the small one, which you see here. And even further, the peak of the pulse is transmitted more than the wings, because it has higher intensity. So you can see that a saturable absorber promotes pulse formation by making a pulse sharper and sharper and suppressing small pulses and selecting big pulses. Now, a saturable absorber can be a material in one spot, but more commonly we use nonlinear polarization rotation, which we heard a little bit about in the previous talk, and it's actually distributed around the laser. There is no actual absorption, it's based on nonlinear interference. So why does mode locking happen? Imagine we have an amplitude spectrum, a bunch of sinusoids. In general, their phases are random, and we get a random wave train here. If we can bring those phases to the same value, we get a nice, clean, short pulse. Well, that short pulse will experience least loss through a saturable absorber. So a very simple way to think of mode locking is saturable absorption promotes the short pulse gets amplified, and that process is repeated until the pulse gets so short that the dispersion of the cavity matters. We really should say phase locking rather than mode locking. phase locking of the modes, which you see here. But for some reason, people started calling it mode locking a long time ago. Of course, laser cavities have many transverse modes in general. They don't just have a single mode. If you have many transverse modes, the resulting field is a superposition of those modes. And it can look somewhat symmetric like the one on the left here, or it can look like a speckle pattern. It all depends on the amplitudes and phases of the modes in the superposition. So we really should be thinking about 3D modes, which is a combination of transverse and longitudinal modes. For example, for this particular transverse mode, which I would call LP11, here are 3 different longitudinal modes that correspond to it. And of course, there's an infinite set. So the question we asked is, can we lock transverse and longitudinal modes together? And I should say phase lock. What's the challenge? Well, in the end, we want a comb of equally spaced frequencies, and we want their phases to be locked. So first, we need the frequencies equally spaced. Now, of course, that doesn't happen as soon as there's some dispersion in a cavity from material. So the resonance are shifted, and one way to think of mode locking is nonlinearity pulls those back onto the equally spaced teeth of the comb. If we have multiple transverse modes, there's a different comb for each mode. So if we have modal dispersion, different velocities for the different modes, plus chromatic dispersion, and you see we have many different resonances here, all of which have to be pulled back onto the equally spaced teeth of a comb to get mode locking. So this is a very disordered situation that we have to impose order on. So an analogy we sometimes use is this is like trying to make a high temperature gas form a crystal. Obviously, that's difficult. It can be insightful and intuitive to think in the time domain instead of the frequency domain. This is a numerical simulation of the propagation of these modes on the left. These are the 5 lowest cylindrically symmetric modes of a multi-mode waveguide. We launch these intensity profiles at low intensity, and you see 2 things happen. The pulse in each mode spreads out. That's the effect of chromatic dispersion. And the different modes separate from each other because they have different velocities. That's the modal dispersion. So that's what happens in linear propagation. Now, if we turn up the energy or the power in each mode, you'll see what happens. We can make the modes couple. So the same 5 transverse modes, now with equal energies in each mode, we launch those. And just as before, they start to spread out and separate from each other. But look what happens now. The lowest 3 and even part of the 4th mode get locked together, and they're no longer spreading out. So this is a soliton, but now it's a soliton with several modes. So we would call this group of pulses a multi-mode soliton. Why does it happen? They're coupled by nonlinearity, and you see the reason down here. The coupling shifts the frequencies, and if the frequency shifts, the group velocity shifts, and that's how they end up locked together in time. So that's multi-mode soliton formation. So a different way to ask the question is, can we build a laser and make multi-mode solitons form inside it? What do we need? Well, everything we needed to make a mode lock laser with 1 transverse mode or 1 transverse dimension, but now everything has to be 3D or spatiotemporal. We have to control the dispersion. We need nonlinear interactions, and I just introduced the 3D modes to you. And we need a saturable absorber, but it's now spatiotemporal. The work that I'm going to tell you about uses graded index multimode fiber. Ideally, the index profile in the core isn't just graded, it's a parabola. So this looks like a harmonic oscillator in quantum mechanics, but upside down. Here are what the modes of graded index fiber look like. Here are the lowest 5 cylindrically symmetric modes. Here are some of the low order modes that are not cylindrically symmetric. LP means linearly polarized modes. And of course, there can be many more modes than these. I just want to show you these. Again, I'm not going to derive them. I think the shapes of them won't surprise you too much. Here's why we want to use graded index fiber. if we look at the difference in group delay or group velocity between modes of a step index fiber, you see they're on the order of picoseconds per meter. That means that if we have pulses in two different modes, they separate by about a picosecond in a meter of propagation. If we look at graded index fiber, the group delay difference between the modes is much, much smaller. So that says two different modes almost stay together as they propagate. If they stay together, that allows them to have a stronger nonlinear interaction, which is what we want. So here's our approach in a simplified way to making a multi-mode or spatiotemporal mode locked laser. We choose the graded index, parabolic index fiber nominally, it's not actually parabolic, to make the dispersions comparable, the chromatic and modal dispersions comparable and not too big. And now I'm going to describe as if the pulse shaping is separate in the time domain and the space domain. Of course they're not, they're coupled by nonlinearity, but this was our thinking. In the time domain, we make pulses by working with normal group velocity dispersion. So solitons, ordinary solitons cannot form. How can we make a pulse? The answer is we make a cavity that supports a frequency swept or chirped pulse. If that comes to a filter, the filter cuts off the red and blue edges of the spectrum. But because the pulse is chirped, those are the beginning and ending tails in time. So you see that filtering a chirp pulse acts a little bit like a saturable absorber. It promotes the peak of the pulse and cuts off the wings. It makes the pulse shorter. That's a cartoon. It actually works. This is an animation that's accurate with realistic parameters on a laser designed to work on the basis of this. This is a fiber laser that consists of segments of single mode fiber at the beginning and end and gain fiber in the middle. It has a saturable absorber that also serves as an output coupler, and it has a filter. I'm going to show the animation of the pulse going around the cavity, which is indicated by the red dot here. The spectrogram of the pulse is shown on this diagram. The projection on the time domain is shown up here, and the projection on the frequency domain is shown here. We like the spectrogram because at a glance, if it's not vertical or horizontal, we see that there's a frequency sweep on the pulse. So it has information about the instantaneous frequency or the phase. So the pulse propagates through single mode fiber. The spectrum changes a little because there's already some nonlinear phase shift and the frequency sweep increases. It gets to the gain, and now you see the pulse is amplified quite a bit. The spectrum changes shape even more. At that point, the pulse energy is high, so when the pulse propagates through single mode fiber here, the spectrum changes shape further and even picks up what look like a cat's ears, or we call these Batman ears because they look like Batman's mask. It goes through the saturable absorber, which actually doesn't change it much, but then it goes through the filter. And as I said, the filter cuts off the edges in frequency, which are the edges in time, and now the pulse is ready to go around the cavity again. So that's an example of a converged solution of this laser. This is something we figured out how to do actually almost 15 years ago, and this is the way to make the highest power short pulse fiber lasers to date. What about the space domain? Well, we want to encourage multiple modes to oscillate. So here was our thinking. If we make a spatial filter, just an iris or an aperture, that's small compared to the fundamental mode of the cavity, the best way for light to get through is if it's in a superposition of higher order modes. Here's a superposition of these three modes. You see the central lobe is smaller than the fundamental mode. So a small aperture promotes multiple spatial modes to oscillate inside a laser. What couples the modes? Well, I just mentioned the spatial filtering. Disorder can couple the modes. It's not a major issue in this laser. I mentioned cross-phase modulation from the Kerr nonlinearity, spectral filtering, I just explained, and we have a saturable absorber to couple the modes. So how do you actually build such a laser? You get graded index fiber, or yes, graded index fiber that supports many modes, and you simply put a filter in the cavity and a spatial filter in the cavity. I'm going to tell you about results today with a fiber that supports 100 transverse spatial modes and of course 2 polarizations. Before we go in the lab to build something, we normally do numerical simulations. We can't simulate a laser with 100 modes. It's too computationally intensive. We can simulate one with 7 modes. So here are the lowest, some of the lowest 7 order modes of the fiber. What do we mean when we say simulate a laser? We put a noise field inside the cavity, a random noise field. And then we let it evolve according to the equations that govern propagation in each section of the cavity. Usually it does not converge, and it's a failed attempt. When it does converge, we record the laser parameters and the performance parameters, and we have a success and we try again. So here's an example of a converged solution. That noise field very quickly goes to this set of pulses. You see 1, 2, 3, maybe 4 modes are locked together in time. They have different temporal profiles, but they're locked together in time and propagating. Here are their corresponding power spectra. So this is a first theoretical suggestion that we can have multi-mode mode locking in a fiber laser with the conditions that we chose. Okay, in experiment, we build more or less what I showed you. We have a highly multi-mode gain fiber. It's not a parabolic index gradient, but it is graded. So the modal dispersion is not too big. We like to work in unidirectional ring cavities for reasons I won't tell you about. So we have an isolator, light just goes around in one direction. We put a spatial filter, a spectral filter, and then a spatial filter. And these quarter and half wave plates implement the saturable absorber based on nonlinear polarization rotation in the fiber. Here's what it looks like in the lab. It looks like any optics experiment almost. I hope you can see the fiber down here. It's glowing slightly green, but I know it's difficult, so I outlined it. And the path of the light around the cavity is green in the fiber and then yellow in the bulk components. Of course, this is not an integrated fiber laser. This is a physics experiment designed to demonstrate a new concept. And this is an infrared pumped infrared laser, so it's very boring to the eye, to the human eye anyway. The output comes from a beam splitter and goes to diagnostics. So here's what happens in experiments. If we look at the beam and the spectrum at low pump power, the beam is multimode. This corresponds to tens of transverse modes oscillating, and the spectrum is very narrow. We turn up the pump power. First, we see a bistable state that consists of the continuous wave, or CW state, with a narrow spectrum, bistable with this broad spectrum, which we are identifying as STML, spatiotemporally mode locked. We'll say more about why. You see the spatial profile changes and the spectrum gets much broader. That's an encouraging sign, but a broad spectrum is necessary but not sufficient to make a short pulse. As we go to higher pump power, we now isolate spatiotemporally mode locked states. And this continues until fairly high pump power. Well, now we have a problem. The temporal profile depends on position in the beam. The spatial profile depends on position in the time profile. The frequency spectrum depends on spatial profile. Everything depends on everything. So we really need a 3-dimensional spatiotemporal diagnostic, which I'm not going to have time to talk about today. You can see the problem. What we did was collect all of this information in space, all of this energy in the multiple modes that make up this beam, and focus that into an autocorrelator to get this time profile. And the duration is about 150 femtoseconds, which is approximately the Fourier transform limit of this spectrum, or this spectrum, sorry, which is very encouraging. Furthermore, we measure the radio frequency power spectrum, and we have a nice spike at the repetition rate of the cavity. This is actually 4 different positions on the beam shown here, and they overlay each other, so all 4 positions have exactly the same repetition rate. Another piece of evidence that we've made a mode lock state or a synchronized state. So let's be clear about what we've done. Continuous wave lasing has no control of the fields, so it's fluctuating randomly like this. We've arranged to lock all those phases of the modes, so we've made a field that looks like this at one position inside the cavity. Multiple transverse modes, but completely controlled. Here's what the transition to mode locking looks like in the lab. I'm going to tell you what happens because the video goes pretty fast. We're looking at the output beam. This is a superposition of multiple, approximately cylindrically symmetric modes. Here's the spectrum. It's structured, but you see it's quite, well, it's broad. And we'll show you the pulse train in a moment. Logan is going to block the cavity with his hand. That will extinguish mode locking. You'll see the laser come back on in spontaneous emission and continuous wave operation fluctuating, and then it will undergo the transition to the mode lock state. So he blocks the cavity, and now you see fluctuating spatial profile, highly fluctuating spectral profile, and a narrow spectrum in general. He doesn't do anything to the laser. It spontaneously undergoes this transition to mode locking. And there you see the pulse train in the time domain. Sorry for the home video quality. In a way, this is our new baby, I suppose. So I think, I hope I've shown you that we've succeeded in locking longitudinal and transverse modes of a laser. So what? Who cares? Is this important? We think it's important for a number of reasons. Unfortunately, I don't have time to show you many of them, but there are many new mode lock states. We call it the zoo, and one of our jobs is to figure out which animals in that zoo we think are the most important to study. Of course, if these were all analogs of what we could see in 1D lasers, it wouldn't be very interesting. And there are new phenomena, so they're not, and it will be very interesting. For what it's worth, we lock up to 100 million modes, which is many more than have been locked in any laser to date. And of course, we have almost no real theoretical understanding. So that's the science motivation. Let me say that this is a first step toward complete 3D and maybe even 4D, you would call it, control of the electric field inside a laser. 4D meaning 3D in space and 1 in time. So that's very exciting. And again, I won't have time to go over it, but people always want higher power from lasers. And initial work we've done shows that we should be able to scale the power through the number of modes rather than through the size of a fundamental mode. So there are possible performance implications here too. As I said, we really need, I've shown you very crude measurements of the laser. We need 3D electric field, not just intensity measurements. And we need manageable and intuitive theoretical models. 3D mode locking has never really been done theoretically. We've recently taken a first step at it. It's a very hard problem. So a frequently asked question, FAQ, at this point is often, what's m squared? M squared is the quality factor of the beam. M squared is 1 for a perfectly diffraction limited beam. So of course, that's not the point now. We tried to make a laser that oscillates in many transverse modes, so m squared should be poor. On the other hand, we appreciate the question. A different way to ask the question is, who cares if you make a output beam? That's a fair point from the point of view of applications. So I want to briefly mention another new effect that's been observed in multimode fiber recently that could be relevant here. So imagine you make a highly multimode beam that looks like this, a speckle pattern, and you launch it into a multimode fiber. And this can even have random coupling among the modes. What do you expect to come out? Well, of course, you expect a speckle pattern. Disorder in, more disorder will produce disorder. But look what happens if you turn up the power of the input beam, and not even by very much. The energy condenses largely into the fundamental mode, and part of the energy is roughly equipartitioned among the higher order modes out here. So I'm intentionally using provocative language when I say condense. We all know about quantum condensates, but what do we know about classical wave condensates? This may be some evidence of classical wave condensation. And I'll just say that to intrigue you. This is actually work from Limoges University in France, who did this with nanosecond pulses. In my group at about the same time, we demonstrated this effect with femtosecond pulses. So can we use this in a multimode mode lock laser? This is something a student in my group has been working on. He simulated multimode oscillation through the cavity. Here are some of the mode patterns. And then the idea was have the propagation be multimode in the gain fiber, the active fiber, and then allow that multimode field to propagate through a passive fiber where it could undergo this self-cleaning or beam cleanup to make a good output mode. That could be the best of both worlds, possibly. And in fact, the first step toward this has recently been taken by Professor Psaltis's group in EPFL in Switzerland. They've reached some success on this before we did. So to summarize the points I want you to take away, you can mode lock in space and time, or transverse and longitudinal modes, by strong spatial filtering and spectral filtering inside a laser cavity. Many mode lock states are possible. Again, you only saw glimpses of a few. The potential is there for 3D control of the field and scaling to higher power. And as I mentioned, we've recently put out the framework of a theoretical treatment of this that's intuitive at some level. If you're curious, you can look this paper up. Well, some obvious questions are still there. What about anomalous dispersion? Can we make one of these based on ordinary multimode solitons? In my group, we've developed new temporal pulse evolutions in single mode fiber. Now there's the potential for new spatiotemporal pulse evolutions. I told you about work in graded index fiber. What about step index fiber? That will have its own challenges, but it's also its own advantages. Multi-mode fiber and multi-core fiber are conceptually almost the same, but they have different technical advantages and disadvantages. That could be interesting. I talked about population-based gain, inversion gain. One could conceivably do spatiotemporal mode locking in Raman lasers, where the gain is by stimulated Raman scattering, or parametric gain. And one more idea, I talked about continuous wave mode lock laser, meaning continuous wave pumping, but you could do synchronous pumping. And because the modes, the transverse modes, have different velocities, you could select different modes on the basis of the pumping. This is just the beginning of a much longer list. This looks to me like 3 or 4 student theses already. So there's a lot of interesting work to be done going forward in this area. If you're interested in this and you want to learn about it, we have developed a massively parallel solver for multimode propagation, which is important. And we wrote a paper that includes some tutorial aspects of multimode propagation. You can actually get the massively parallel solver from my group's website if you're interested. So we thank our sponsors for support as always, and I thank you for your attention.
Thank you, Professor Weiss, for this enlightening talk. Now there are some questions. So Tulsi says that she wishes to do mode locking with few mode fiber-based saturable absorber instead of graded index multimode fiber. What are the challenges that are there?
If I understand the question, the idea is to build a mode lock laser instead of with 100 modes, with a fiber that supports a few modes, like 3 or 6, and then use a saturable absorber to do the mode locking. I think this is an interesting idea. Certainly is possible. And in fact, if you look in the first paper we wrote on this, we started by mode locking with a few mode gain fiber and then a highly multimode passive fiber. So I suspect following from that, it should be quite possible. Depending what you use for the saturable absorber, it could be nonlinear polarization, rotation, and passive fiber, or you could conceivably use a structure like a cesium. The properties will be spatiotemporal because of the focus. On the other hand, a cesium typically doesn't have deep modulation depth, and that's highly desirable for mode locking in fiber lasers because the loss and the gain are so large. That's one of the reasons that nonlinear polarization evolution is so attractive in fiber lasers. But of course, many fiber lasers mode locked by cesiums exist. And there are other saturable absorbers for sure.
We have one more question that is that how can we measure 3D electric field?
Very good question. It's hard, but I'll show you. Okay, I'm sorry. I thought I had a slide on this in reserve, but it looks like I didn't keep it. I'll answer the question. The idea is to take the field we want to measure and spatially filter it so that it consists of only a single transverse mode. Then we use that as a reference beam, interfere it with the field of interest. When you do that, you make fringes, and those fringes have information about the spatial modes in the field. This is called off-axis digital holography, and it's a standard technique. There are now several papers. By the way, we're not the first people to develop a 3D electric field measurement technique. I would refer the student to papers on a technique called termites. It's an acronym, TERMITES, which is partly what we follow, and also some papers recently from Rick Turbino's group, who has extended concepts like frog to 3D electric field. I'm sorry I don't have the slide. It would have helped a lot to show you, but the short answer is you interfere the field of interest with a reference beam, and from the fringes you can extract the spatial properties, which you then project on the modes of the fiber.
Moving on to the next question by Dr. Adhi. Can the locking happen with any saturable absorber or only with the NPR?
Short answer is we don't know. 3 or 4 other groups have, or maybe a few more, have followed up on the work that we've done. I can't think of one that used a saturable absorber other than nonlinear polarization rotation, but I'm going by memory. And if you just search forward from our work, I think you'll find, as I said, there are only a handful of papers on spatiotemporal mode locking still. I would recommend looking at papers from Professor Psaltis's group in EPFL, because they have at least a couple out, and it would be a good place to start besides our work. I can't say it will work because I don't know evidence of it. And in general, mode locking is difficult, so I would like to have as much modulation depth as I could. And a deep modulation cesium, for example, is very hard to get.
Next question is from Sandeep. Is it possible to selectively choose oscillating transverse mode by controlling aperture dimension?
Good question. Yes. And again, we're just learning, but let me show you an example. Let's see. Can you see this now? This graph?
Yes, yes, yes.
So this is complicated. It will take me a moment, but this is almost a direct answer to the question. This is, at this graph, only numerical simulation and the theory we recently developed. This shows the modal energy content as a function of the spatial filter size inside the cavity. So for example, for very small spatial filters, what this says is we have blue, red, and black, which are LP02, LP03, and LP01. These are cylindrically symmetric modes oscillating in the cavity, where the dominant one is actually not the fundamental mode, it's LP02, with about 40% of the energy. LP03 maybe a little under 40%, and LP01 maybe 20%. Is that clear? So there's an example. At small spatial filter sizes, we get a superposition of cylindrically symmetric modes, which, by the way, backs up our rationale for designing the laser to work in the first place. Now, as we make the spatial filter bigger, for 15 to 30 micron, you see now the mode decomposition is dominated by LP01. This has about 70% of the energy. And then we also have other cylindrically symmetric modes. And if we go to larger spatial filters, what we see now are the modes that are not cylindrically symmetric coming into the mix of the spatial profile. So we get more spatial mode diversity when we go to larger spatial filter sizes. So this is a first step toward understanding that. It's a further step toward controlling it and designing a laser for a certain thing, but you can see the connection.
We have one follow-up question from Sandeep. Is it possible to do locking with OAM mode, multimode fiber laser?
Very good question. I'm sure many people are thinking about it. Maybe not many, because spatiotemporal mode locking is complex. I don't know the answer. The OAM modes are a subset of any of the eigenmodes. So the answer is I don't see why not. If you think this is interesting, you should investigate it. I'm sure there'd be enormous interest in somebody making a laser oscillating on OAM modes.
Thank you, sir. I don't see any more questions. So if there are any questions, please raise your hand and we'll unmute you. Okay. So I have a question that is, why at high input beam power, self-focusing get balanced by diffraction? Also, does the critical power of the balance changes with the wavelength?
Okay. So let me so diffraction makes a beam spread out, and that doesn't depend on power at all. Self-focusing depends on power. So the higher the power, the stronger the self-focusing. So at low power, of course, diffraction wins and a beam spreads out. As you imagine increasing the power incrementally, you might expect to have self-focusing compensate diffraction, and then at some value perfectly balance it. And that's mathematically true. Unfortunately, the balance is the same as the balance of making a pencil stand up on its point. It's an unstable equilibrium. So in 2D anyway, a pencil in principle can stand on its point, but in practice it doesn't. Or a pendulum can be in the position up instead of down. It's likewise an unstable equilibrium. So it's not possible to get stable in 2D. Instead, what happens is the beam collapses and other nonlinear processes occur. There was a second part to the question and I've forgotten it. Sorry, what was that?
Okay. Also, does the critical power for this balance changes with the wavelength?
Oh, absolutely. In fact, very good question. It goes as the wavelength squared. So at longer wavelengths, the critical power goes up quite a bit. The number I gave was for a wavelength about 1 micron of 5 megawatts in glass. But if you go to 10 microns, it's obviously much, much higher, unless the nonlinear index also changes. But short answer to your question is yes, it goes as lambda squared.
We have one more question from Sandeep. That is, can method of spatial and temporal filtering work for mode locking in OPOs?
We think that's a very exciting direction. Multimode OPO looks like a very interesting, challenging project to do. Again, nobody knows because it hasn't been done, but I would urge the student to pursue this if you find this interesting. If you can succeed, it will have major impact for sure. It's on our list to do. I don't know if we'll get there.
There is one more question from Tulsi S. Working principle of fiber saturable absorber for step index and graded index multimode fiber combination. I think she is asking the working principle. Tulsi, can you clarify your question? I'll request host to unmute Tulsi if she wants.
You want me to mute?
No. So if I understand the question is, working principle of fiber saturable absorber for step index and graded index multimode fiber combination.
I'm not sure I understand the question, but the idea will be the same. for whether it's step index or graded index. I think the question is asking if you were to combine step index and graded index, would it still work? I suppose so at some level, but I think it would be very complicated. And I'm not sure why you would want to do that. One other thing to keep in mind, I'll remind you that in step index fiber, the modal dispersion is at least 10 times larger than in graded index fiber. So it will be difficult to do mode locking in step index fiber, except at very high power. If that doesn't answer the question, I'm happy to try again.
Okay, I can ask the host to open, like, allow the mic for Tulsi, and she can. So you can unmute yourself and ask the question.
Hello. Hello.
Hello.
Good evening, sir. How are you, sir?
I'm good, thank you.
Sir, actually, I am doing mode lock laser all fiber based satchel observer, sir. Actually, I am fabricating my own satchel observer, like combination of single mode step index multimode fiber with grid index multimode fibers.
Oh, now I think I understand what you're doing. You're making the structure that consists of single mode fibers.
Yes, sir. Yes, sir. Exactly.
Yes. Okay. I'm sorry. I didn't appreciate that. Okay. So go ahead. What's your question?
So instead of grid index multimode fiber, I used to do with few mode fiber. What is the difference between the few mode fiber combination and the grid index multimode fiber combination for the satchel observer property?
I don't know specifically. We haven't done that in our group. I would think so. The modal dispersion will be larger. On the other hand, there will only be a few modes. So it's an interesting thing to consider, and it may be possible to lock a few modes. We've never tried to do that case. When we made a laser with few mode supporting gain fiber, we actually connected that to highly multimode passive fiber and tried to excite many modes in that passive fiber. I don't know if anybody has actually tried to make a laser mode locked in just a few transverse modes. You may be one of the first people thinking about this. There's nothing wrong with your thinking. Whether we can say it will work or not, I don't think anybody can say. So you're leading the way on this one.
Thank you, sir.
Good luck on it. You're muted. Ms. Sharma,
Thank
you're
you.
muted.
Thank you, sir, for answering all the questions so patiently. And let's thank the speaker once again. Thank you, sir.
Thank you for your attention. Best wishes to all of you.
Thank you. So with this talk, we conclude today's session. I want to thank all the speakers for their time and participation. I thank everyone in the audience for being present here and asking wonderful questions. Thank you and have a great day ahead. See you all tomorrow online.
Bye.